Now let's see set of all strings generated by any alphabet. Let us say alphabet sigma equal to a comma b. This is the alphabet given, and what can you say about this set containing all the strings which are possible over sigma, which means sigma star. This set which contains all the symbols possible over a comma b is sigma star. And what are all the elements present in this? Epsilon, a, b, aa, ab, ba, bb, so on, isn't it? They are all the strings, and definitely it is infinite. Now we want to find out whether it is countable infinite or uncountable infinite, and what does that depend on? Whether you will be able to come up with a enumeration method. Now let's see what method you want to use. So let us say for some time you forget about epsilon, and let us say it is like all the set of all strings are nothing but, every string is nothing but a word, English alphabet word, English language word. Then if you follow the dictionary order, what happens? In dictionary order you could write them in one order, definitely all these strings. Now if you follow the dictionary order, what happens is, maybe the first element will be a, and the next element will be aa, next element will be aaa, and all these a's will be like this forever. The problem with this enumeration is, with this type of ordering is, if you follow this type of ordering, you will never come across the word starting with B or simply B. B can never be generated in finite number of steps. Therefore, this method, this ordering fails. Therefore, we want some other clever ordering using which we will be able to generate every string even if it is starting with B. So, some other enumeration order which you could use is, maybe you could pause the video and you could think for some time. So, what you could use is, you could go in the increasing order of lengths, which means you could generate all these strings of length 0. Therefore, epsilon will be generated. Next, you could generate all the strings of length 2. So, what are all the strings of length 2? A and B, and inside a particular length, you could use a dictionary order. The reason is, inside a particular length there are finite number of strings. So, if there are finite number of strings, you can use dictionary order, so that you can reach any element in a finite number of steps. So, inside this string lengths of 1, I can arrange them in dictionary order, which means A and B. And now, inside string lengths of 2, I can again use dictionary order, which means AA, AB, BA, BB. And again inside strings of length 3, I can again use dictionary order. AAA, you get 8 strings, right? AAB, ABA, so on, BBB. So now using this method, if you generate every string possible, then what happens is, this one will be generated in 1 step, this one can be generated in 2 steps, this can be generated in 3 steps, 4 steps, 5 steps, 6 steps, so on. Every element in this set can be generated in fixed number of steps. You can give me any number, I can generate in a fixed number of steps. I mean, you can give me any string, I can generate in a fixed number of steps. For example, if you ask me to generate AAB, for example, then after how many steps I can generate it? 7, 8, 9. Therefore, every element is going to get an index, and that index is nothing but mapping into the natural numbers. Therefore, since every number has got a mapping into the natural numbers, we can say that this set is countable. So, the set of all strings possible over any alphabet is actually countable. You can extend it to any alphabet, not just A comma B. The set of all strings possible over any alphabet is always countable. It has a very important implication, and this result is so popular, and this enumeration method is so popular in the this theoretical world, that they have even given this a name. So if you use this particular ordering, it is also called as proper order. Proper order means going in the increasing order of string lengths, and then within the string lengths we can sort them out, isn't it? That is called as proper order. So proper order is very popular, and it has even got a name. This enumeration is very popular, it has even got a name. Now let's see, if a set is countable, There are lots of implications on this. Okay, so if a set is countable, then what can we say? I'll just see what to do this, how to do. So now you understand that the set of all strings possible over sigma equal to a comma b are countable. And now there is one more important rule, that every subset of countable set is either finite or countable. It is very interesting, which means if a set is already known to be countable, if you take a subset of it, then that is also countable. This particular property has very important implications. I'll just discuss them shortly, but then just understand how it is right. Now I'm saying that a set is countable. A set is countable means this particular set S is countable, then this set is having one-to-one correspondence between all the elements and the set of all natural numbers. This is what I mean to say. Already this set is having one-to-one correspondence with the set of all elements in the set of natural numbers. And now if I take a subset of it, subset means I'm taking some subset small s, then subset means only some of the elements will be here. Now already these elements are present in this set, therefore there will be one-to-one mapping between this particular element and the particular element that is already present in this. For example, if in this set S I am going to choose a number or I am going to choose an element from this set capital S and place it here, I will just put a one-to-one correspondence between those two numbers. Now for every element already there is an image here. Image is nothing but itself. Try to understand it. Already a set is said to be countable, therefore it is having one-to-one correspondence with the set of all natural numbers. For every element in this set there is one natural number in this set, which is set of natural numbers. That is what the meaning of countability is. So now what is that I am trying to do is, I'll just find out, or I'll just take a subset of elements of this set. Then what happens is, I am getting some elements in this set, and for every element, how did I get this element? Because that element is already present in this set, isn't it? Therefore I'll put a one-to-one mapping between the element chosen and its image there. Image means the same element. Then what happens is, already I have one-to-one mapping from the subset to the set, and already there is a one-to-one mapping from the set to the natural numbers. Therefore by composition, that is called composition, we shall discuss it in functions. By composition rule, this set is also countable. Therefore every subset of a countable set is countable in case if it is infinite. In case if it is finite, it is simply finite, but then we are not interested in this. We are not interested. So every subset of a countable set is either finite or countable. So this point is very, very important. Okay. Now we already found out that sigma star over any sigma is countable, which means set of all possible strings is countable. And now a language is nothing but subset of this. Every language till now we have seen is nothing but a subset of sigma star, which means either you take a power n, b power n, or a power n, b power n, c power n, or whatever it is. Every language is a subset of this set, and this set is already known to be countable. Therefore every language is countable. Understand it? Every language is countable. I am not talking about number of languages. Given a language, that is definitely countable, which means all the strings in a language can be put in one-to-one correspondence with the natural numbers. Okay, so every language is going to be a countable language, or it is going to be finite language. Okay, write it somewhere. Now let's look at the Turing thesis. Turing thesis says that Turing is a scientist. In 1930s he has proposed a thesis. I mean, it is not a thesis, it is a hypothesis or conjecture, which means he made a statement, and till today, I mean from 1930 till today, there have been various arguments whether he is right or wrong, but then no one is able to prove that he is wrong. Since from 1930 till date, since no one is able to prove him wrong, we started believing that he is right. Okay, so that is what is Turing thesis. In 1930 he made a statement. Till now no one proved that he is wrong. Therefore, since even though there is no proof that he is right, we started believing that he must be right. That is what is it. Now look at this. The thesis actually, okay, one more thing, it is not important for GATE. I just want you to know the concept. I mean, I'm just explaining with theory so that you will understand everything better, but they are not going to ask this in GATE because there is no direct way they could ask this as a question. But then I'll just explain you. What you could do is I'll just finish the explanation, then you could take down the notes, whatever from now on, whatever I say, everything I'll write it down. You please make a note of it, otherwise later you might get confused. I'm going step by step very slowly, and Turing machines is a somewhat difficult concept and explaining it is also difficult. Therefore I am going to write everything on the board. You please make a note of it. Okay, see this. Any computation that can be carried out by mechanical means can be performed by some Turing machine. What it is trying to do is anything that can be done by a mechanical means, which means like a computer, can be done by a Turing machine. Alternatively, it can be stated as Turing machine is as powerful as a computer. That is what the meaning of it. And now, if you have to say that Turing machine is as powerful as a computer, then Turing machine should solve every problem that is being solved by a computer, which means every program that is written on the computer should be implementable on a Turing machine. But then if you have to prove that way, there are infinite programs which are written on computers today. If I had to take every program and then write it on a Turing machine and implement it, you know that, right? Turing machine, even to do a small work like addition, it has to write a very big Turing machine. We have to design a very big Turing machine. Now if I have to take a big program and then implement it as a Turing machine, it is going to be very hectic and you will run out of your patience, isn't it? So it is not going to be a good method to take every problem and convert it to Turing machine and then say that Turing machine is as good as computer. Turing machine is as powerful as computer. It doesn't work that way. Therefore, what is the other way is, maybe you come up with a problem for which there is a program in computers, but then for which a Turing machine doesn't exist. If we can do that, we can say that Turing thesis is wrong. But till now, no one is able to come up with such a problem. Okay, so we started believing that Turing is right, which means he said that anything that can be done by a computer can be done by a Turing machine. Now we are believing it so much that sometimes even Turing machine is used as the definition for computer. So sometimes in place of computer we are calling it as Turing machine, or in order to define the capabilities of a computer itself, we are trying to say that anything that can be done by Turing machine can be done by computer now. See, are you understanding it? It is bit difficult to understand. Just try to understand it. He made a point saying that a Turing machine can do anything that can be done by a computer, and no one is able to disprove it till now. Therefore, we started believing it so much that slowly we are calling a computer as a Turing machine. And you know, it is a basic law, like you know this Newton's laws, right? 3 laws of motion. There is no method or there is no proof proving that these 3 laws of motion are right. Newton's laws of motion are right. No one has proved it. But then we started accepting it and we believe that they are right. The reason is because every experimental result is actually agreeing according to these laws. If you could come up with an experiment in which the result does not agree with the Newton's laws, then you could say that he is wrong. But then as of now, no one did it. That is why that has become the basic law in physics. Similarly, this Turing thesis has become the basic law of computer science, and moreover, Turing has become so popular that the highest award in computer science, we don't have Nobel Prize in computer science. If you do anything great in computer science, you are not going to get a Nobel Prize. But then the scientists who did a lot of work in computer science are going to get the highest award as Turing. Turing award is the highest award. So Turing has become so popular with that statement and with his work that no one is able to disprove it. It has become the basic law of computer science. Okay, and now what are the various arguments which are supporting his law is like this. Some arguments why Turing thesis is accepted as a definition of mechanical computation are: or computer. So now after saying this statement, we don't know how to define the mechanical means itself. A Turing machine is a well defined, which means we have defined a Turing machine with Q, sigma, delta, everything. Turing machine has a good definition, but then we don't have a definition for computer as of now. So it is now becoming difficult to define a computer. So we have to define the computer first. And people, what they started doing is they started using the definition of Turing machine in order to define the computer. What are arguments which are favoring this which are favoring this kind of support is, first thing is, anything that can be done by existing digital computer can also be done by Turing machine. So you give any particular problem P, definitely it can be broken down into small operations, and each of these operations can be performed by the Turing machine. Therefore any problem that is currently done by the computer can be done by Turing machine. So this is one of the argument which is supporting that Turing machine is as powerful as computer. And the next argument is, no one has yet been able to suggest a problem solvable by algorithm but which is not solvable by Turing machine, which means no one has come up with one problem which can be solved by a computer, by an algorithm, but not by a Turing machine. So till now no one has been able to do that. Therefore from now on, whatever definitions we are going to use or say about the Turing machine, they all are depending on the basic assumption that Turing machine is very powerful or as powerful as a computer. In future, if someone comes up with a problem which proves that problem can be solved by computer but it cannot be solved by a Turing machine, then from now on, whatever definitions I am going to say, all these definitions have to be changed. So for using this point, the entire foundation for Turing machines is going to be laid. So whatever definition I am going to say from now on is based on the assumption that no one is ever able to come up with a problem which can be solved by a computer but not by a Turing machine. In future, if someone comes up with a problem, we have to change all the definitions which I am going to teach from now on. Okay, but the chances that someone will come up with such a problem are very less. We are safe that I don't know, maybe someone might come up, but the chances are very less. See, from 1930 till date, no one is able to come up with such a problem. So the chances are becoming lesser and lesser as the years are passing by. So till now we didn't find it, so maybe we might not find it. Who knows? We don't know. Okay. And next one is, alternative models have been proposed for mechanical computation, which means there are various kinds of computers now available and various types of models available, and even various modifications of Turing machines are available, but none of them is able to do much powerful work than the standard Turing machine. So whatever you do to a computer or anything, any mechanical means, none of them is as more powerful than the Turing machine. So as of now, Turing machine, this Turing thesis is valid, which is nothing but anything that can be done by a mechanical means can also be done by a Turing machine, which means anything that can be done by a computer can also be done by a Turing machine. Okay, so better you take down all these points and just keep them in mind. They are not going to ask you in GATE. It might be useful to know about them. Okay, fine. We have already seen a standard Turing machine. A standard Turing machine will look at an input and it will either go to the right or to the left, and if it needs, it might change the symbol and change the state from one state to the other state. That is what we have already seen about the standard Turing machine. Now, apart from this standard Turing machine, we could add we could modify it, and then we could see whether the power means, by talking about the power of a Turing machine, I mean to say the languages accepted by the Turing machine. So whenever I am talking about the power of a Turing machine, please keep in mind that what I mean to say is the number of languages accepted by the Turing machine. That is what is the power. So power of any machine is given by the number of languages that the machine could accept. For example, PDA powerful is, the power of PDA is it could accept many of the languages, but then it cannot accept A power n, B power n, C power n. But Turing machine, on the other hand, we have seen that it could accept A power n, B power n, C power n, and it could even accept A power n, B power n, C power n, D power n. You could extend it to any long, isn't it? We have already seen it. And now by talking about the power of the Turing machine, what I really mean is not the time complexity or space complexity. What I mean is the number of languages that it could accept. Now already standard Turing machine, which we defined earlier, is already able to accept some of the languages. Some languages it is already accepting. Now by giving this Turing machine some extra facilities or some more modifications, let's see the resulting Turing machines, will they be able to accept more languages compared to the standard one. But then it has been found out that even if you give more power, even if you give more facilities or more modifications to the standard Turing machine, still the number of languages which were accepted by the previous standard Turing machine are remaining the same, which means even if you change the standard Turing machine to some other new Turing machine, the languages which are accepted by the standard Turing machine are only accepted by the new machines, which means by doing any modifications we are not actually able to increase the power of a Turing machine. That is what we concluded. So by the theoretical proofs, what people have found out is by increasing the or by doing some modification to the standard Turing machine, we are not able to accept any new languages which are not accepted previously by the standard Turing machine. Whatever were accepted by the previous machine are now accepted by the new modifications. In fact, some of the modifications are actually reducing the power, not increasing the power. But for now, we shall discuss what are the Turing machine modifications, after which the power remains same. Okay, so let's see some of the modifications for the Turing machines here. First one is, see this, Turing machine with stay option. So generally we know that the standard Turing machine will either move to the right or it will move to the left, and then it will change the symbol. But then if you give the power to a Turing machine that it need not move to the right or left, it can even stay, which means along with that these are all the standard modifications to the Turing machines. So first modification is, to the Turing machine I am giving you a stay option, which means if you are in some particular state, your transition function will be, and if you look at a stack, that tape symbol, you will go to some particular state, we are going to go to some particular state, and then we could change the symbol, and now generally the standard Turing machine will move left or right, isn't it? But along with that we could add stay symbol, stay option. Stay option means you need not always move, you can stay at a point and you could just be there, right? If even after adding this option we found out that the power of the original Turing machine, the standard Turing machine, cannot be improved, therefore even a Turing machine with stay option is as good as a Turing machine, standard Turing machine. So that is what we found out. And now next look at the next one, Turing machine with semi-infinite tape. Semi-infinite tape means I told you that standard Turing machine has both sides infinite tape, which means if you are having A, B, C as the input, the standard Turing machine has both sides infinity. That is what we already know, right? Now a Turing machine with semi-infinite tape means it is not infinite both the sides, it will be infinite only one side, which means you cannot move to the left beyond some point. That is not possible, you will fall off the tape. So we found out that by restricting the Turing machine to semi-infiniteness, which means you could move only to the right, not to the left, still the power of the Turing machine, the standard Turing machine, it didn't get affected, which means a Turing machine with semi-infinite tape is as good as standard Turing machine. It is not able to accept any more languages, neither it is accepting less languages. So this is equivalent to the standard Turing machine. And next one is offline Turing machine. So what is offline Turing machine is, we have till now seen that both the input and output are present on the tape, and now the Turing machine has a right that it could modify the input. But then what you could do is, you might not want the input to be modified, then you could have a restriction that, or you could provide the input in a separate file, and now our Turing machine will look at this file and then work on the tape. So which means you have the Turing machine. Now to the Turing machine I will give the input in a separate file, input file, and now this will contain the tape. Okay, now we are going to have this input which is read only. So our finite control of the Turing machine can read the symbols from the input and then it could write it there. So it could either read or write. It is read write only. So if this is the facility given, that is called offline Turing machine. Offline Turing machine means input is given in a separate file. So you are supposed to read the input from a separate file and you are not allowed to modify the input. In case if you have to do some modifications on the input, then you have to first copy the entire input onto the tape and then do the modifications on the tape. But even after your computation is over, the input is going to remain intact on the input file. It is called offline Turing machine. So by having such a kind of arrangement, still we found out that this Turing machine is as good as standard Turing machine. Okay. And next one is multi-tape Turing machine. Multi-tape Turing machine means we are going to have lots of tapes, not just one tape. So with single tape, it is called standard Turing machine. Now if I give you many tape, that is called multi-tape Turing machine, which means I'll have the finite control and then I'll have lots of tapes and I'll have read write heads with that. Okay, now this is called multi-tape Turing machine. So what is the transition function is, you will be in one state and then you will be looking at n symbols. So this small n is number of tapes you have. So in this case, if you have 3 tapes, you will be looking at all the 3 tape symbols. Then you will be going to some state and you are going to write there on the n tapes some symbols that is given by this, and then you are going to either in the n tapes you are going to independently move left or move right. Try to understand this. You will be in one state and you will be looking at n tapes, that is by tau power n, which means tau power n is nothing but from each tape you are going to look at one symbol. Therefore how many symbols are you going to look? N tapes, n symbols, right? And now using this you are going to go to one particular state, and in that state you are going to modify this tape symbol to something tau power n, and then you are going to move either to the left or to the right on every tape, okay, independently. It is called as multi-tape Turing machine. And again it has been found out that the standard Turing machine is as good as multi-tape Turing machine. Whatever are the languages accepted by standard Turing machine, they are accepted by multi-tape Turing machine. Multi-tape Turing machine is not going to add any more power to the standard one, which means to the standard one, even if you give it many tapes, it is saying that I am as good, I could do the same work with a single tape, like even if you give me more tapes, I will not be able to accept any more languages. But then it is interesting, even though the power of a Turing machine is not affected, but there is something different. In the sense, I told you that we are comparing the power of the Turing machine by using the number of languages or by using the languages accepted by the Turing machine. But then by using these modifications, sometimes the time taken to accept any string may be different. I'll just give you an example. Even though both are having the same power, remember that multi-tape Turing machine and the standard Turing machine are having the same power, no doubt in that. But then it could do something better for some languages, in the sense the number of steps required to accept a particular string of some languages might improve using the multi-tape. So you have seen this a power n, b power n, isn't it? Now if I have the input a, b, 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 then how does the standard Turing machine accept it? It is going to go back and forth. So how is it doing it? Make it x and then go front, make it y, go back, and then go like this, and then so it is going to move back and forth a lot of times. But now if you have multi-tapes, if you have more than one tape, you need not move back and forth these many times. You could actually do it in a better way. So in this one, if you just think about the time taken, so in order to accept a power n, b power n, if I have A, so on, and then B, so on, A power n, B power n, then the number of steps required in order to accept is, in order to just match 1x, 1a with 1b, we have to move actually n times, n cells, isn't it? So in order to match up with one pair, the time taken is n steps. Then how many pairs we should match? N pairs. Therefore time taken is order of n square, or the number of steps taken is order of n square. But if we have a multi-tape Turing machine, what we could do is, let us say I have two tapes. Now on one tape there is AA, BB, input is given. Then initially what I do is, I copy the entire input to the other tape. So I'll just copy I'll just copy input to the other tape, which means I'll just copy AA, BB onto the other tape. Then what I will do is, in just one row, see, for copying it is going to be order of n time. You just scan it and then put it there, and after copying it, just set this to here, one read write head to here and one read write head to here, for which time taken is order of n. And you can just simply scan one symbol here, one symbol there, one symbol here, one symbol there, which means in linear time you could actually match them. So by using multi-tape Turing machine, we could actually decrease the time taken in order to process some of the languages. It is true with any Turing machine with a modification. So the power in terms of number of languages accepted is going to be same, but the time complexity required to accept a particular language, that might vary, but that is not going to add any power, because we are defining power in terms of number of languages but not by the time. So every modification is going to be beneficial for some languages, but then overall put together the total number of languages accepted, that doesn't change. Okay, so remember that even the multi-tape Turing machine is as powerful as the standard Turing machine, or standard Turing machine is as powerful as multi-tape one. Okay, and next one is jumping Turing machine. So jumping Turing machine means, till now we have seen that the read write head might move only one step ahead, either to the left or to the right. But now jumping Turing machine, instead of just moving one step ahead, it could in one go move many steps, which means if you have any input like this in the tape, you will be standing here. Generally our standard Turing machine moves only one step to the right or one step to the left, but then this jumping Turing machine can directly jump to any number of steps to the right. So to the transition function, one of the argument is also going to be the number of steps you want to move right or left. In our standard Turing machine, you know that delta is, you will be in one state and then you will be looking at the input, and then you are going to make a decision about what is the state you want to go and what is that you want to write on that input, and then you are going to have either to the move to the left or right, isn't it? Along with this move to the left or right, you could even specify the number of steps, some number n. So you can even move to the left or right, not just one step, you could jump n number of steps. So if you give it as 3, then it is going to jump 3 steps. Again, it is found out that the standard Turing machine and this Turing machine both are equivalent in power, so it is not going to add any more power. Okay, and next one is non-erasing Turing machine. Non-erasing Turing machine means, till now we have seen that our standard Turing machine has a capacity to take an input, and in place of that input, let us say if the input is 0 or 1, in place of that input it could change it to in place of that input, it could change it to a blank, our standard Turing machine, isn't it? But then if you remove that option, which means you are not supposed to change the input to a blank. If you remove that option, then it is called non-erasing Turing machine. The input, whatever is there, you are not supposed to write a blank on that. You could write any other symbol. So if you use that, that is called non-erasing Turing machine. Again, it is also equivalent to the standard Turing machine. Now how is it equivalent is, So whenever, I'll just tell you the proof. Generally, now till now we are saying that all these are equivalent. Then how are they going to prove it is, they will take one Turing machine and they will try to simulate the other Turing machine, which means the standard Turing machine, if it is having a transition function, then for every move of the standard Turing machine, there should be a move corresponding to that in the modified version. That is called simulating, which means if the standard Turing machine is able to do some task, the modified Turing machine should also be able to do that particular task. Now in our standard Turing machine, we have the notion of erasing. It can replace any symbol with a blank. But then non-erasing Turing machine is saying that we are not going to erase anything. Then how is it equivalent to the standard Turing machine is, we are going to use, instead of blank, we can use a different symbol, some other symbol. So instead of capital B, you can mark it as X. So that is not, according to the Turing machine definition, it is not a blank, but according to you, it is a blank. So if you use that, then it is nothing but we are not erasing it, but our task is done. So you know that X is a blank, but Turing machine thinks that it is not erased. Okay. And next one is always writing Turing machine. So our standard Turing machine, we have a restriction that, we have a liberty that if you are seeing a symbol, you can leave the symbol as it is. But always writing Turing machine means, if you are looking at a symbol A, then you are supposed to definitely change that symbol to some other symbol B. That is what the standard Turing, this always writing Turing machine does. Now it can be proved that it can be this is not going to add any power to the standard Turing machine. How can we prove it is? I'm just telling you the proof, it is not required. How can we prove it is? They are saying that every symbol, whenever you visit it, it should definitely be changed. Then what you could do is, if it is small a, just change it to a capital A. But according to you, you know that capital A and small a both are same. But then the Turing machine thinks that, oh okay, it is changed, isn't it? You can cheat it. And later what you could do is, after entire your computation is done, again change it back to small a, isn't it? Therefore whatever result you wanted, you could achieve it, but then giving an illusion to the Turing machine that you are always changing the symbols. It is actually proven that it is not going to add any power to the standard Turing machine, which means standard Turing machine is as powerful as this always writing Turing machine. Now look at this one, multi-dimensional Turing machine. So multi-dimensional Turing machine means, in our tape, instead of having two dimensions, which means left or right, we can even have we can even go up as well as down. So multi-dimensional Turing machine looks like this. It is not just having left and right, it could even move up and down. So let us say your finite control is pointing to a cell like this. Now from this cell, it can move left, it can move right, it can move up, it can move down, isn't it? So multi-dimensional Turing machine, you will be in one state, and upon looking at the input symbol, you can go to some other state and change that symbol if you want, and you could move left, or you could move right, or you could move up, or you could move down. So that is why it is called multi-dimensional Turing machine. And again, it has been proven that it is not going to add any power to the standard Turing machine. Both are equivalent. And next one is multi-head Turing machine. Multi-head Turing machine means it is having only single tape, but it can read from different places at the same time, which means our finite control, it can look at various places simultaneously, and then it can take the decision. Again, it is proven that it is not of much help, so it is as powerful as standard Turing machine. And next one is automata with a queue. So automata with a queue means, if there is a finite automata to which we are adding a queue, then that is nothing but that will be equivalent to the Turing machine. It can be proven that if the finite automata is given a queue is okay, remember that queue is a much powerful data structure compared to the stack. If you have a queue, you could do more compared to what you could do on a stack. Okay, and it can be seen in data structures again. But anyway, you can remember that automata, when it is given a queue, it is as good as a Turing machine. And next one is Turing machine with only 3 states. It is very difficult to prove it. I mean, don't look at the proof. It is going to take a lot of effort to understand it, but then if you could remember it, by heart it. So Turing machine with just 3 states is going to be as good as any Turing machine. How is it possible? We could design a universal Turing machine. I'll tell you that later, but anyway I'm not going to prove it. So it can be proved that when people have already given the proof that a Turing machine, any Turing machine can be minimized. There is no algorithm, but then we can prove it. Any Turing machine can be minimized to a Turing machine which has only 3 states. Okay, so keep that in mind, and if you want to look at the proof, you might have to refer to some research papers. It is going to be very difficult. Forget, don't dig into it. Okay, next one is multi-tape Turing machine with stay option and at most 2 tapes. So if we have a Turing machine which is having multi-tape means you already know. Along with that, if it is having stay option also, then only 2 states are enough. Remember this also, don't dig into the proof. And now this is as good as standard Turing machine. So any standard Turing machine can be converted to a Turing machine with 3 states, first point. And second one is any Turing machine can be converted to a multi-tape Turing machine with stay option which will have only 2 states, at most 2 states. So it is very important, remember these 2 points. And proofs are going to be very difficult, don't dig into it. Next one is non-deterministic Turing machine. You already know that non-determinism means upon looking at one symbol and upon looking at if you are in one state and one symbol, which means you are in one configuration, you can make multiple copies of yourself, which means you can simultaneously go to many states and you could change and you could get many tapes and change the tape configuration, and also you can move to the left or right as you wish. So non-determinism is same as non-determinism in the finite automata. Now coming to finite automata, we have seen that DFA and NFA are both equivalent in power, and coming to push-down automata, we have seen that non-deterministic push-down automata is more powerful than deterministic push-down automata. But coming to Turing machine, here it can be proven that non-deterministic Turing machine and deterministic Turing machine both are same in power. Okay, it is very important, remember this, very important. So non-deterministic Turing machine does not add any more power to the deterministic Turing machine. So both are equivalent in power, but it is contrary to what has happened in push-down automata. Okay, now non-deterministic Turing machine is nothing but you will be in one state and you will be looking at the input symbol, and from there you can split yourself, which means you can make any copies of yourself. A 2 power is nothing but power set, isn't it? You can make any copies of yourself, and each copy can enter any state, and each copy can change its own tape. Every copy is going to get its own tape. Each copy can change its own tape any number of the way it wants, and then on its own tape it can move either left or right independently. That is called non-determinism. But still non-determinism is not going to add any power. Deterministic Turing machine is equivalent to non-deterministic Turing machine. Okay, very important. Deterministic Turing machine and non-deterministic Turing machine both are equivalent in power. Next one is a non-deterministic push-down automata. So to a push-down automata with 2 independent stacks. So you know what is a push-down automata. Push-down automata has only one stack. Now to the push-down automata, if you give one more stack, then it is as good as Turing machine. That is what they say. Okay, understand this. Automata with a queue or push-down automata with one more stack, which means with totally 2 stacks, they are as good as Turing machines. So see this queue, which means generally you know what is a non-deterministic push-down automata transition, right? You please refer to that non-deterministic push-down automata. Let me explain you this here. You will be in some state and you will be looking at the input sigma, or you will be looking at epsilon, and you will be looking at the stack configuration. This tau and tau are nothing but top of the stacks, and you will be looking at 2 stacks, 2 top of the stacks, and from there you could go to any number of, which means you can make any number of copies of yourself. Each copy can enter its own state q, and they can replace the top of the stack with any string they want independently. That is the independent meaning, which means You need not push the same things on both these stacks. If both these stacks are going to be dependent, which means whatever you are writing on one stack is going to be copied on other stack, it is as good as having only one stack, isn't it? But here both are independent. Okay, so remember that whatever points I told you all here, I am not going to give you proof. Proof is going to be very difficult. In fact, for all the Turing machine concepts, I'll just try to explain you in words without any formal proofs. Formal proofs are not required. Coming to GATE, they'll just ask you the statements, not the proofs. For GATE, it is good enough. But if you want to learn more, maybe you might have to refer to the research papers where they have the formal proofs, and it is going to take hell a lot of time. But for GATE, just keep it simple. Understand whatever I'm trying to say. You just take a detailed notes of it and try to mug it up, which means read 2-3 times so that you will remember it. So in this, the most important point is deterministic and non-deterministic Turing machines are equivalent in power. Okay, fine. Now you might have got one doubt. The Turing thesis says that every Turing machine is as powerful as a computer, isn't it? That is what Turing thesis said. So every Turing machine is actually as powerful as a computer. But then what is a computer? It has a power to run any program. But then when I was designing these Turing machines, I was designing the Turing machines for a specific problem, which means a Turing machine which is designed to accept a power n, b power n cannot add two numbers a plus b. But our computer, of our digital computer, it will be able to add two numbers as well as it will be able to do this, isn't it? So there is a basic difference. Our computer acts in a different way and our Turing machine is acting in a different way. You might have got that doubt. When I am saying that Turing machine is as powerful as a digital computer, our digital computer can do many things. So depending on the input program, the program which you give, depending on that, our computer will change its behavior. But then a Turing machine, once it is programmed, which means once I design the Turing machine, it is able to solve only one particular problem and it is not able to solve other problems. A Turing machine which is designed to solve a power n, b power n will not be able to solve a plus b, but our real computer does. Then how can I say that a Turing machine is as powerful as a computer, right? So in order to answer your doubt, in order to clarify why Turing thesis is right, we could do some other thing. So we are going to design a new Turing machine which will act as a computer. In the sense, I am going to design a new Turing machine which will take as input one Turing machine and then run that Turing machine inside this big Turing machine. Okay, it is going to be somewhat confusing. You have to really pay attention here. So what I mean to say is, I am going to design a new Turing machine which will act as a computer and which will answer your doubt and which will prove that Turing thesis is right. What is Turing thesis? Every Turing machine is as powerful as a computer. Therefore, I am going to really design a Turing machine which is as powerful as a computer. So that Turing machine is called universal Turing machine. Universal Turing machine means it is the biggest Turing machine. Okay. Now let's see how does this universal Turing machine works. A universal Turing machine is going to have a finite control, but then it is a multi-tape Turing machine. It is going to have 3 tapes. It is going to have 3 tapes. Let me call one tape as tape 1, tape 1, and other tape as tape 2, and the other tape as tape 3. Tape 3. So it is a multi tape Turing machine, and you already know that multi-tape Turing machine is as good as a standard Turing machine. Then why am I taking multi-tape Turing machine? Is it is, you know, it actually simplifies many things. That is the reason. So in order to implement a multi-tape Turing machine using a single tape Turing machine, it is going to be difficult or complex to explain you how it works. But if I take a multi-tape Turing machine, the explanation will be very straightforward. Now this is entirely a one Turing machine. I want to use this as a computer. Then if it has to be a computer, then it should be able to do any generic work. So what I do is, for example, if I want to add two numbers a plus b, then what I do is I design a Turing machine separately. I'll have a Turing machine separately, and which is written actually to add two numbers. So what will that Turing machine will have? That Turing machine will have a finite control, and along with that it will have a input tape, and on this input tape you are going to put what are the two numbers you are going to add, right? So the two numbers are, let us say, 2 plus 3. Then I am going to represent 2 and I am going to represent 3, and now I want to add it. And now this this Turing machine is going to be designed the way we have already seen it. So this is some other Turing machine, the normal Turing machine, and that is universal Turing machine. Now what will this universal Turing machine do is, it will take this Turing machine and it will store the Turing machine in its one tape. Therefore this tape T1 contains representation of some other Turing machine. Okay, and now what about the input? The numbers, whatever is the input given to the original Turing machine, that input can be saved in the second tape of the universal Turing machine, which means here I am going to put the input, actual input, right? And this tape 3 is used for the rough work. Rough work means, now what we do is, this universal Turing machine will trace out this small Turing machine on this input. While tracing out the Turing machine on some input, what is that we are supposed to remember is what is the present state we are in. So here it is going to save the internal state, which means initially internal state will be Q0. If you assume that let us say initially the internal state is Q1, if you assume that this Turing machine is going to start with internal initial state as Q1, then Q1 will be in this tape, then input will be here. Now you will see Q1 and you will see the first symbol of the input, then you will go to the representation of this Turing machine and you will see for this configuration, which means what is the configuration? Q1, and for the input let us say 1, then delta of Q1 comma 1, then it will go and consult this Turing machine representation to see what should be really done here. Now let us say this Turing machine representation is saying that if this is the configuration, then you have to go to the state Q2 and write it as some other symbol, let us say 1 or 0, and then let us say X something, if you remember that transition. Okay, let us say X, and you might have to move right or left. Then what will this one do is, our universal Turing machine will see this configuration from this representation of the Turing machine, and it will change the internal state from Q1 to Q2. It will just write Q2, so that it will remember that now we have entered the new state Q2, and along with that it will do whatever modifications are specified on the input in this input, which means it will make that 1 as X, and it is asking you to move right, therefore you will move right and you will see the next symbol. Then again what will you do? Again you will see that the configuration is you are in state Q2 and now you are looking at the symbol 1. Then what should be done? Then again our universal Turing machine will visit the representation of our Turing machine and see for this configuration what has to be done. Then appropriately it is going to apply the changes. Got it? Therefore, in order to represent in which state we are in at present, we are going to use tape 3, and in order to represent what is the input we are looking at and what has been done to the input, we are going to use tape 2. And in tape 1 the entire mystery lies. The entire Turing machine, some other Turing machine, has to be saved in one tape. How are we going to do that? That is the mystery, isn't it? So to solve that mystery, what we are going to do is, how can we represent this entire some other Turing machine in one tape, right? So what we assume is, without loss of generality, what we assume is that the original Turing machine has set of states Q as Q1, Q2, Q3, Q4, so on, and the tau means the input alphabet as A1, A2, A3, A4, so on, and A1 could be blank, or we could assume any other symbol. So every symbol is represented like this and every state is represented like this. I'm not talking about a specific Turing machine which is going to add. In general, it can be applied to any Turing machine. So if you have any general Turing machine, you can represent it in number of states and number of this input symbols, I mean the symbols which are allowed on the tape. Then what we do is we encode every symbol. So for Q1, the encoding I use 1, and for Q2 the encoding I use is 1 1. For Q3 the encoding I use is 1 1 1. For Q4 the encoding I use is 1 1 1 1. Similarly, for A1 the encoding I use is 1. For A2 the encoding I use is 1 1, and for A3 the encoding I use is 1 1 1. A4 the encoding is like this. So on I can continue encoding them, right? Now we know that every symbol which is required in these states to represent a state, or every symbol which is required to represent a input, is going to be encoded. There is no problem in using the same encoding for state and then the input, because in transition function we are going to use it. I'll show you how it is going to be easy. Now all the ones are used for encoding, and now I am going to use the symbol 0, this particular symbol, as a separator. So whenever I put a 0, it means that to the left of it there is something else and to the right of it there is something else. Now how to represent a Turing machine is we have to represent its transition function. Now assume that in the transition function I have something like this: delta of, if you are in state Q1, let me write it here. In this transition function, let us say I have something like this: delta of, if you are in state Q1 and if you are looking at symbol A1, let us say you want to go to, the transition is defined as you have to go to state Q2 and make it to A2 and move right if this is the symbol there. Then how can you represent this in terms of zeros and ones is simple. See this, Q1 already we represented as 1 1 and then followed by 0 so that we can differentiate it, and then A1 we already represented as 1 and then followed by 0, differentiate it, and then Q2 is represented as 1 1 and then write as 0 so that you can differentiate it, and then A2 is 1 1, we already seen it. And now for right and left also we could use some encoding. Let us say for left it is 1 and for right it is 2 ones. Then I am going to write it as 1 1. Then again the next symbol is going to follow, right? So using a string of 1 1, I can represent every transition. So the entire transition function for a Turing machine can be represented as a string of zeros and ones. It has a very important implication which we are going to see later. But for now, understand that every Turing machine can be encoded as a string of zeros and ones. Now these strings of zeros and ones will be kept in this T1. Okay. Then how does this universal Turing machine work? If you want to use a Turing machine as an adder, you design the entire Turing machine, and now we have seen that every Turing machine can be represented as a string of zeros and ones, and now that representation is going to be stored in the tape T1. Therefore, universal Turing machine is going to see the actual Turing machine, which means the program which you have given to it, and it is going to see the input, and then it is going to use this tape T3 in order to simulate what happens if this Turing machine actually runs on this input. So that is how this can be used as a computer. Okay. Therefore, Turing is right. A Turing machine can be used as a computer, and Turing machine is as powerful as a today's digital computer, right? And one important point here you should remember is, from all this discussion, you have to remember one important point. Every Turing machine can be represented as a string of zeros and ones, which means you can take any Turing machine and encode all its states and the input symbol into ones and use 0 as a delimiter, and then you could encode the delta. See that transition function is nothing but a Turing machine, isn't it? So if you could represent the transition function in terms of zeros and ones, it is nothing but we are representing any Turing machine in terms of zeros and ones. Therefore, one important point you should remember here, and again we are going to revisit this point, every Turing machine can be represented as a sequence of zeros or ones. Therefore, a Turing machine is nothing but a string of zeros or ones. So how can you represent a Turing machine is, if I have sigma equal to 0 comma 1, and if I construct the language sigma star, then Turing machine is nothing but one of the string of this language. But then just be careful that every string of zeros and ones may not be a Turing machine. Okay, I'll just tell you two statements. Just write it down. One statement is, every Turing machine can be represented as a string of zeros and ones. That is one statement. And the second statement is, not every string of zeros and ones might be a Turing machine. The reason is, if you take a random string, it may not get converted to a Turing machine. But then if you take a Turing machine, we can convert it. Keep that in mind. Okay. Therefore, the Turing machine is nothing but a string of zeros and ones, right? So that is how we have proven that Turing is actually right, that a Turing machine can be used as a computer. So finally, to wrap it out, I have three tapes, T1, T2, T3. At any point, I am going to use T2 and T3 to find out the configuration of the tracing, and then I will use that configuration and I will go into T1 to see how the Turing machine behaves in that configuration. And once I get that transition, I will apply the changes on these two. Got it? That is how our universal Turing machine can simulate any Turing machine on the given input. Therefore, Turing is right. Turing is right. Right? We have seen that by giving a Turing machine more facilities like more tapes, or by giving it more options like stay option, or by giving it determinism or non-determinism, we have seen that we are not able to extend the power of a Turing machine. Therefore, whatever are the languages accepted by Turing machine, the languages are going to be same. We are not able to extend it by doing any more modifications. But an interesting question is, we are not able to extend the power of a Turing machine. Can we limit the power of a Turing machine by restricting the way in which we are going to use the tape? So the interesting question is, what I want to ask is, by limiting the tape, usage of the tape, can we restrict the power of a Turing machine? That is what I wanted to know. By giving it more tapes and by increasing it, giving it more facilities, we are definitely not able to increase the power of a Turing machine. But then my question is, by restricting the way the tape is used, can we decrease the power of the Turing machine? And the answer is, it turns out to be yes. For example, if I have a Turing machine, and now if I have a tape, and on the tape, if I limit the Turing machine, let us say this is a non-deterministic Turing machine. If I limit the Turing machine to use the tape like a stack, which means it can only push it, using a tape as a stack is simple. So you can say that it is the bottom of the stack, the tape itself. And now once you move here, you should always read the top of the stack only, and then you should write something there. So that is how. So if you limit the non-deterministic Turing machine in such a way that it can use the tape like a stack, then it converts to a PDA, isn't it? If I limit the tape to be used as the stack and given non-determinism, then it will act as a push-down automata. And what if I limit the tape not like a stack, but then if I give a Turing machine a tape, and then now I ask it not to use the entire tape, it has to use only a finite amount of tape, which means only this part. It should not use beyond that. Then it is nothing but it is a finite automata with a finite amount of memory. Therefore, it will boil down to finite automata. Okay. So things you should remember is, here, if I have a Turing machine which is non-deterministic Turing machine, the reason is push-down automata can be non-deterministic as well, and we know that non-deterministic push-down automata is more powerful. So if a Turing machine has to act as a non-deterministic push-down automata, at least the finite control should be non-deterministic. Therefore, if a non-deterministic Turing machine is given the tape, but then is given the tape but then it is restricted to use the tape as a stack, then it is just as good as push down automata, PD, which is nothing but it is as good as push down automata, which is nothing but non-deterministic push down automata. Okay, and now if we restrict a Turing machine, tape of the Turing machine to a finite size, which means we are not going to let it use let us say the finite is fixed, whatever is the size of the input given, we are always supposed to use that finite amount of cells, let us say 10 cells. It is not supposed to use beyond that 10 cells or 20 cells. I'll fix it in the beginning, and the Turing machine should use only those fixed amount of memory, then it is nothing but a kind of finite automata. You remember, finite automata has a capacity to remember only finite memory, which means inside its transitions, whatever is present, that is the memory of the finite automata. Therefore, if I have the Turing machine with the tape as at the restriction that the tape is finite, it is not infinite on both the sides, therefore Turing machine is not supposed to use infinite length tape. If I have that restriction, then the Turing machine will just become a automata, finite automata, right? So these are interesting, isn't it? So we are able to restrict the power of a Turing machine by restricting the way it is going to use a tape. And one interesting modification is, what if I restrict, what if I say to a Turing machine that it can use the tape, but then it can use the tape only in the part on which the input is present. Understand this? So now I am going to restrict a Turing machine in such a way that it can use the tape, but then on the tape it can use only the part in which the input is present. For example, if the input is AABB, then if I restrict the Turing machine in such a way that I'll put these enclosing symbols here and here, and our Turing machine is not supposed to cross these points, and it can use only this space in which the input is present, that will be an interesting modification, and that is called as linear bounded automata. Therefore, a linear bounded automata is nothing but a Turing machine, but then which is restricted. Restricted means it is not supposed to use beyond the input. Therefore, it is supposed to use Turing machine only, but then on the tape it has to use only the part in which input is present. Now, what is the difference between this one and the finite memory is, finite means whatever is the size of the input, the Turing machine is supposed to use only a fixed number. It doesn't vary according to the size of the input. But then if I have this linear bounded automata, the Turing machine will get the opportunity to use large memory in case if the input is large, and less memory in case if the input is less. Therefore, for smaller strings, the Turing machine will get the opportunity to use only small amount of memory, the tape, and for bigger strings it will get a opportunity to use big strings. Okay, now it is called linear bounded automata. And now we found out that this linear bounded automata is less powerful than Turing machine. Okay, so understand this. Now we have got a new machine which is not finite automata, which is not push down automata, which is called linear bounded automata. What is linear bounded automata? It is a Turing machine which is modified in such a way that you are not supposed to use anything other than the input. So wherever the input is given, you are supposed to use only that input, not beyond that. Okay, that is called linear bounded automata. And now some important interesting things about linear bounded automata is, it is definitely powerful than push down automata. I'll just give you one example which cannot be accepted by push down automata, which will be accepted by linear bounded automata. For example, if I have a power n, b power n, c power n, we clearly know that it cannot be accepted by a push down automata. The reason is we have c power n. A power n, b power n can be accepted by push down automata, remember? And now this cannot be accepted, this can be accepted by linear bounded automata. How? Now the linear bounded automata has the facility to use the memory or the tape on which the input is present, and we are lucky that for this language, in order to accept it, we don't need any extra space. We just see the A, mark it X, see the B, mark it Y, see the C, mark it Z, and again come back and do the same. Therefore, we are never crossing the boundaries. Therefore, this language can be easily accepted by linear bounded automata without using any extra space other than the input. For example, if the input is AA, BB, CC, and if there are bounds on either sides, then linear bounded automata can simply use only this space and accept it. How? Make it X, make it Y, make it Z. Make it X, make it Y, make it Z. Over. It need not go beyond it. It need not go beyond the end markers. They are called end markers, right? So I have given you one language which can be accepted by linear bounded automata and which cannot be accepted by push-down automata. Therefore, we can say that linear bounded automata is more powerful than push-down automata. But then it is not the actual proof. I cannot say like that. The reason is, if I have to say that linear bounded automata is powerful than push-down automata, then linear bounded automata should accept every language that is accepted by push-down automata. I didn't show you that. But then just go with this and remember it that linear bounded automata is more powerful than push-down automata, and the proof is going to be very, very difficult. So don't get into the proofs. For now, just understand that linear bounded automata is more powerful. And if you want the proof, I'll just give you a hint of how to prove it. Now already we are having that memory, right? The tape. You just change the tape into a stack, and you will never need more than the size of the input as a stack to solve any problem in push-down automata. Okay, I don't think that you will understand it. If you understood it, it is fine. Otherwise, leave it. I'll just repeat it. You can rewind the video and watch it once again. I'll just repeat it. If you understand it, it is fine. I'm saying that a push-down automata can solve any problem that it can accept any language that it wants to accept by not pushing more than the size of the input onto the stack. Therefore, you can use the linear bounded automata in such a way that you convert the given tape with the given input into a stack, and already we know that tape is as big as the input. Therefore, the stack is as big as the input. Therefore, any problem that can be solved by push-down automata can also be solved by linear bounded automata. Anyway, if you didn't understand it, leave it. Okay, so only thing you should keep in mind is linear bounded automata is also a Turing machine with just the restriction that it should not go out of the bounds. That is why it is called linearly bounded. It is linearly bounded to the size of the input. Whatever is the size of the input, you just use that space. Don't go beyond it. Okay, and now it is powerful than push-down automata, but powerless compared to Turing machine. Therefore, if you compare about the powers of all the machines that we have seen till now, so one thing is finite automata is less powerful than push-down automata, and push-down automata is less powerful than linear bounded automata, and linear bounded automata is less powerful than Turing machine. Why? Turing machine doesn't have any restriction. And coming to the case of determinism and non-determinism, finite automata is equivalent both the versions, deterministic as well as non-deterministic. It is equivalent. And push-down automata is not equivalent coming to deterministic and non-deterministic. Non-deterministic is more powerful than deterministic. And coming to Turing machines, both deterministic and non-deterministic Turing machines are equivalent in power. You please keep noting it down. And coming to linear bounded automata, we don't know. Coming to linear bounded automata, we don't know whether a deterministic linear bounded automata is equivalent in power to non-deterministic linear bounded automata. But whenever I am comparing about the power of linear bounded automata and then push-down automata, I am assuming that the linear bounded automata is non-deterministic in nature. Otherwise, I cannot say this. And we don't know what is the power of a deterministic linear bounded automata. We didn't find it out. So just understand that no one right now knows whether linear bounded automata, deterministic and non-deterministic versions are equivalent or not. Again, finite automata is equivalent, deterministic, non-deterministic, note it down. And push-down automata not equivalent. And linear bounded automata undecidable, no one knows whether they are equivalent or not. And Turing machines, they are equivalent. Okay, And when I'm talking about the powers, I'm talking about taking them as non-deterministic machines in all the cases. In case if I take deterministic linear bounded automata, I might not be able to compare it with push-down automata. So my assumption is, when push-down automata is non-deterministic, let me take a non-deterministic linear bounded automata and compare with push-down automata. Okay, so that is how we can compare all the machines. So we have got now nearly 4 classes of machines, isn't it? Finite automata, push-down automata, linear bound automata, and Turing machine. And again, each machine can be divided into 2 classes. Therefore, there are totally 8 types of machines: deterministic, non-deterministic, deterministic, non-deterministic. So in everything we have 2 versions, right? So that is how the machines can be classified and the powers can be given. Okay. So I told you that linear bounded automata is more powerful than push-down automata. Therefore, any language that is accepted by PDA will also be accepted by linear bounded automata. And apart from that, there are some other examples, standard examples. These are the standard examples which you might by heart. They didn't ask any such question in the gate, but then they might ask. So to be in safer side, you could by heart this. These are some of the examples of the languages which are accepted by linear bounded automata. Okay. A power n, B power n, C power n. It can be extended. You can put even D power n and anything. Okay, which means using this space you can actually accept it. And A power n factorial and A power n such that n is equal to m square, which means n is a perfect square. And then A power n, n is a prime. A power n, n is not a prime. WW. It is an interesting language. WW means there has to be a string followed by the same string. In order to accept this, what our Turing machine should do is, it should be able to find out the center. I'm not going to give you the proof, but then I'll just give you a hint about how to find out the center. What you could do is, mark the first, if the input is small a, small b, then you change it to capital A, capital B. If the input is small a, small b like this, you change it to capital A, capital B in order to mark it. So how to find out the center is, if the input is given as AAB, AAB, now you first change the left side, this one to A, and go to the right end, change it to B, this one to A and this one to A, this one to B and this one to A. So whenever you come across this, you can say that this is the center. So how to remember the center is simple. So you keep on marking the left side, left and right end, left and right end like this, and whenever these 2 ends meet, that is the center. And once you have identified the center, then just see if from the center, if 2, you can start matching like this. You can mark the center and you can start it. Proof is not important, I just given it for the sake of explanation, but then nothing is going to be asked like this in gate, so proof is not important. Maybe if you can by heart these examples, it is better. And other is W power n. So here also you should find out what is the size of the n, right? What is the size of the W? Then only you can see how to compare each one. And again W, W, W power r. So you can extend these languages, but these are the standard models. These are the languages which are accepted by LBA, apart from the languages which are already accepted by PDA. Anything accepted by push-down automata can be accepted by linear bounded automata. Just remember these examples. Okay. Now, like the regular languages and context-free languages, is there any name for the languages accepted by Turing machine? That is the question, which means the set of all languages accepted by Turing machine, what do we call them? So they have named them as recursively enumerable languages. Recursively enumerable languages, which means if for a language there is a Turing machine, or if a language is accepted by a Turing machine, then that language can be called as recursively enumerable languages. But just keep in mind that whenever I am discussing about all this, I am going to say that Turing machine is powerful than push-down automata. Therefore, context-free languages are a subclass of recursively enumerable languages, which means any language which is accepted by a push-down automata can also be accepted by a Turing machine. Therefore, by definition, context-free grammars or context-free languages should be present inside the recursively enumerable languages. But Turing machines doesn't have the power to accept epsilon, which means null string will not be accepted by Turing machines, but then null is present in push down automata, which means they are present in context free grammars, context free languages. So whenever I say that the context free languages are subset of recursively enumerable languages, just keep in mind that I am not considering the languages having epsilon. So epsilon doesn't make a lot of difference. So you can remove epsilon from all the languages, and then whatever I am going to say is going to be valid. So just for the sake of epsilon, I don't want to miss out this comparison. That is why we are not talking about epsilon from now on. And my assumption is that any language that I am going to talk about is not going to contain epsilon. Okay, just keep that in mind. Now, any language that is accepted by Turing machine is called recursively enumerable language. That is what I am saying. And if there is a Turing machine, what does it mean? Okay, first of all, what is a language? First we are going to define sigma, and then we are going to define sigma star. Sigma star is nothing but set of all strings possible, and a language is nothing but subset of sigma star, which means a language is this. Now whenever I say that there is a Turing machine for a language, it means that to a Turing machine, if I give any string from this language, it is going to say yes, the string is present in the language. If you have such a machine, then it is called as recursively enumerable language. But then the problem with a Turing machine is it may not halt. It may sometimes fall in infinite loop. Okay, so you please write down whatever I am saying. Whatever I speak, you just write it down so that later it will be easy for you to understand. And now, if a string is not in the language, which means if the string is not present in the language, and if I give such a string to the Turing machine, then the Turing machine may say no, which means it may halt and say no, which means it may halt in a non-final state, or sometimes it may fall in infinite loop. This is the problem with Turing machine. So understand this. For a language, if there is a Turing machine which is accepting the language, then it is called recursively enumerable language. But the problem with Turing machine is, if a string is present in the language and if I give it that string, it will stop and say yes, the string is present in the language. But if the string is not present in the language, if I give it such a string, it may say no. Sometimes if you are lucky, it will halt and say no, and sometimes it will fall in infinite loop. It will say that I am still processing, you please wait. Now you have given a string to a Turing machine. It is saying that I am still processing, you please wait. You don't know how much longer to wait. Maybe if you wait for some more time, it is like this. Maybe you might have seen this problem when you are calling this customer support will be there. I think Airtel or something. Airtel, whenever you call them to speak to a customer service representative, you will be waiting in the queue, and they will say that please wait, we are going to attend your call shortly. Now let us say you have waited for half an hour, and now you don't know whether to disconnect it or not. The reason is they are asking you to wait, and you don't know what is your number. Maybe if you wait for one more minute, you might get the call, or if you disconnect now, who knows, maybe the call is it might take one more hour, and disconnecting it is the right choice. So we never know that. Similarly here also, you understood the correlation. I am saying that you call some customer service representative and they are not answering your call, they are putting your call on hold. Now how long should you wait? They are asking you to wait, but you don't know how long is it going to take. It might take forever. They might answer in 1 minute, they might answer in 1 hour, or they might never answer, and you have to keep on waiting throughout your life. So what is that you are going to do? If you cut the call, who knows, maybe in 1 hour or maybe in 1 second they might attend the call, and you are just waited so long and you are just stopped it there. Similarly, whenever Turing machine falls in infinite loop, the problem is we don't know whether to wait or whether to stop the Turing machine. If you wait in a hope that answer might be just in the next step, then you might be wrong and you might keep on waiting. But if you stop it, sometimes what happens is answer might be actually in the next step and you have stopped it. So you don't know that. That is the problem with the Turing machine. Understand it? Now, I don't want such a dilemma. What I want is, I want a Turing machine which should definitely say yes or no. It should never fall in an infinite loop, which means It should take some time, any time, I don't care, but then it should say yes, it is present, or no, it is not present, which means if I restrict a Turing machine in such a way that I'm going to ask the Turing machine more specifically, say yes or no, don't please fall in infinite loop. If I ask it in such a way that, then what happens? See this? Now if this is the sigma star set of all strings possible, and if it is your language L, and now there is a Turing machine. Now this Turing machine is designed in such a way that if any string is given from the language, if the string is present in the language, it will say yes, this string is present in the language. If the string is not present in the language, if it is given to the Turing machine, if it says no, and it is not going to fall in infinite loop. If such is the characteristic of the Turing machine, then this is called as halting Turing machine. Halting Turing machine. Okay, so halting Turing machine means a Turing machine which always halts wherever or whatever the input string is. Either you give the input from the language or you give the string input outside the language, it is always going to halt. If the string is present in the language, it is going to halt in the final state, and you can say that yes, the string is present in the language. If the string is not in the language, it is going to halt in a non-final state, and you can say that no, the string is not present in the language. Okay, so understand the difference. Now recursively enumerable language means if there is a Turing machine, I don't care whether it is halting machine or non-halting machine, if there is a Turing machine for a language, then I can say that the language is recursively enumerable. Then there is a subclass of languages where the Turing machine always halts. If the Turing machine always halts, it is called halting Turing machine. If for a language, if there is a halting Turing machine, then such language is called recursive language. Recursive language. Okay, so try to understand the difference. If there is a Turing machine, then the language is recursively enumerable. If there is a Turing machine which always halts, if I add that one more statement which always halts, then that language is called recursively enumerable. Sorry, recursive language. Therefore, you can think of the languages like this. If this is all set of languages which are recursively enumerable, which means these are all the set of languages for which there is a Turing machine definitely, then the set of all languages which are recursive will fall here. Regular languages are different and these are different. Recursively enumerable means there is a Turing machine, and recursive language means there is a Turing machine which halts. Therefore, by definition, every recursive language is a recursively enumerable language. Why? Because recursive language, enumerable language says that if there is a Turing machine, I don't care about anything, it is a recursive enumerable language. And now recursive language says that yes, there is a Turing machine which halts, but then it doesn't care whether it is halting or not. Therefore, every recursive language is recursively enumerable language, but then the reverse is not true, which means I cannot give you if a language is recursively enumerable, it need not be recursive language. The reason is the Turing machine, that particular Turing machine might not halt. Okay, so depending on this halting, we have got two types of languages. One is called recursively enumerable and other is called recursive languages. And there is already, we have already seen that there is one more language which is linear bounded automata, isn't it? Now the language accepted by linear bounded automata is called context sensitive language. Context sensitive language. And context sensitive language falls here. Therefore, linear bounded automata is a halting Turing machine. Okay, so now I have told you that there are three types of languages. One is if there is a Turing machine, that language is called recursively enumerable. Second is if the Turing machine halts, that language is called recursive language. And third thing is if the Turing machine halts as well as it is going to use only a part of the tape on which the input is present, then that is called context sensitive language. Okay, so if you look at the entire languages, now I have added three more languages. You already know about regular languages and you already know about context free languages. Now I have added three more languages. Now what I will do is I will show you the relationship between all these languages without any confusion. So if there is any confusion, just revise it one more time. You just play the video once again and just go through this. What I mean to say is Turing, the biggest language power set is this recursively enumerable, inside that context sensitive. Anyway, I'll just show you now with a big diagram about what are the machines and then what are the languages, corresponding languages. Okay. Now let's see what are all the types of machines we have seen and what are the languages associated with them and what are the grammars associated with them. So just follow the way I am going to construct the diagram. The way I construct it is going to answer lots of questions, so just follow it closely. See this. Now let us say this is the set of all Turing machines. Then the languages accepted by set of all Turing machines are called, let me call it as recursively enumerable languages. So what does it mean? If a language is going to have a Turing machine, I don't want to know anything about the Turing machine, what type of Turing machine it is, deterministic, non-deterministic, halting, non-halting, nothing. If it is having a Turing machine, then that language is called recursively enumerable language. Then the subset of machines, Turing machines, which will always halt. The subset of Turing machine which will always halt, they are called halting Turing machines. Now the languages accepted by these halting Turing machines are nothing but subset of recursively enumerable languages, and these languages I call them as recursive languages. Recursive languages. So Turing machines correspond to recursively enumerable languages and halting Turing machines correspond to recursive languages. Okay. And now this subset of the machines, these Turing machines, which will use only the stack or the tape which is limited to the size of the input, that is called linear bounded automata. And the languages that are accepted by this linear bounded automata are called context sensitive languages. Context sensitive languages. Okay. And whatever language is accepted by linear bounded automata is also called as context sensitive language, which will be subset of it. Right. And now the subset of the language, these machines, one of the subset is non-deterministic push-down automata, or let us say only push-down automata. Why to put one more? Or okay, let's put non-deterministic push-down automata into picture here. So our space is not going to be enough. Let's see, non-deterministic push-down automata, and these languages are called set of all context-free languages. Right. And now a subset of this non-deterministic push-down automata is nothing but a deterministic push-down automata, and the languages accepted by this deterministic push-down automata are nothing but deterministic context-free languages. Deterministic context-free languages. Deterministic context-free languages are actually a subset of context-free languages. Okay. And now finally, the machine which is subset of this deterministic context-free language push-down automata is finite automata, and the languages accepted by that machine is regular languages. Okay, so understand this. Now the way I have constructed the diagram will explain you some few things. Now every recursive language is recursively enumerable language. The reason is, if there is a Turing machine which halts, that is enough to say that there is a Turing machine. Therefore, by definition, any language which is having a Turing machine is nothing but recursively enumerable. Now every context sensitive language is recursively enumerable. The reason is context sensitive language is nothing but a Turing machine. It is a language accepted by a Turing machine which is bounded to use only the input part. So since there is a Turing machine, it is also recursively enumerable, and moreover this context that linearly bounded automata is supposed to halt. Therefore it is a subset of recursive languages. And next thing is context-free language. Now I told you that we can modify the Turing machine in such a way that the Turing machine can be used, or the Turing machine can be modified in such a way that the tape can be used as a stack. Now when we are using the tape as a stack, it is nothing but the push-down automata. Therefore push-down automata is nothing but a Turing machine which is going to use the tape as a stack. Therefore every context-free language is also a recursively enumerable language. And moreover, regular language is nothing but a finite automata. The language accepted by finite automata, and finite automata is nothing but a Turing machine in which the tape is limited to the finite amount of space. So if I do such a modification to a Turing machine, since that is a Turing machine, it is recursively enumerable. So you can answer all the questions. So questions will be like this: every regular language is context free, and every context free is context sensitive, every context sensitive is recursive, every recursive is recursively enumerable. That is the relationship between the languages and the machines. Now let's see the relationship between the machines, languages and grammars. We have already seen some few grammars. So one type of grammar which we have already examined is regular grammar. So regular grammar are the grammars which will generate the regular languages. And next one is context free languages. So for context free languages, we already have the grammar. Don't distinguish between the deterministic and non-deterministic context free languages. You can say that context free grammars, CFG, are the grammars which are associated with context free languages. And next one is context sensitive languages. Let me check where it is. Next one is context sensitive languages. Therefore for context sensitive languages, the corresponding grammar is context sensitive grammar. And next one is recursively enumerable languages. For the recursively enumerable languages, the corresponding grammar is unrestricted grammar. Unrestricted grammar. We have basically these 4 types of grammars, and you need not worry about recursive languages or deterministic and non-deterministic context free languages. But then basically we have these 4 types of grammars. It is also called as type 3 grammar, type 2 grammar, type 1 grammar and type 0 grammar. Now we shall see more about this each of these languages and more about each of the grammars. Okay, so you can now understand what is the relationship between various machines, and then what is the relationship between machines and the languages and the grammars, and therefore what is the relationship between the machines and the grammars. Okay, so we have got all these languages now, all these machines. Now let's see the properties of them. So the way I want to examine it is, I'll come with the Turing machines and then halting and then linear bound automata. And however, you already know about finite automata, push-down automata and context-free languages and regular languages, context-free grammars and regular grammars. Only thing you are supposed to know is what is Turing machine and then what is the language associated and what is the grammar. So let's talk about the grammars associated with Turing machines and linear bounded automata. Okay. Now look at this type of grammar which is called unrestricted grammar. So I told you that the languages accepted by Turing machine are called recursively enumerable languages, and the grammars which will generate these languages are called unrestricted grammars. Okay, so just keep that in mind. The languages corresponding to Turing machine are recursively enumerable, and the grammars corresponding to this recursively enumerable are unrestricted. Maybe write it down. Languages corresponding to Turing machines are called recursively enumerable languages, and the grammars associated with this recursively enumerable languages are called unrestricted grammars. Okay, this is the relation. Now watch this. A grammar is called unrestricted grammar if all the productions are of form U derives V, which means if I have all the productions like this, then it is called unrestricted grammar, where U is in V union T plus. So what does it mean? The left hand side can contain any number of variables as well as terminals, but only restriction is that left hand side should not contain any epsilon. The reason is there is plus, it is not star. Just keep that in mind. The left hand side can contain anything, only restriction is that it should not contain any epsilon, which means the null string should not derive any other string. That is the meaning of it. Except other than that, you can have any number of symbols on the left hand side. You can have only terminals, or you can have only variables, or you can have a combination of variables and terminals. Anything is fine, but either, and they can come in any order, that is okay. Nothing is, no, there is nothing wrong, but only thing is you just see that there is no epsilon in the left hand side, and the right hand side is completely unrestricted, so you can have anything including epsilon in the right hand side. Okay, so if you have such a grammar, it is called unrestricted grammar, right? Now let's look at this one. What language does the following unrestricted grammar derive? So they have given some unrestricted grammar. Okay, first of all, is this unrestricted grammar? Just check this. Left hand side could be anything, any combination of variables and terminals, and right hand side could also be any combination of variables and terminals, but the left hand side has to be a non-null, as it is unrestricted grammar. And one more thing, unrestricted grammar can derive epsilon, which means empty string, but I told you that according to the definition of Turing machine, it doesn't have a capacity to accept epsilon, because if there is nothing, we cannot define nothing on the tape. There is a symbol called as B. Therefore, Turing machine is not configured in order to accept a empty language. But then here I am showing you that this unrestricted grammar is going to derive all the languages accepted by the Turing machine, which means it is able to accept even epsilon. It is able to generate even epsilon. But then our Turing machine does not have epsilon. So just keep in mind that I am just talking about the languages in which there is no epsilon. Completely throughout the discussion of this topic, keep in mind that I am talking about the languages which are not having epsilon. Okay. Now let's see this one. They are given you this grammar, and they are asking you what is this one deriving. So just look at this and try to understand it. So by reading the grammar, you should be able to understand it. In case if you don't understand the meaning of it by reading the grammar, the next step is try to derive all these strings, and then you see the pattern and you identify it. Let's try to read it and understand it if you could. Okay. First one is S derives S1 followed by capital B, and S1 is A S1B. So you might have seen such a kind of grammar previously in context free grammars. Now what does S1 derive? A power n, B power n, isn't it? Now what is capital B doing? It is taking 1B and it is generating 3Bs, which means it is simply taking 1B and it is replacing with 3Bs. Next time again it will take 1B and replace with 3Bs. So it is actually increasing the Bs with a common ratio of 2, which means that in AP the common difference is 2. It is taking 1B and every time it is incrementing it by 2Bs. So initially if there is 1B, then later it will be 3, and later it will be 5, and later it will be 7. So it is going to increase like that, and or B is going to simply generate null, which means B can terminate at any point. Initially it will take 1B, it will keep on expanding it by incrementing 2, 2, 2, 2 like that, or it can stop at any point. And AS1B is reducing to AA, which means S1 is taking 1A, 1B and combining AB to AA. So S1 is reducing the number of Bs or converting one AB into AA. So if you could understand this, it is simple. S1 is nothing but A power n, B power n is generated by S power S1, and at last it is going to dissolve one AB into AA. Therefore S1 is going to generate A power n plus 1 followed by B power n. So finally this S1 is able to generate A power n plus 1. Why plus 1? The reason is it is going to take a AB and it is going to convert it into AA. Therefore at the last step, even though initially A power n, B power n is generated, at the last what happens is number of A's are going to be increased by 1 and number of B's are going to be decreased by 1. And later what is B is trying to do is B can add any number of B's. So B can take 1B from this and then it will keep on adding 2 more B's. Therefore B power 3K, isn't it? So if you didn't understand this, the explanation, what you could do is you can just look at all these strings generated by this and you can guess it. Now one derivation is giving us AA, other derivation is giving us AA followed by B's. So if you look at this pattern, you could write like that: L equal to A power n plus 1, B power n plus k. A power n plus 1 and B power n plus k, where n is greater than or equal to 1. So you could work it out. What you do is you generate many strings from this language, and then you can check that this equation is going to be followed by all the strings generated. You can just check it. So in the options, what you do is, if all the options are given, you just generate all the strings and then take every string and see that it is following that rule or not, right? Okay. A grammar is said to be context sensitive if all the productions are of form x derives y, where x comma y belongs to v union t plus and mod x is less than or equal to mod y, which means a grammar is said to be context sensitive if you have all the productions of form like this, and x and y, they both belong to v union t plus. So x and y can be any combination of variables and terminals, but only restriction is either in the left hand side or in the right hand side we are not going to allow epsilon at all, because both of them are going to belong to v union t plus. That is the main difference between unrestricted grammars and context sensitive grammars. In unrestricted grammars, what we had is, in the right hand side we are allowing epsilon, but here we are never allowing epsilon. And now look at this this restriction. The left hand side, the length of the left hand side string is always less than or equal to length of the right hand side string, which means we are always going to expand the derivation. So whenever we take the left hand side and when we substitute with the right hand side in the process of derivation, the string length will always be in the increasing order, which means at every step of derivation we see that the length of the derivation, the length of the string either remains same or it is going to increase. Are you understanding it? See this, the left hand side length is always less than or equal to right hand side length, which means if you replace a string x with a string y in the derivation procedure, what happens is, in the process of derivation, whenever you replace it, either the string length is going to be constant, is not going to change in case when string lengths are same, or the resulting string length is going to be increased in case if the string length of the right hand side is more. So what does it mean? Always the grammar is non-contracting, or non-contracting means it will never contract, it will always expand, or it will remain same. It is called non-contracting. Okay, and then I think it is obvious to see why it is why it is called context sensitive. The reason why it is called context sensitive is, if I have a production in context free grammar, it is A. It is context free in the sense, wherever you see capital A, you can replace it with small a. This grammar is called context free, remember? And capital A derives small a is context free because wherever you see capital A, you can replace with small a without worrying about the context in which capital A has occurred. But then in this one, if I have something like this, A B derives A B, then it is not actually replacing capital A with small a, which means you cannot remove this production and you cannot add this production directly, even though it is looking obvious that capital A is going to be replaced by small a by this expansion. It is not true. Actually, capital A is going to be replaced with small a only in the condition when capital A occurs when its left hand side is a, small a, and its right hand side is small b. It is nothing but context sensitive. So we are going to do this replacement only in the context where capital A has occurred between a small a and small b. Then only we are going to replace capital A with small a. So we are not, it is not straightforward. It is not context free. That is why it is called context sensitive. So the grammar is called context sensitive because we are going to apply many of the rules looking at the context in which a variable is occurring. It is not that every time there is capital A we are going to do it context free. Got it? That is why it is called context sensitive. We shall see an example of how to use the context sensitive grammars, or how they look like, and how we can do the derivation. Okay, we shall see an example. Let's look at an example of context sensitive grammar. But before going ahead, I'll just tell you a few points about this unrestricted and context sensitive grammars. First thing is, these two are very difficult to write. It is not very easy like we have practiced with context free grammars. These are very difficult to design, and there are only a handful of examples available. There are not lot of examples available, and one good thing is, till now they have not asked any question about these grammars in GATE. Till now no question has been asked, and maybe to be on the safer side, I'm just explaining you how they work. But then I don't think that if they ask you such a question in exam, GATE exam, to design the grammar, it is very difficult. Maybe they might ask you a question like this: given a context sensitive grammar, what is the language generated by this? They'll ask you such kind of questions. So just know or just understand how to derive a string. I think that you already know it, right? Okay, now let's look at this example. What is the grammar generated by the following context sensitive language? Okay, before going ahead, one more thing. In context sensitive grammars, I told you that the right hand side and left hand side can be anything but not epsilon. Therefore, by definition, context sensitive grammars does not generate any epsilon. Therefore, context sensitive languages does not contain epsilon. But then in the diagram, I told you that context sensitive languages are actually superset of pushed on these context free languages. There also the assumption is epsilon is not included. Okay, now watch this. This is the grammar given. They are asking you what is the language generated by this grammar. First of all, if they have given you the language and then if they have asked you to come up with the grammar, it would be really difficult. One good thing is they are already giving you the grammar and then they are asking you what is the language accepted, because it is easier to do that way. Okay, and don't worry, in GATE they will not ask you this. And so how to do it is, just try to derive a string, then you will understand what is the language generated by this. Actually the language generated by this is a power n, b power n, c power n, such that n is greater than or equal to 1. A power n, b power n, c power n, n is greater than or equal to 1. To see this, let's see an example with that. So I have just written down the derivation. So what I did is, initially I started out with this production, and then I started expanding like this step by step. But then anyway, let's see this derivation and I'll explain you how the grammar works. So first thing is, I derived ABC. Either you could derive ABC directly, or you could use small a, capital A, BC. If you have used ABC, your derivation will end there, which means you are going to generate a power 1, b power 1, c power 1, which is in the language. So that is the smallest string. In case if you are using this, it means that you want to derive a bigger string compared to this. And why is it bigger? The reason is our grammar is non-contracting. So you are always going to expand the string length. So whenever you are using this, definitely we assume that if you go and replace capital A with something, either the string length is going to be 4 or it is going to be greater than or equal to 4. It will never shrink. So definitely I am going to increase the string length by using this. So I have taken this. Then how A is working is, A will start at the left end, which means after small a's, and then it will travel to the right end, which means it will travel till it hits the C, and there it will generate one extra BC and convert it into capital B. Okay, it is very difficult to understand, just try to understand it. What capital A will do is, A will start at the left end after S, and then it will just travel to the right end till C's are hit, and whenever it sees the first C, it will generate one extra BC, and again it will start traveling to the left side as capital B. So see this, A has started here and now A will shift there, A will move here, and whenever it has hit small c, it will generate one extra BC and convert itself to B. That is what A is doing. So see this, now this move, this production is going to help capital A to traverse over the B's. So it will be at the, see, if there are all A's here and capital A will be here and all B's will be here and C's will be here, then this production will effectively help A to cross over the B's. That is what that production will do. Got it? So see this, A, again let's see here, see, A is starting at the leftmost and it will gradually move until it hits the C. See, A will be moving here and then A will be moving here, A will be moving here, and now once it has hit the C, it is going to generate one extra BC and convert itself to capital B. That is what this one is doing. So this production is going to help A to traverse over B, and this production is whenever A has hit C, which means it has seen C, then it is going to produce one extra BC. C is going to remain there, one extra BC is produced, and A is getting converted to B. Got it? And what is the purpose of B is, B will start from this end, right end, and it will keep on moving left, and whenever it hits A, it is going to generate one extra A. So effectively A is going to generate BCs and capital B is going to generate one extra A. So BC will be generated by A and B will be generated by A. For example, you start with A, B, C. Now B will go to the right end and here it will generate BC, which means A, B, B, C, and now again B will start here, it will come to the left end, it will generate A. So balancing out. A's responsibility is to go to the right end and generate a BC, and B's responsibility is to come to the left end and generate a so that everything will be balanced out. 1 BC, 1 A, 1 BC, 1 A, 1 BC, 1 A, like that. Okay. Now just see this. What B is trying to do is, B will start at this point and it will move left, move left, move left. For moving left, it is going to use this production. If BB is there, it is going to write it as capital B small b, which is nothing but moving left. And once it has moved left, it is going to hit this end and is going to generate one extra A. So B is going to generate one extra A, or in case if you want one extra ABC, then you go with this. If you don't want to stop this procedure, already one extra A is generated, along with that you generate capital A also. Now what will capital A do? It will go to the right end and generate BC. Now let's see the entire procedure. Now A will come to the right end and it will generate a BC. BC is generated. Now B will go to the left end and it will generate a A. Now A will go to the right end here, and it will generate a BC. Now B will go to the left end here, and it will generate a A. Like that it will work. So A and B are actually messengers. A will go to the right end, B will go to the left end, right and left end. Like that it is going to work. It is very complex to understand, so I hope that you understood it. But then in exam they are not going to ask you to design such a grammar. It is going to take a lot of time, a lot of time. Maybe you could just try how difficult it is, just to see how difficult it is. Maybe you could just try deriving a grammar for A power n, B power n, C power n. So what should you be doing? Generate AB. See, I'll just tell you the hint. I'll just give you the hint. I'm not going to do it. In case if I have time at the end, I'll do it. But then I'm just giving you the hint. Just see how to generate it. If I have A power n, B power n, C power n, D power n, now you have to go till this point and generate CD, and go till this point and generate AB. Go till this point, generate CD, go till this point and generate AB. It has to continuously happen. Okay. It is going to be difficult. Let me warn you, it is going to be difficult, but it will be fun to try it out. You please try it out. Okay. Fine. Now let's say we have the language A power n, B power m, C power n, D power m, such that n comma m greater than or equal to 1. For this language I want to construct a context sensitive grammar. So first of all, it is not going to be asked in GATE. Okay, don't worry about it. So don't worry about context sensitive languages at all. I don't think that they will ask you in the GATE, but then it is to be in the safer side, I am just teaching you. So it is not very difficult, as it is difficult to design it, but then not too difficult. Once I explain it, it will be very easy. So don't get worried about it. So let's just see how to design it. A power n, B power m, C power n, D power m, such that n comma m greater than or equal to 1. Definitely this language is not context free. The reason is, if you try to design a push down automata, if you push A and push B, and if you want to compare C against A's, by that time on the top of the stack there will be B's. They will not let you compare C and A's, right? Therefore it is not possible for you to construct a push down automata for this language. That we already know, it is not possible. Then the other alternative, if push down automata is not possible, then the next level is context sensitive languages. Now we have already seen for this language A power n, b power n, c power n such that n is greater than or equal to 1. For this language we have seen the context sensitive grammar. How does this context sensitive grammar, how did it work is, it started here and it slowly moved right, A slowly moved right and generated a BC, and again B slowly moved left and generated A. Like that we use two messengers. A is moving right and generated BC, and B is moving left and generated A. Similarly, we can use the same ideas and we can do this question. Okay. So this is entirely the one grammar only. Even though I have written some lines like this, it is completely the grammar. See how big it is. So don't worry about it. It can be done easily only. But then the lines, I have drawn these lines like this so that I want to separate the phases. I want to show you, or I want to explain you what this collectively these productions are trying to do, so that explanation will be easy. So I want to generate a power n, b power m, c power n, d power m. Now these four productions, they are not two, there are four productions. All these four productions combinedly, they want to give the effect, or they want to produce this. They want to produce a power n capital B, c power n capital D. So this is what they wanted to produce. So just see this. If you just want to produce 1A, 1C and BD, you can take this. Otherwise, if you want to produce any number of A's and C's, A power n, C power n, then you can take this production, and then in place of A, you can keep on using this, so that A power n, B power n will be generated. And if you want to stop it, you stop it with this. Therefore, if you want anything greater than 1, n is greater than 1, then you can use this production followed by these two productions. Anyway, by using all these four productions, finally what could you derive is a power n capital B, c power n, d power n, just like that context free grammar. Okay, if you want to see this, just see this how it is going to happen. If you want to generate directly A, B, C, D, done. If you want to generate A square, B, C square, D, then what you could do is A, C, D, and now in place of this A, you could put A, C, C, D. Now it is nothing but, B, in place of this A, you could put this, then it is nothing but A square, A square capital B, C square capital D. Therefore, using those four productions, what you could generate is A power n capital B, C power n capital D. Now what is the purpose of this B is, B has to go to the right and generate a D, and then get changed to some other messenger, let us say E, and now E has to come left and generate a B. Okay, so B has to go to the right and generate a D, and it will convert itself to some other variable, and that variable has to come left and generate a B. So we are going to use D as the end marker, which means B will keep on, capital B will keep on moving right until it meets the end, and when it meets the end, it is going to drop a D there, and again it has to come back and drop a B here, because both B's and D's have to be matched. So the same way how we designed A power n, B power n, C power n, here also we are going to do the same kind of traveling and then creating, traveling and creating. So what is that we are going to create here? B has to travel right and then create a D, and then convert itself to some other variable, and again we have to come left and then create a B. Okay, so for that reason what we are going to use is, if B has to travel right, see these productions, see this production, if B has to travel right, it has to move over C's and B's. Why is it required is, at some point in the derivation you might get a string like this, AA and then BB and then CC and then DD you have, and you will have D here and you will have B here in some point of derivation. Okay, then what should B do is, B should jump over all the B's, capital B, and then it should jump over all the D's, all the C's, and then finally it should meet the D. Okay, so these two productions will help B in traversing or jumping over C's and jumping over D, isn't it? See this, it is nothing but b is jumping this side, that is why b has come here. B is jumping this side, that is why b has come here. Therefore what is happening, b will jump all the b's and then b will be here, and b will jump all the c's, and finally b will meet d. Then what should it have, what should it do? Whenever it meets d, it is supposed to generate one extra d. Okay, it will generate one extra d, and then if it generates one extra d here, it has to again go there and generate one extra b. Therefore it is going to convert itself to e. So see this, what is happening is, whenever b meets d, which means b has reached the end of c's, therefore that is the point where it could generate a d. Then it could generate one extra d and then convert itself into e. Why? Because once it converts itself into e, then e can come to the left and generate a b. It is not just enough that you generate the d there, you have to even generate b's. Why? B's and d's have to be matched. That is why what happens is, a will keep on, b will keep on going here and it will go there, and finally it will generate a d, one extra d, and it will become e. Now what should e do? E should keep on coming left, and once it meets a, it should generate one extra b. Then only d's and b's will be matched. Then what it should do is, e is supposed to jump over c's and b's. Therefore look at this, this move will help e in jumping over c. So it is going to jump like this, that is why e is here, right? E is coming, and again it is going to jump here, that is why e is here. Therefore e is going to jump over all the c's and all the b's, and finally e will go and meet the first a. Whenever it has reached the first a, it will understand that that is the point at which it has to generate a b. Therefore whenever it has reached the first a, then it is going to convert into b and end the procedure, which means it can stop here and convert into a b. But the problem is, using this, if I kill b here, if I kill d here and if I kill e here, the procedure is going to end. But sometimes, see, you can generate any number of a's and any number of c's using the first four productions, that is fine. But then if I use only till there, that point, we are generating only one d and one b, isn't it? Only this will be generated. If you want to continue this procedure and generate many number of b's and d's, our d should not die here and our e should not die here, and the procedure should be alive. That is why what you could do is, initially when the b has met d, it need not kill d. Let the d be there, generate one extra small d, this nd limited d be there, and generate one extra small d, and now you convert yourself into f. Now what is the purpose of f? Go to the left and generate one extra a, but then again reproduce b, so that this entire procedure will be alive, isn't it? That is why f will jump all the c's and f will jump all the e's, and whenever it meets a, it will generate one extra b, and it will even reproduce capital B, so that capital B will again go and meet d and produce a d, and again b will meet a and b will convert itself to f and come back and meet small a and produce a b. So this entire method is used in order to generate any number of b's and d's. So initially these four productions are going to generate equal number of a's and c's, and then this procedure is going to generate any number of b's and d's. In case if you want only one b and d, you go with this, or in case if you want to kill this procedure at any point, you can go with this. Got it? That is how context sensitive grammar can be generated for this. It is not asked in GATE. Maybe if they want to ask something about it, they will just give you a blank and they will ask you to fill it up. It is not very easy to understand or answer it, but let's be in the safer side. Since you have already learnt it, better you just write it down, and before the exam you could revise it once. Okay, this is about the context sensitive grammar. This is a very important theorem. I'll just read out the theorem, and maybe you please write it down, and if possible by heart it. Anyway, I'm going to give you the proof, but just you can write it down. See this: if a language L and its complement L complement are both recursively enumerable, then both languages are recursive. I don't think that you'll understand anything now. I'm just reading it out so that you'll write it down, then I'll talk about it. And next one is, if L is recursive, then L complement is also recursive, and consequently both are recursively enumerable. Okay, so what to understand from this given explanation is, So before you understand anything, let me talk about the difference between recursively enumerable and recursive languages. According to the definition of recursively enumerable, I said that if for a language there is a Turing machine exists, then it is recursively enumerable. And when I was talking about recursive languages, I told that if for a language, if a Turing machine exists which always halts, then that language is recursive. So the main difference between recursively enumerable and recursive languages, the Turing machine for recursive languages always halts, and the Turing machine for a non-recursive, recursively enumerable language may or may not halt. So see this, the main difference is if a language is recursively enumerable, then it will have Turing machine, right? And now to this Turing machine, if I give a string w, then it might halt and say yes, the language is the string is in the language, in case if the string really belongs to the language, okay? Or it may say no, or it may fall in infinite loop. This is the problem. So recursively enumerable languages have the problem that given a string, the Turing machine may say yes, will definitely say yes if the string belongs to the language, and what it will do is it will say no, or sometimes it will fall in infinite loop if the string does not belong to the language. And what is the recursive language is? Recursive language means it will have a Turing machine, and given a string to the Turing machine, it will say yes, this string is present, or no, this string is not present in the language. In case here string does not belongs to the language, then it will say no or infinity, and here if the string belongs to the language, it will say yes, and if the string does not belong to the language, it will say no, straightforward, right? And you need not wait. The problem here is you don't know how long to wait. It might be the case that the Turing machine really needs extra time to compute, and it is really doing some computation, and therefore you might have to wait in that case. Or it might be the case that it has entered an infinite loop and there is no way you know that you are in the infinite loop. Let us say you are watching a Turing machine, you are sitting and watching a Turing machine, it is doing some computation. Now you don't know whether to switch it off or not, because it is still computing, it is not saying anything. It might be the case that it needs more time really, or it might be the case that it might have entered the infinite loop. Therefore we cannot say anything about that. So the main difference between recursively enumerable languages and recursive languages, Turing machine may fall in infinite loop in case of recursive enumerable languages sometimes whenever this given string does not belong to the language. And in case of recursive languages, the Turing machine does not fall in infinite loop. Whatever it is, it will give you a straightforward answer. Therefore you could wait until it halts. Here the Turing machine always halts, here the Turing machine does not halt, okay? Now, so what is the main difference is there is something called as membership algorithm. Membership algorithm is given a string and a language, our question is whether this string belongs to the language. Tell me yes or no. If you can answer that using an algorithm, then that is called membership algorithm. Here membership algorithm is not possible. The reason is if you give it a string and ask it whether it is present in the language or not, it may sometimes say yes and it might never say an answer. Therefore you are not going to get a no all the time, right? Therefore there is no membership algorithm for recursively enumerable languages. Write it somewhere. There is no membership algorithm for recursively enumerable languages. But coming to recursive languages, given a string and you ask it the question that whether this string belongs to the language or not, that is called membership question. And for that question, definitely it will answer with yes or no. Why? Because Turing machine is always going to halt. Therefore, for recursive languages, membership algorithm exists. Membership algorithm exists. This is the main difference. Understand this? For recursively enumerable languages, no membership algorithm exists, but for recursive languages, membership algorithm exists, right? So given a Turing machine, right, that may or may not halt, and if we just say that the language is having a Turing machine and we didn't say anything about whether it halts or not, then it is nothing but a recursively enumerable language. If I say that the language is having a Turing machine which always halts, then it is nothing but recursive language. Therefore, since the Turing machine always halts, we can say that there is a membership algorithm for recursive languages and there is no membership algorithm for recursively enumerable languages. That is the main difference between these two, recursive languages and recursively enumerable languages. Okay. Now, after understanding this difference, now let's go to the theorem and see how to prove this. Now they are saying that if a language and its complement both are recursively enumerable, then the language is recursive. So what does that mean? Assume that this is sigma star. Sigma star means set of all strings possible. Okay, let me write it here. Assume that this is sigma star. Sigma star means set of all strings possible, and let us say this is L. L is nothing but a language which is nothing but a subset of the set of all strings. Okay, and now they are saying that if a language L and its complement both are recursively enumerable. So what does that mean? Both for L as well as L complement there are Turing machines which will say definitely yes for the strings which are present in the language, and if a string is not present in the language they will be helpless. They might say no or they might fall in infinite loop. So understand this. Now if this is L, see this is set of all strings possible, and out of which this is L which is nothing but the language, and this is L complement. L complement is nothing but sigma star minus L, therefore this is L complement. Now they are saying that a language L and its complement both are recursively enumerable. That is what they said. So the language L and its complement both are recursively enumerable. Then what happens is we can design a Turing, it implies that actually there are two Turing machines, Turing machine 1 TM1 and Turing machine TM2. One is for language L and other is for language L complement, in such a way that if I give any string which is present in the language L to Turing machine 1, it will say yes, the string is present. That is the meaning of this. So whenever we say that there is a Turing machine for a language, what does it mean? It means that given any string in the language to the Turing machine, it will definitely say yes. But if you give it any string which is not in the language, we don't know. Maybe it will say no sometimes if you are lucky, otherwise it will fall in infinite loop, right? So to this, since L is given as a recursively enumerable language, I am assuming that there is a Turing machine TM1 in such a way that if I give any string to this TM1 which is present in L, it is going to say yes, the language is yes, the string is present in the language. But then the problem is if I give it any string which is not present in the language, it might say no or it might fall in infinite loop, but I don't care about it now. Okay, and now L complement is also a recursively enumerable language. Therefore definitely there must be a Turing machine TM2, some Turing machine, to which if I give a language from L complement, which means which is not in L, it should definitely halt and say yes, the string is present inside the L complement, right? Now using these two Turing machines, what I will do is I will build a new Turing machine. What that new Turing machine will do is, now you give me any string in the entire sigma star, either it could be present in L or it could be present in L complement. You just give me one string, then I'll distribute it to both of them, then at least one of them is going to halt and say yes, isn't it? Therefore I got a new Turing machine TM3 by using a combination of these two Turing machines in such a way that you give me any string anywhere from sigma star, then I'll give it to them both the Turing machines simultaneously, and both of them will start working. And since the string is going to be present in either L or L complement, because you cannot give it outside that, one of the Turing machine will definitely halt and say yes, which means wherever the string is, right? So if this one says halts and says yes, then I am going to say that yes, this string is present in L. If this one is going to halt and say yes, even though it is saying yes here, I'll just interpret it as no, right? Therefore, if a string is present inside the language, I'm going to say that yes, it is present inside the language. If the string is not present inside the language, I'm going to say that no, it is not present inside the language, using the help of these two Turing machines. Therefore, I got a new Turing machine which always halts. So whenever I get a reply from any one of them, I'm going to stop the main Turing machine. I'm going to stop both of them. So we are never going to follow infinite loop. So now I got a Turing machine which always halts whatever the string is, wherever the string is. Therefore, the language L is recursive. So try to understand it. I don't know if you understood it or not. See, if the language L and its complement both are recursively enumerable, what does that mean? Both are having Turing machines independently, and those Turing machines are going to halt on any input given to them, if the input is in the language, isn't it? Therefore, I assume that TM1 is the Turing machine corresponding to the language L, and TM2 is the Turing machine corresponding to language L complement. And by the definition, these Turing machines are supposed to halt if we give them any string which is present in the language. Therefore, TM1 is going to halt for every string which is present in L, and TM2 is going to halt for every string which is present in L complement, and they are going to say yes, isn't it? Now I'll combine these two Turing machines into a new Turing machine in such a way that you give me any string, I'm going to distribute it to both the Turing machines, both of them simultaneously. Then at least one of the Turing machines is going to say yes. So whenever at least one of them is going to say yes, you can stop both of them, which means we are not going to follow an infinite loop. If the TM1 says yes, then the output will be yes. If TM2 says yes, then output will be no. It is a simple complementation, isn't it? Therefore, I got a new Turing machine which is going to halt for all the strings inside sigma star, and which is going to say yes, a string is present in L, or no, the string is not present in L, which is nothing but we even got the membership algorithm. A halting Turing machine is also a membership algorithm, isn't it? So this statement is right. If the language L and its complement both are recursively enumerable, then both the languages are recursive. So both L as well as L complement both are recursive. Now I have shown you that this is a Turing machine which halts for language L. Now if you just reverse the results, this one no and this one is yes, then you can say that this is the Turing machine for the language L complement. So both are recursive. And next point is, if L is recursive, then L complement is also recursive. That is the next statement. They are just independent. I hope that you understood this. Let me explain you the next statement. If L is recursive, then L complement is also recursive, and consequently both are recursively enumerable. So it is very easy to prove. They are saying that a language L is recursive, which means, let us say this is sigma star, and a language L is as always a subset of sigma star, and now they are saying that language L is recursive, which means for the language L there is a Turing machine which always halts. So what does it mean? Give it any string which is present inside the language L, it will say yes. Give it any string which is not present inside the language, it will say no. Already it is there, right? Then if language L is recursive, this is already there, this Turing machine is already there, then L complement is also recursive. They are saying that the complement of the language is also recursive. So what does that mean? How can you prove that? Now for the complement of the language, you should get a Turing machine which should say yes if the string is present in that, which should say no if the string is not present in that. Then what I do is, I'll construct a new Turing machine, let us say TM new. Now this new Turing machine will act exactly the opposite way, which means whenever the original Turing machine said yes, you will say no, and whenever the original Turing machine said no, you will say yes. Now what happened because of this? So if the string is present inside the language L, then you are going to say no. If the string is not present inside the language L, then you are going to say yes. Anyway, you are going to halt on both the cases, and therefore this is the Turing machine which always halts for the language L complement. So we got a halting Turing machine for L complement also. Therefore L complement is also recursive, and consequently both are recursively enumerable. Why? Because recursively enumerable just wants a Turing machine. It doesn't care whether it halts or not. and now we have shown that both of them are having Turing machines, therefore consequently both of them are recursively enumerable, isn't it? This theorem is very important, and proof is pretty simple. I don't know whether you understood it or not. If you didn't understand it, you please rewind the video and watch it 4-5 times. You are supposed to understand it. It is very straightforward. Okay, and now let me talk about this membership algorithm. So membership algorithm is nothing but, given a string, your machine should stop and say yes or no. You should not fall in infinite loop. For regular languages, your finite automata, give you a finite automata a string, it is always going to halt and say yes. Finite automata will never fall in infinite loop, isn't it? The reason is, finite automata moves in only one direction, and by the time the entire string is scanned, it will definitely halt. It is not supposed to move left. Similarly, pushdown automata will also move in one direction, therefore it will definitely halt. So membership algorithm exists for finite automata, which means regular languages, and for context free languages, which means pushdown automata, and for context sensitive languages and for recursive languages. Only language which does not have membership algorithm is recursively enumerable language. The reason is, the Turing machine may fall in a infinite loop. So keep that in mind. So membership algorithm is nothing but, given a string W, whether the string belongs to the language. This is nothing but membership algorithm. Now all the languages will have membership algorithm except only one language, which is recursively enumerable language. Got it? Okay. We have seen various types of grammars, various types of machines, and various types of languages. Now collectively on these languages, there are some few questions we could ask, like, how these I'm saying that there is a let me draw the diagram, then you'll understand it better. I told you that there is one language which is enclosing everything, that is recursively enumerable language, which is nothing but set of all languages. This is nothing but set of all languages which are acceptable by or accepted by Turing machines. And now inside this, the set of all languages which are accepted by halting Turing machines is there, which is recursive language. And inside that, set of all languages which are accepted by linear bounded automata, which are called context sensitive languages. And inside that, set of all languages accepted by pushdown automata, which are called as context free languages. And inside that, set of all languages accepted by finite automata, which are called as regular languages. So we have all these classes of languages. Now the one interesting question which you could ask is this regular languages really a subset of context free languages? Which means, is there at least one language which is not regular, which is context free? If there is at least one language which is not regular, which is context free, then you can say that regular language is a proper subset of context free language. And for that, yes, we can say answer is yes. The language is a power n, b power n. A power n, b power n, n is greater than or equal to 1 or 0 is a language which is not regular but which is context free. Similarly, you could ask one more question saying that, is context free languages, set of all context free languages, a proper subset of context sensitive languages? Which means all the strings accepted, all the languages, is there any at least one language which is accepted by context sensitive or which is accepted by linear bounded automata, which is not accepted by a pushdown automata? And you can find out that yes, there is one language which is a power n, b power n, c power n. And now naturally, to extend this question, you might ask, is there any language which is recursive and which is not context sensitive language? That is a difficult question to answer. In this sense, now I have given you some examples like this just to prove that yes, it is a proper subset. But then if you have to prove that there is a language which is recursive but not context sensitive, I cannot give you any such language like this, which means I cannot say a power n, b power n, c power n or a power p such that p is a prime. Such kind of proof or language is not available for us. So in order to prove that, there are mathematical theorems which are used in order to say that, in order to prove that there is at least one language which is recursive but which is not context sensitive. So we don't have any language, or if you ask me to give us an example, I don't have any example, not anyone has. So proving it is a other case, which means they have used mathematical theorems to prove that there will be one language, at least one language, which is not context sensitive and which is recursive. That is what we could say. But then precisely writing that formal language is difficult. We can say that there exists at least one language and we can prove that, but then we cannot say what that language is because we don't have that. Okay, I mean, so, and again the same question is true here also. So if you ask me, is there at least one language which is recursively enumerable, which is not recursive? Answer is yes, there is at least one language, but then I cannot give you in this form a power n, b power n, c power n. So using the mathematical theorems we can prove that these are all proper subsets of each other, which means this one is proper subset of this, this one is proper subset of this, but then we cannot say exactly what what that language is. And now next extension is, you might ask, next question you might be asked, you might have doubt is, yes, Turing machine is the most powerful machine in all the machines like finite automata, push-down automata, linear bounded automata. If you take all the machines, we know that Turing machine is the most powerful machine. Now the natural question is, how powerful is this Turing machine? So you might ask whether Turing machine is capable of accepting every possible language, which means if there are some languages, let us say set of all languages, I'll take all the languages which are possible. Now the interesting question to ask is Turing machine capable of accepting all these languages, which means for every language will there be a Turing machine? That is the interesting question. So in order to answer it, we are going to use the set theory. Okay, so the question is, I want to answer this question. For every language is there a Turing machine accepting it? It is a difficult question to answer. So for every language, do we have a Turing machine to accept it? Is a difficult question to answer it directly, but then we are going to use indirect proof to prove it. So I'll just give you a overview about what I am trying to do, and then I'll tell you in detail how to do it. Okay, giving you an overview will help you in understanding the concept better before getting into the actual concept. In order to answer it, what I'll try to do is, I'll show that the set of all Turing machines are infinite. The set of all Turing machines are infinite, and I'll show that the set of all languages are also infinite. This is set of all Turing machines and this is set of all languages, and then I'll show that, I'll try to prove that the number of Turing machines available, even though infinite, are lesser compared to the number of languages available. Both are infinite only, but then I'll prove that this is a bigger infinity and this is a smaller infinity. By showing that, we can understand that for every language, if you give one Turing machine, then we'll quickly run out of the Turing machines, and then there will be some languages remaining for which there will be no possible Turing machine. Remember, every machine can accept only one language. Therefore, if I have, let us say, 10 machines, I can accept only 10 languages. Similarly, if I have these many machines, I can accept only these many languages. Now it just indicates that there are some languages remaining for which we will never be able to give a Turing machine. Therefore, using this we can prove that Turing machine is not so powerful that it can accept everything. Therefore, there are some languages which are not even recursively enumerable. Recursively enumerable means they are not accepted by Turing machine. So even the most powerful machine, Turing machine, is not capable of accepting every language. So using this proof, using this argument, we can prove that. But then I cannot find out a language which is not accepted by Turing machine. That is not what I mean to say. What I mean to say is, I'll use some methods or theorems using which I'll prove this. Now in order to prove this, I'll talk about countable sets, uncountable sets, finite sets, infinite sets. Then I'll just build some mathematical theory gradually, one by one, step by step, and you please keep noting them down, and later slowly I'll prove this method. Okay. Now look at this. Sets are of two types. Sets means you know that already. Set is nothing but a collection of objects. I'm not going to define it. And sets is of two types. Again, we have something called as set theory, group theory. There I am going to discuss about sets in mathematics. But now I'll just discuss the part which I need in order to explain about the Turing machines. I am not going to discuss everything. Okay. Later we shall see it again. Now sets are of two types. One is finite and other is infinite. Finite sets means if all, you know that, okay, I'm not going to define. Finite means if there are countable number of elements like 10 elements, 20 elements or whatever. For example, if I have a power n such that n is less than or equal to 10 power 10 power 10, even though there are many elements, it is still finite, okay. So you know what a finite is. I'm not going to define it. And now infinite means there is no upper bound. For example, a power n is greater than or equal to 1. If I have anything like this, a power n such that n is greater than or equal to 1, there is no upper limit, that is called infinite. Now coming to infinite, there are two types of infinite sets. One is countable infinite and other is uncountable infinite. So countable infinite is actually smaller infinite compared to infinite means there are lots of strings or lots of elements, and again in these lot of elements we can say that it is not too many and it is too many, which means if I say that a set is countable infinite, it means it is infinite but it is not too much. And if I say it is uncountable infinite, it is infinite and it is too much. If you try to compare a countable infinite set and uncountable infinite set, we'll see that we'll take it that countable infinite set is lesser compared to uncountable. So it is not right in writing like this, but then still this is the actual meaning. So you should not write it directly, but I'm going to write it. It is the actual meaning, but don't write it anywhere. What I mean to say is finite set is less than, countable set is less than uncountable set. It is not given anywhere, but actually that is the meaning that I want you to understand. So finite set is less than, countable sets is less than uncountable sets. And now my main intention in talking about this entire theory is simple. I want to prove that set of all Turing machines are countable and set of all languages are uncountable. Therefore number of Turing machines are less than number of languages. Therefore there are some languages which are not accepted by any Turing machine. So there are some languages which are not recursively enumerable. That is what I want to prove by the end. Okay. Now before going ahead, given any set, how will you distinguish whether it is finite or infinite? That is very easy, straightforward. Now once you found out that talking about finite sets is not very interesting because no one is interested in talking about it, but then talking about infinite sets is actually the most interesting thing. Now when we talk about infinite sets, we have to make distinction between two types. One is countable and uncountable. Given any set which is infinite, how can you say that it is countable, or how can you say that it is uncountable? That is the most important question. Now watch this. Countable set means a set capital S, any given set, is said to be countable if all the elements of the set can be put in one-to-one correspondence with the set of natural numbers. What do I mean by saying this is, if a set is given and if you take every element of the set and if you can give one element from the natural numbers to this one, and if you can arrange them all like that, then it is called as countable set. And what is uncountable set is a set, obviously if a set is infinite and if it is not countable, definitely it is uncountable, isn't it? So instead of saying it entirely, which means if we cannot put in one-to-one correspondence with the set of natural numbers, what you could directly say is a set is said to be uncountable if it is infinite and if it is not countable. You can directly say that even. Okay. So I'll just take an example and I'll show you what I mean by giving one-to-one correspondence from the set, from all the elements of a set to all the elements of a natural numbers. See this, the definition says that a set is said to be countable if all the elements of the set can be put in one-to-one correspondence with the set of all natural numbers. It is, you might think that it is very simple definition, but then in order to actually apply this, it takes a lot of experience and practice. So I'll discuss about some of the examples using which you can answer any question in GATE coming to this topic, countability. Okay, so watch it once. Let us say, let us start with a small example, set of all even numbers. Let us assume that set of all even numbers is written like this: 0, 2, 4, 6, 8, 10, 12, so on. They are all set of all even numbers. Okay, and now I'll take set of all natural numbers. Set of all natural numbers are 1, 2, 3, 4, 5, 6, 7, so on. Fine. Now there should be one-to-one correspondence between every number here to every number here. If I can give that one-to-one correspondence, which means for every element in the set E, if you can give a element in the set N natural numbers, then I can say that set of all even numbers is countable. Okay, so how can I do that? We already did it, isn't it? So now for 0, the element given in natural numbers is 1. For 2, the element given is 2. For 4, the element given is 3. For 6, element given is 4. Right? Now how did we do that? So what is the procedure? So given any element, will there be a natural number? That is the question. So let us say the element given is 2i. So what is the natural number corresponding to this? I think for 2i, natural number corresponding to this is I plus 1, isn't it? Check that. For example, 2i, 2 into 1, 1 plus 1, 2 into 2, 2 plus 1, 2 into 3, 3 plus 1. Therefore, for any element of form 2i, we can give an element of form I plus 1. Right? So what can you understand from this? We can understand that for every element in the natural even numbers, we can give a element from the natural numbers as a correspondence. Therefore, we can say that this even numbers is countable since we are able to give it. So it is very straightforward for this example, but then it is not so easy to prove that some other languages or some other sets are actually countable. So let's just extend some of the I'll just explain you some of the terminologies used here. One is called index. Now element 0 is given element 1. Therefore, I call this number as the index given to this number as the index given to this. Therefore, every element is going to get an index, and that index is nothing but a number from the natural number set. So one other way of saying it is, if every element in the given set is going to have an index, then that index is nothing but the number to which it can be mapped to in the natural numbers. Therefore, you can say that such a number is such a set is countable, right? And this is how you can say that the set is countable, and every element is also going to have an index. So the element 2i has an index of I plus 1, isn't it? So if we can get the indices, then we can say that if every element is having an index, then we can say that the set is countable. One definition is, if you can put them in one-to-one correspondence with natural numbers, it is countable. Or for every element, if there is an index, which means the position at which it can be placed in the set, if you can say that, then also it is countable. Now let's see one more example. Let us say set of all odd numbers: 1, 3, 5, 7, 9, 11, so on. Now, can these elements be put in one-to-one correspondence with natural numbers? Check this. We can put them like this, isn't it? Therefore, for every element in this odd number set, there should be an element in the even number, in the natural number set. For the element 2i plus 1, what do you think is the corresponding index? So for the element 2i plus 1, for example, for the element 5, the corresponding element is 3. So how can you get this one? It is nothing but same as I plus 1. So for every element of the set of odd numbers of type 2i plus 1, the corresponding index we have is I plus 1, isn't it? Therefore, what can we say? Since we are having for every element one element in the natural number, there is a one-to-one correspondence between the elements. Therefore, the set of all even numbers is countable and the set of all odd numbers is countable. Okay. And now let's see one more example. The set of all real numbers. Real numbers means you can take any number, 0.1, 0.2, 0.3, anything, isn't it? Now if you take set of all real numbers, the problem is just between 0 and 1 there can be so many numbers that they can all eat up the natural numbers available. Whatever natural numbers are there, I can generate so many numbers between these two that they can eat up all of them. Or you can come up with any method in which you will try to assign a number to that, but then it will all fail. Therefore the set of all real numbers, see the proving that set of all real numbers is this way: between 0 and 1 we have so many numbers that they are capable of eating up all the numbers. Okay, so later I'll prove it in a concrete manner using some method called as diagonalization, but for now understand that we just is an informal proof, just to understand for your understanding sake. It is informal proof. Later I am going to give you a formal proof. What I mean to say is, only between 0 and 1 we have lots of numbers that all these numbers have the capacity to eat up all the numbers of natural numbers. So only between these two, if we eat up all the natural numbers, what about the remaining numbers on the number line scale? Real numbers means everything, isn't it? Therefore we cannot actually give one-to-one correspondence between real numbers and natural numbers. Therefore set of all real numbers is uncountable. Remember this, I'll give you the proof later. So the proof for even numbers is countable and odd numbers is countable is, for every element I have given you an index. For every element 2i, the index is I plus 1. For every element 2i plus 1, the index is I plus 1. Therefore if you are able to give an index, that is nothing but a correspondence in the natural number. That is how I am able to prove that they are countable. But then for these real numbers I will not be able to come up with any index. Now I'll just use some other proof. This one-to-one correspondence is okay, you can prove it this way, but then it is difficult to prove it for all the sets that they are countable. We shall use some other better methods to prove that a set is countable. Okay, I'll tell you what they are now. Using the previous definition for countable sets, like putting one-to-one correspondence from all the elements of a set to natural numbers, it is very confusing, which means for some sets it might look as if we can easily put them in one-to-one correspondence, and for some sets it might look as if we cannot put them in one-to-one correspondence, and in both the cases you might go wrong. So by using the definition which is given in textbooks, some of the textbooks, that previous definition, it is very difficult to say whether a language is countable or not, whether a set is countable or not. Therefore I have framed this new definition, and using this you will be able to understand this concept very easily, and you will be able to answer any gate question, and you will be able to prove the rest of the things very easily. So I framed this definition. You please read it and make a note of it, and it is right, and anything that you want to prove as countable can be kept in this form. Okay, I'll read it out and I'll explain you this, and then I'll take examples. The previous examples which we have seen, the set of all even numbers, odd numbers, we shall again examine them in the light of this definition, and then we shall see how we could use this one in order to prove that set of all Turing machines are countable, which means set of all Turing machines are infinite but less, and then we shall prove set of all languages are uncountable later. Okay, so just watch it once. A set is said to be countable. A set is said to be countable if there exists an enumeration method using which all the elements of the set can be generated for any particular element. Okay, let's go step by step. A set is said to be countable if there exists an enumeration method using which all the elements of the set can be generated. This means that if you are given a set, then you should be able to write a kind of algorithm or program, but then I am not saying that it is an algorithm because it need not stop. So you just give a method using which we should be able to generate all the elements of the set one by one. You give me a method, okay, using which all of them are going to be generated, and then for any particular element, which means given any element, if you follow your method, it takes only finite number of steps to generate it. If that is the case, which means try to understand it, I'll give you an infinite set. What you should do is you should come up with a method or a procedure or we should not call it an algorithm. Calling it as a method or procedure is right, but then don't call it an algorithm because it need not stop. It could go on infinity, but then what is required is you should be able to write it down as a method. Now that method should be able to generate all the elements of the set one by one, one by one, one by one. And now given any particular element, I should be able to reach that element using your method in a finite number of steps. Now if you can give me such a method, then the language is said to be countable, then the set is said to be countable. Okay, so come up with a method, given a set, generate it, which means generate all the elements, enumerate. Enumerate means write it down. Every element, writing every element one after one is enumeration. And now enumeration method means we are writing a method which will write down all the elements one after the other. Now your method should write down all the elements one after the other. Then what I need is, I want this method so that all the elements have to be generated, so that all the elements can be generated in any particular way. And if any particular element is given, I should be able to reach it in finite number of steps. If such a method is given, then I can call that the set is countable. And the finite number of steps that are required, that are taken to generate an element, which means given an element you are able to generate it in finite number of steps, right? That finite number of steps which are actually taken in order to generate that element can be used as its index, which means you can call that number as the index. Now once you get the index, that is nothing but a mapping into the natural numbers, isn't it? Once we get an index, that is nothing but the mapping into the natural numbers, isn't it? So it is simple, very simple. So definition is very simple, and I'll just take the example and then I'll show you how to use this definition to prove that a set is countable. Now as an example, let's say set of all even numbers. Set of all even numbers. Now you come up with a procedure using which you will be able to generate all the even numbers, and then using your procedure, if I give you any element, you should be able to reach that element in a finite number of steps. If you can do these two things, then I can say that it is a countable, right? So how can I generate set of all even numbers? You can just write a for loop, isn't it? Maybe I can write like this: for I equal to 0 to infinity. It is not a algorithm because we are going to infinity. What is an algorithm? You should always stop in finite number of steps. But since I is going from 0 to infinity, we are never going to stop in finite number of steps, isn't it? For I equal to 0 to infinity, if I write like generate means just print 2i. So this is the enumeration method, right? So now if I write like this, what will this enumeration procedure do? It will try to generate all the numbers one after the other. Like first it will generate 0, then it will generate 2, then it will generate 4, then it will generate 6, then it will generate everything. Therefore we found out an enumeration method using which we will be able to generate all the elements. But then it is not just enough. Just finding out the enumeration method is not enough. What you should do next is, you should be able to generate a given number in a finite number of steps. For example, how many steps does it take to generate 0? 1 step. How many steps does it take to generate 2? 2 steps. How many steps does it take to generate 4? 3 steps. 6, 4, 8, 5 steps, so on. Therefore, every element can be generated after fixed number of steps. What is the implication of that? Now these number of steps can be used as the index for this particular element. Therefore, for every element I found a natural number, isn't it? That natural number is the index itself. Therefore I can say that the set of all even numbers are countable because there is a one-to-one mapping to the natural numbers. We found the one-to-one mapping without actually doing that original definition. See, you might feel that this method is long and it is difficult, but then later you'll understand that with other examples this is the easiest method rather than putting one-to-one correspondence to natural numbers. Okay, now let's see how to do this with the set of all odd numbers. Now we found out that set of all even numbers are countable. Now let's see what to do with the set of all odd numbers. Set of all odd numbers. It is simple. For I equal to 0 to infinity, you generate I plus 1. then 2i plus 1, then what will be generated? Initially 1 will be generated, and then 3 will be generated, 5, 7, 9, 11, so on, right? And what about the index? This will be generated in one step, this will be generated in 2 steps, 3 steps, 4 steps, 5 steps, so on, isn't it? So every element can be generated in these many steps. Therefore these are nothing but the indices for these elements, and since every element has got an index, and one more thing, for a particular index there will be two elements will not be there, which means two elements are not going to be mapped to one index. In one step we are generating only one element, therefore every element will get a different index, because at every step only one element is going to be generated. So this particular element can be used as the mapping into the natural numbers. So for every element of the set we got a mapping into the natural numbers. So we can say that set of all odd numbers is also countable. What about set of all real numbers then? Set of all real numbers, it is very difficult to come up with a enumeration method first. So you cannot generate all the real numbers using a enumeration method. Maybe you might try to generate it, but then later you will not be able to reach a particular element. Let us say you are trying to generate all the real numbers, but then if you start with 0.0, then 0.01, then 0.001, then 0.0001, this procedure itself will never stop, because if I start with 0.01 and then 0.1, 0.01, 0.001, this procedure itself will never stop, and it will go on, keep on going for infinity, and you will never reach a element starting with 1.0. Therefore, even though it is not an actual proof, we shall prove this later. I'll prove that the set of all real numbers are not countable later using some other method. But for now, just understand that giving a enumeration method and then generating an element in fixed number of steps for real numbers is impossible. Therefore, it is uncountable. Let's examine some other examples. Now let's examine one more interesting language. I want to see whether the set of all quotients of form p by q, the set of all quotients of form p by q, where p comma q are positive integers. So let us say p comma q are two numbers which are positive integers, and now we have set of all quotients of that form. Now what I would like to see is whether all these numbers of this form are countable or not. That is what I wanted to see. And in order to do this, let's observe how to do this. So if all the numbers are of form p by q, and if they are all in a set, is that set countable or not? So what we should come up with is, first of all, how will that set look like? Let us say that is set S. That set will look like this: 1 by 1, 1 by 2, 2 by 1, 1 by 3, 1 by 4, 3 by 4, so on. There will be lots of elements like that. Okay, and these are all the elements, and now we want to find out whether this set is countable or not. So how can we find out whether a set is countable or not? You try to find out a enumeration procedure or a method, meaningful way, in which you can generate all the elements of the set, and given any element, that should be reached in a finite number of steps, and that number is going to be the index into the real numbers, natural numbers. Therefore you can say that is natural. Now let's see what could be the enumeration method. Let us say I want to generate all the numbers in one order like this. I'll want to do it 1 by 1, 1 by 2, 1 by 3, 1 by 4, 1 by 5, 1 by 6, so on. Now what is the problem with this? It is enumeration method. It is able to generate all the numbers, or it is looking like as if it is going to generate all the numbers, but then it is not a enumeration method which we wanted. The reason is, if you go on enumerating the numbers like this, the number 2 by 1, that will never be generated. The reason is, there will be infinite number of numbers which will be having numerator as 1. 1 by 1, 1 by 2, 1 by 3, it will keep on going, and using this method you will never come across the number 2 by 1. Therefore, given this number 2 by 1, you will never be able to generate it in a finite number of steps. Why? We are going to go infinite times, and then sometime we will come across this, and we don't know when. We have infinite numbers. So we failed to find out a enumeration method. So failing to find out enumeration method, is that going to be the proof to say that it is not countable? No way. If you are not able to find an enumeration method, it doesn't mean that there does not exist some other enumeration method using which you could enumerate it. Okay, so it is not actually true to say that since we are not able to find a particular enumeration method, the number is not, the set is not countable. In order to say that set is not countable, you should do some other proof explicitly proving that the set is not countable. We cannot use such an argument, that is invalid. Now but then how can we prove that a set is countable? By finding out an enumeration method, we can say that the set is countable. But then without finding an enumeration method, we cannot say that the set is uncountable. For that the proof is different. Okay. Now let's try to see, is there any other way I could enumerate the strings? Therefore, I could enumerate the elements, therefore I could generate a particular element in a fixed number of steps. If I have 2 by 1, if I take this method 2 by 1, 2 by 2, not 2 by 1, let me say, other method is I want to increase the numerator, which means 1 by 1, 2 by 1, 3 by 1, 4 by 1. If I go on like this, again I get infinite number of numbers, isn't it? But all of them are going to have the denominator as 1, and you will never be able to reach the number 1 by 2. Therefore, even this enumeration is also not the valid one which we wanted. Then we want some other meaningful method using which we will be able to generate every particular string in a fixed number of steps. So maybe if you could think for some time, you could come across this, many ideas. I'm going to tell you one of them. You might come across some other ideas, but I'll tell you one of them. So one good idea is, don't go either in the increasing order of numerator or in the increasing order of denominator. What you do is just add numerator plus denominator and you go in the increasing order of the sum. So if numerator is p, denominator is q, you add p plus q and now go in the increasing order of p plus q's. For example, here in this case, what is the smallest number? 1 and 1. Therefore, the first sum is 2. So only number possible is 1 by 1. The sum is 2. And the next number possible is, next sum possible is 1 and 2. Therefore 3. So what are the various numbers possible which are having a sum of 3? Adding up numerator and denominator. One is 1 by 2 and other is 2 by 1. So go in the increasing order of sum of p and q, and inside a particular sum go in the increasing order, which means both these numbers are going to have the sum as 3, but then go in the increasing order, which means 1 by 2 is less than 2 by 1. And what is the next number? 4, isn't it? What are the numbers of p by q form which have the sum as 4? 1 and 3, 2 and 2, and then 3 by 1. These are the three numbers possible, isn't it? Next one is 5. So what are the numbers which will have 5? 1 and 4, and you can write it down, so on, right? So using this method, if I enumerate all the strings, all the elements of the set, then for any given element, we can say that it will be generated after these many steps. Therefore, every element will get an index, and that index is going to be mapping into the natural number. For example, index for this number according to this enumeration method is 1, and index to this number is 2, and index to this number is 3, this number is 4, 5, 6, isn't it? Therefore, if given any number like 3 by 1, we can say that after 6 steps I'll be able to reach it. After first step this is generated, second step, third step, fourth step, 5 steps, 6 steps. Therefore, every element, we can say that every element could be generated after fixed number of steps, and that finite number of steps is going to be the index for the element, and now that element, that index could be used as the mapping into the natural numbers. Therefore, the set of all these numbers, the set of all these numbers of form p by q are having one-to-one mapping with the natural numbers. If you see that this is nothing but the one-to-one mapping with the natural numbers, right? Therefore, we can say that the set of all numbers of form p by q are countable. Remember this. Now let's see set of all strings generated by any alphabet. Let us say alphabet sigma equal to A comma B. This is the alphabet given, and what can you say about this set containing all the strings which are possible over sigma, which means sigma star. This set which contains all the symbols possible over A comma B is sigma star. And what are all the elements present in this? Epsilon, A, B, AA, AB, BA, BB, so on, isn't it? They are all the strings, and definitely it is infinite. Now we want to find out whether it is countable infinite or uncountable infinite, and what does that depend on? Whether you will be able to come up with a enumeration method. Now let's see what method you want to use. So let us say for some time you forget about epsilon, and let us say it is like all the set of all strings are nothing but, every string is nothing but a word, English alphabet word, English language word. Then if you follow the dictionary order, what happens? In dictionary order you could write them in one order, definitely all these strings. Now if you follow the dictionary order, what happens is, maybe the first element will be A, and the next element will be AA, next element will be AAA, and all these A's will be like this forever. The problem with this enumeration is, with this type of ordering is, if you follow this type of ordering, you will never come across the word starting with B or simply B. B can never be generated in finite number of steps. Therefore this method, this ordering fails. Therefore we want some other clever ordering using which we will be able to generate every string even if it is starting with B. So some other enumeration order which you could use is, maybe you could pause the video and you could think for some time. So what you could use is, you could go in the increasing order of lengths, which means you could generate all these strings of length 0. Therefore epsilon will be generated. Next you could generate all the strings of length 2. So what are all the strings of length 2? A and B, and inside a particular length you could use a dictionary order. The reason is, inside a particular length there are finite number of strings. So if there are finite number of strings, you can use dictionary order so that you can reach any element in a finite number of steps. So inside this string lengths of 1, I can arrange them in dictionary order, which means A and B. And now inside string lengths of 2, I can again use dictionary order, which means AA, AB, BA, BB. And again inside strings of length 3, I can again use dictionary order. AAA, you get 8 strings, right? AAB, ABA, so on, BBB. So now using this method, if you generate every string possible, then what happens is, this one will be generated in 1 step, this one can be generated in 2 steps, this can be generated in 3 steps, 4 steps, 5 steps, 6 steps, so on. Every element in this set can be generated in fixed number of steps. You can give me any number, I can generate in a fixed number of steps. I mean, you can give me any string, I can generate in a fixed number of steps. For example, if you ask me to generate AAB, for example, then after how many steps I can generate it? 7, 8, 9. Therefore every element is going to get an index, and that index is nothing but mapping into the natural numbers. Therefore, since every number has got a mapping into the natural numbers, we can say that this set is countable. So the set of all strings possible over any alphabet is actually countable. You can extend it to any alphabet, not just A comma B. The set of all strings possible over any alphabet is always countable. It has a very important implication, and this result is so popular, and this enumeration method is so popular in the this theoretical world, that they have even given this a name. So if you use this particular ordering, it is also called as proper order. Proper order means going in the increasing order of string lengths, and then within the string lengths we can sort them out, isn't it? That is called as proper order. So proper order is very popular, and it has even got a name. This enumeration is very popular, it has even got a name. Now let's see, if a set is countable, there are lots of implications on this. Okay, so if a set is countable, then what can we say? I'll just see what to do this, how to do. So now you understand that the set of all strings possible over sigma equal to a comma b are countable. And now there is one more important rule, that every subset of countable set is either finite or countable. It is very interesting, which means if a set is already known to be countable, if you take a subset of it, then that is also countable. This particular property has very important implications. I'll just discuss them shortly, but then just understand how it is right. Now I'm saying that a set is countable. A set is countable means this particular set S is countable, then this set is having one-to-one correspondence between all the elements and the set of all natural numbers. This is what I mean to say. Already this set is having one-to-one correspondence with the set of all elements in the set of natural numbers. And now if I take a subset of it, subset means I'm taking some subset small s, then subset means only some of the elements will be here. Now already these elements are present in this set, therefore there will be one-to-one mapping between this particular element and the particular element that is already present in this. For example, if in this set yes, I am going to choose a number or I am going to choose an element from this set capital S and place it here, I will just put a one-to-one correspondence between those two numbers. Now for every element already there is an image here. Image is nothing but itself. Try to understand it. Already a set is said to be countable, therefore it is having one-to-one correspondence with the set of all natural numbers. For every element in this set, there is one natural number in this set, which is set of natural numbers. That is what the meaning of countability is. So now what is that I am trying to do is, I'll just find out, or I'll just take a subset of elements of this set. Then what happens is, I am getting some elements in this set, and for every element, how did I get this element? Because that element is already present in this set, isn't it? Therefore I'll put a one-to-one mapping between the element chosen and its image there. Image means the same element. Then what happens is, already I have one-to-one mapping from the subset to the set, and already there is a one-to-one mapping from the set to the natural numbers. Therefore by composition, that is called composition, we shall discuss it in functions. By composition rule, this set is also countable. Therefore every subset of a countable set is countable in case if it is infinite. In case if it is finite, it is simply finite, but then we are not interested in this. We are not interested. So every subset of a countable set is either finite or countable. So this point is very important. Okay, now we already found out that sigma star over any sigma is countable, which means set of all possible strings is countable. And now a language is nothing but subset of this. Every language till now we have seen is nothing but a subset of sigma star, which means either you take a power n, b power n, or a power n, b power n, c power n, or whatever it is. Every language is a subset of this set, and this set is already known to be countable. Therefore every language is countable. Understand it? Every language is countable. I am not talking about number of languages. Given a language, that is definitely countable, which means all the strings in a language can be put in one-to-one correspondence with the natural numbers. Okay, so every language is going to be a countable language, or it is going to be finite language. Okay, write it somewhere. Now look at this question. Let us say sigma equal to 0, 1, which means alphabet is only zeros and ones. And now sigma star, the set of all strings possible over sigma is sigma star, which is epsilon 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, so on, right? And now this set is also nothing but this set sigma star is also countable. The reason is already we have seen that if sigma equal to a comma b, sigma star is countable. Just you replace 0 with a and b 1 with b, then we get the same language and we can use the proper ordering and we can prove that it is countable. And now we know that this sigma star is countable, and we already know that every Turing machine can be encoded as a string of zeros and ones. You please refer to that topic where I did it. I think in the topic of universal, when I was talking about universal Turing machine, I told you how to convert a Turing machine into a string of zeros and ones. Now this set sigma star is countable, isn't it? And now second thing I know is, first thing I know is sigma star is countable if sigma equal to 0 comma 1. In fact, any sigma star is countable. And now the second thing I know is every Turing machine can be encoded as a string of zeros and ones. This one also I know it. So these two things I know. One thing is sigma star is countable. Second thing is every Turing machine can be encoded as zeros or ones, zeros and ones. Therefore, set of all Turing machines is nothing but set of all strings of zeros and ones, isn't it? Third thing is I can say that set of all Turing machines, let me represent it as S, is a subset of sigma star. Just try to understand this point. Now if I encode every Turing machine as a string of zeros and ones, and now if I list them all in one set, that set will definitely be a subset of this. Or you can take this sigma star and you can take each string one by one, which is generated by enumeration method, and then you can check whether a given string can be a valid Turing machine or not. If it is a valid Turing machine, you can take it. If it is not a valid Turing machine, you throw it. Then whatever strings I get into S, that is definitely a subset of sigma star. Now what can you say? So using these 3 points, what we can say is, and we already know that, one more point I am just adding it, you already know that point, but just I am adding it. Now every subset of countable set is either finite. If it is not finite, it is countable, isn't it? So we know that set of all Turing machines, they are not just finite, they are infinite. But then what kind of infinite? Countable infinite. Therefore, using this rule, we are able to find out that this set of all Turing machines are countable. Okay. So this point, therefore using all these points, I hope that you are writing them down. Therefore using all these points, we can say that set of all Turing machines are countable. Using all these points, I can derive this. So this point has lot of implications. Okay. Now we know that. Okay. So if you understood it, I'll derive more points on that. You please note down all these points. Now sigma star. If sigma equal to 0 comma 1, then sigma star is countable. This one we have already proved it. And next one is every Turing machine can be encoded as a string of zeros and ones. We did it when I discussed about the universal Turing machine. And next one is set of all Turing machines is a subset of sigma star. Why? Because if you write down all these strings of zeros and ones, they are nothing but they belong to the sigma star only. Therefore there is subset, and we already know that every subset of countable set is finite or countable. This one also we have already seen. Therefore from all these points we can say that set of all Turing machines are countable. Now this particular point is going to have lots of implications. Now we shall see what those implications are. Okay. Now knowing that set of all Turing machines are countable is going to lead us to many implications. Now what are the results we get out of it is, since we already know that, watch it. Now Turing machines are countable. Let me say C is the shortcut to represent that Turing machines are countable. Then what does this imply? Then how many our Turing machines are there? there will be those many recursively enumerable languages. Therefore, since the number of Turing machines are countable, the number of recursive languages are countable, isn't it? Therefore, recursively enumerable languages, not recursive, recursively enumerable languages are countable, isn't it? Now, what does this mean? If recursively enumerable languages themselves are countable, so we can say that a recursive language is a subset of recursively enumerable language. Therefore, the number of recursive languages are countable. RL means not regular, it is recursive languages. Recursive languages are countable. Now, context-free language is a subset of recursive language, isn't it? Sorry, context-sensitive language. Therefore, context-sensitive languages are countable, and push down onto that context-free languages are again subset. Therefore, context-free languages are countable, because every subset of a countable set is countable, and we know that all these languages are like Russian dolls. If you open Russian dolls, you know that if you open a doll, inside that there will be one more doll. If you open that doll, inside that there will be one more doll, isn't it? Like that, inside that language everything is contained. So therefore, if the main language is countable, then already the languages which are present inside it as a subset, proper subset, are already countable, isn't it? So context-free languages are countable, therefore regular languages are countable. Everything is countable. All the languages, either you say the number of recursively enumerable languages available, they are countable. Everything is countable. And next implication is, if you look at the hierarchy of these Turing machines, these machines, Turing machine is the biggest machine, and all the machines are present inside it. And what we could say about all this is, now see, the better solution will be, instead of talking about the languages directly, the better idea would be the other one. So for every language there is a Turing machine, isn't it? So every recursively enumerable language if number of Turing machines are countable, every recursively enumerable language is countable. Okay, the set of all recursively enumerable languages, and direct implications will be like this. So we can say that every Turing machine is a push-down automata is, you can modify a Turing machine in such a way that it can act as a push-down automata. Therefore, if Turing machines are countable, then push-down automata are countable. The reason is, we can modify a Turing machine in such a way that even though it is having the input tape, instead of using it as a tape, if it could use it as a stack. Therefore, if Turing machines are countable, then push-down automata are countable. The reason is, push-down automata are a slight modification to Turing machine, isn't it? And now if we know that even LBA is also a slight modification of Turing machine. If already Turing machines are countable, then a subset of the machines which are supposed to use only that restricted stack, they are also countable. Therefore, push-down automata are countable, and finite automata is nothing but a Turing machine which is restricted in such a way that it has to use only finite amount of memory on the tape. Then finite automata are also countable. So everything we know of as of now are all countable because of this rule. Okay, but then even though the number of languages are countable, see this, one important thing is, even though all these languages are countable and the machines are countable, we didn't prove that the set of all languages are countable. Okay, so I'm not trying to confuse you, it is a bit confusing, so you please rewind the video over and again and listen it. So what I didn't prove yet is, I didn't prove that the set of all languages possible are countable. I didn't prove that. Actually, the set of all languages possible are uncountable. Now, the set of all Turing machines or any number of machines possible is countable, and the set of all languages possible is uncountable. Therefore, there are some languages for which there are no machines at all, which means there are some languages which are not even recursively enumerable. Okay, we shall prove it later, but for now these are all the implications which we got from this. Okay, now let us assume that an alphabet is given, sigma equal to a comma b, and it can be extended to any other alphabet, a, b, c, or 0, 1, 2, anything. but assume that one alphabet is given, sigma equal to a comma b. Now we know what is sigma star. Sigma star is set of all strings possible over a comma b, and we already know that sigma star is countable. And now what we could prove is 2 power sigma star. 2 power sigma star is nothing but set of all subsets of sigma star, which is nothing but set of all languages possible. We can prove that 2 power sigma star is uncountable. So how we could prove is, I am going to show you the proof now, and how they have proved it initially is, there is a scientist by name Carter. He has given a method called as diagonalization, using which he made a statement and then he proved that statement. But even though I am going to prove it, I'll just write it in terms of some other statement, and again we shall come back to this. So this point, no, you already know. If sigma equal to a comma b, sigma star is countable, you already know. So how do we know that sigma star is countable? Because we are going to have a proper order. So whenever we have proper order, that is nothing but enumeration, so that is countable. And now you don't know how to write how this is right, which means 2 power sigma star is countable. How is that right? We don't know that yet. Okay, but then what I know is, okay, first going before proving it, let's see what the original proof is, what the original theorem is, and then how they have converted that theorem to this one and they have proved it. Okay, so the original theorem is like this: if a set S is countably infinite, which is nothing but countable, then they say that 2 power S is uncountable. This is what they have proved. So even no, proving this or proving this, both are same, but coming to TOC, it is better that I'll take the first statement and prove it. Or you can, even if I prove the second statement, it can imply this first statement. The reason is, in place of S, I am going to put sigma star. Already we know that sigma star is countable. Then 2 power S is uncountable. It follows from the proof. Either you can take first one or second one. I am taking the first one because we are talking about TOC. Okay. So in TOC we are talking about sigma and languages and sigma star, everything. This will be easy for you to understand. That is why I am taking it. Anyway, there will be no difference. There will be not much difference. And before going ahead, you should understand this representation 2 power S. 2 power S is nothing but set of all subsets, which is also called as power set. So I'll just take a small finite example and I'll show you what a power set is, and then we shall go ahead. See this. Now if S equal to a finite set, I'm not talking about this theorem, I'm just explaining what a power set is. If S equal to a comma b, then what will be 2 power S? Set of all subsets. What is set of all subsets of this? One is empty set is a subset of that, and then a singleton set is a subset of that, and then everything a comma b is a subset of that. Therefore set of all subsets is containing 4 elements, all these 4 elements. So that is what the meaning of power set is. So if a element is, if S is countable infinite, which means if there are infinite number of elements here, then the set of all subsets is nothing but you are going to take some elements of this and we are going to form the subsets. That is the meaning of it. Okay. So now let's just first discuss about that statement. Anyway, you could take down the two statements. Now whatever I am going to prove is going to be the proof of these two. Okay. So this is just an example. Now I want to prove that if sigma equal to a comma b, which means input alphabet is a comma b, then we already know that sigma star is countable. Now I want to prove that 2 power sigma star is uncountable. So first of all, if sigma equal to a comma b, what will be the elements of sigma star? You know that sigma star will contain epsilon a, which means set of all strings possible, a, b. You can write them in any order, no problem. A, B, BA, so on. Or let me just extend it. A, so on. Okay. These are all the elements of sigma star. Sigma star contains all these elements. Now we can represent any subset of sigma star as one element of 2 power sigma star. So the elements of 2 power sigma star are nothing but subsets of this set. Okay, now how do I represent a subset of this is, for example, one element of 2 power sigma star is, first of all, you know what 2 power sigma star is, right? It is nothing but set of all subsets of sigma star, which is nothing but set of all languages possible. Okay, now one language, let us say, is A, B, A. Then how can I represent this language is, I could say if element A is present, then I am going to represent it with a vector. In the under A, I am going to put 1, which means, see, in this set epsilon is not present, therefore it is going to be 0. A is present, therefore it is going to be 1. B is present, therefore it is going to be 1. A is present, therefore it is going to be 1. And no elements are present, therefore all are going to be zeros. So every element of this set 2 power sigma star can be represented as a string of zeros or ones, zeros and ones. So every element is going to be represented like this. Let us say I have an element like this, epsilon and BA, that's it. Then how can I represent it as a string of zeros and ones? Then epsilon is present, A is not present, B is not present, A is not present, AB is not present, BA is present, this is not present, so on. So I can represent every element of 2 power sigma star, which means every language, as a string of zeros or ones. Okay, so what has happened now? Now I am representing every language like this. Now what I do is, I assume that 2 power sigma star is countable. So I initially assume that 2 power sigma star is countable. Therefore, if a set is countable, we know that every element in that set is going to get an index, and depending on that index, I am going to put all the elements in one table. So try to understand it. Now I am assuming that the first assumption is 2 power sigma star is countable. If a set is countable, we know that it can be mapped, it can have a one-to-one mapping with natural numbers, which means every element in that set is going to get an index, and using that index, I am going to put all the numbers, I am going to put all the elements in one table, and the table is going to look like this. So let us say every element is kept in its corresponding index 1, 2, 3, 4, 5, 6, so on, and the elements are like this. Just every element, every possible element. It can be anything. I am just taking this as an example. Something like this. So now every element of this set are now placed in a order fashion, in an orderly way, using the indices of the elements, because the set is a countable set, because I am assuming that the set is a countable set. So all the elements have been written in the table. So every element should definitely get, if an element belongs to the set 2 power sigma star, that should definitely be present in this table at some point, at some index. So either here or here or here. Okay, that is the assumption. So all the elements have their indices, and according to the indices, I have written all the set, all the strings in the table. Now it is going to be infinite length, this way and that way. Anyway, my assumption is I have written all of them. Then what I do is, I'll take the diagonal elements. I'll take the diagonal elements like this, the entire diagonal, the main diagonal, and then what are the elements in the main diagonal? You see that the elements in the main diagonal are 0, 0, 0, 1, 0, so on. Now what I do is, I'll just complement this 1, 1, 1, 0, 1, so on. Now I'll get a new element. This element is not present in the set, definitely. The reason is, this element cannot be the first element, because it is differing with the first it is differing with the first bit of the first element. This element cannot be the second element, because it is differing with the second bit of the second element. This cannot be third element, because it is differing at least in one point. It cannot be fourth element, because it is differing at least in one point. Therefore, whatever we got, the newly got string, that is not present already in the table. Therefore, our assumption that the original language is, or the original set is countable, is wrong. Okay, so what can we say? 2 power sigma star is uncountable. Actually, the proof is very simple. Maybe it will be difficult for you to understand in one go. You please rewind this video and again watch it. Anyway, I'll just give you the summary like this. See, I'm saying that sigma star is set of all strings. So I am going to write the sigma star entirely here, and every element, every language is nothing but a subset of this. Therefore every language can be written like this. Every language can be written like that. Language can contain a string, or it may not contain a string. If it doesn't contain a string, I am going to put a 0. If it contains a string, I am going to put a 1. So now I assume that the set of all languages, which is nothing but 2 power sigma star, are countable. Now according to the definition of countability, if a set is countable, all of the elements are going to get some indices. Now my assumption is that yes, all the elements have got some indices. According to their indices, I am going to order them in a table, just in a table from top to down. Then if I do this, every element which is present, every language which is present in 2 power sigma star should occur at some point at some index, isn't it? So all the languages should be there in the table. That is what is right. Actually that is right if our assumption is right. What is our assumption? That it is countable, right? Now I have taken the main diagonal elements, and now I got a new new language by just complementing this. And that new language cannot be first language or second language or third language, because that new language differs with every language in at least 1 bit, isn't it? Therefore I got a new language which is not already present in our table. Therefore my assumption that all the languages are present in the table at some index is wrong. Therefore my assumption that the entire set is countable is wrong. So what did we get finally? Finally we got that the set 2 power sigma star is uncountable. Okay, it is very important. So what can we say now? The set of all languages possible are uncountable. We have already seen that the set of all Turing machines are countable, but the set of all languages present are uncountable. So what could you say? The number of Turing machines are less than the number of languages. So there must be some languages, or at least one language, or definitely there will be some language. So there must be some languages which are actually not recursively enumerable language, or Turing machine is not so powerful that it could accept every possible language, which means there will be some languages for which there will be no Turing machine. Why? Because every Turing machine can define only one language, and now we have more languages compared to the Turing machines. Okay, so maybe if you didn't understand it, you could write all the points one by one. First point is, I am assuming that 2 power sigma star is uncountable. Therefore every element of 2 power sigma star can be placed in the table, and every element will be placed exactly at some index, isn't it? Then every element is already present in this. Then I later found out that I have got a new element which is not already present. Therefore my assumption that all the elements are present in this is wrong. So my initial assumption that it is countable is wrong. Therefore it is uncountable. So what is the implication we got? Set of all Turing machines are countable, and set of all languages are uncountable. So what could we say? There are some languages for which there is no Turing machine. This is Turing machine which is countable. This is set of all languages which is uncountable, 2 power sigma star. Therefore there are some languages which are not recursively enumerable. So the reason is simple. Every Turing machine can define only one language. So if I give one-to-one mapping, then all the Turing machines will be over too soon, and then there will be many languages remaining for which there will be no Turing machine. Got it? So outside these recursively enumerable languages, there will be even more languages. Okay, so this is how we could prove it. And one more way of saying this same statement is, if S is a countable set, if S is uncountable set, then 2 power S is, if S is countable set, then 2 power S is uncountable. It can be proved in the same way. How? You just write all the elements of S, and then you represent every element of 2 power S as a string of zeros or ones, and you do the same assumptions and do the same thing. In place of sigma star, if you replace S, we get the same thing, right? And using this method, we can prove that real numbers are also uncountable. Maybe you could work it or not on that. So how we could do it is, maybe you can try to write all the real numbers in a table, and then you take the diagonal of this and you just complement the diagonal, then you get a new element, and definitely that element is not in the table. The same way, see, simple, you write all the real numbers in some order in the table, and then you take the diagonal and whatever element is there, you just take the 9's complement. 9's complement means 9 minus that number. Then you suddenly got a new number which is not already in the table. Therefore, you can say that set of all real numbers are uncountable. So if you want to prove that anything is uncountable, the best method is diagonalization. If you want to prove that anything is countable, the best method is that enumeration. You find out enumeration method. Got it? So now using this you will be able to answer any gate question. Okay. See these statements about the countable sets. These statements I am going to give you proof in informal way, and these questions there is a chance that they might ask you as a theory, like true or false questions. Therefore, they will not ask you the proof, but still I will give you some proof to some extent. Okay. So what you could do is you could write down these points and then possible by heart it, or at least see or try to remember them somehow. Our proofs are very simple. I'll just give you the proofs. If S1 and S2 are countable sets, then S1 union S2 is countable, which means if you have two countable sets and if you apply union to that, then it is also countable. So how is it possible is S1 and S2 are already countable, which means there is a enumeration procedure which will generate all the strings of S1 and S2. See this? Now already S1 is countable and S2 is countable, which means there is already a enumeration procedure available which can enumerate A1, A2, A3, all the elements of S1 like this, and all the elements of S2, B1, B2, B3, which is already able to enumerate all the elements like this. Now we are saying that S1 union S2, which means if I apply union these two, the resulting elements, whatever I get, they are also countable. That is what we should prove. Then simple, what we do is run the enumeration method of S1 to one step and generate A1, and run the enumeration method of S2 to one step and generate B1. Therefore, resulting enumeration method is nothing but combination of these two enumeration methods. Run the enumeration method for S1 for one step and generate A1, and run the enumeration method of S2 for one step and generate B1. Therefore, every element will be generated like this: A2, B2, A3, B3, so on. So any element can be generated after finite number of steps. If you want B2, initially if it is 2 steps, now it will be 4 steps. That doesn't matter. Only thing what matters is every element of the set can be generated after some fixed number of sets. Therefore, S1 union S2 is again countable. In fact, you could apply this method to any number of sets, to a finite number of sets, which means if S1, S2, S3, so on Sn are all countable sets, you can apply union to all S1, S2, so on union Sn, and we can generate all the elements in a enumeration procedure, which is actually a combination of enumeration procedure for S1, S2, so on Sn. Similarly, you can extend this. That is what I mean to say, right? And next one is S1 cross S2 is again countable. So if S1 and S2 are countable, S1 cross S2 is also countable. That is what we have to prove. So what you could do is, if S1 and S2 are already countable, then all the elements have already got their indices, isn't it? 1, 2, 3, 4, 5, 6. All the elements have already got their indices, right? Then what you do is, you just add 2 indices, go in the increasing order of indices, which means, okay, how to prove it is, do you remember how we have proved that quotients, set of all quotients of form P by Q? Same method you can apply here. So there the P by Q both are numbers, therefore we have taken the sum of P plus Q, and then we have gone in the increasing order of P plus Q, and for a given P plus Q we have sorted it out, isn't it? The same method can be applied here. So what you could do is, since we are not sure that S1 and S2 contains only numbers, it could be any other elements. So already S1 and S2 are countable, therefore the elements are like this: A1, A2, A3, A4, so on, and then B1, B2, B3, B4, so on. Then you could give them natural numbers 1, 2, 3, 4. Why? Because they are the indices, right? So every element is going to get a natural number. Now you just replace every element in S1 and S2 with their corresponding indices. Then what you do is, go in the increasing order of these natural numbers like this. First you generate all these numbers, then you give them the corresponding natural numbers, then go in the increasing order of the sum of these natural numbers, which means now if you take that the sum is 2, then what is the only combination possible? 1 1. 1 1 is nothing but a1 b1. And what is the next sum? 3. So 3 means 1 2 and then 2 1, isn't it? Therefore what do we get? The element a1 b2 and the element 2 1 is nothing but a2 b1, right? Therefore we get every order pair at some point. And next the sum is 4. 4 means 1 3 2 2 3 1, isn't it? So you can go on like this, and 1 3 is nothing but a1 b3 and 2 2 is nothing but a2 b2 and 3 1 is nothing but a3 b1. So like this you can generate all the elements in some order. So even if you don't remember the proof, just remember that if two sets are countable, then their cross product is countable. If two sets are countable, then their union is countable, and the union can be extended to any number of finite sets, as well as cross product can be extended to any number of finite sets. See this? That is what they are saying. It can be extended to any number of countable sets. Cross product, the previous one, it can be extended to S1, S2, S3, so on, anything. How? The same method can be used, isn't it? So the starting point is, since they are countable, they already have enumeration method. Therefore I am using that enumeration method to be used as enumeration method for the resulting set. Got it? And now the set of all languages that are not recursively enumerable is uncountable. It is somewhat interesting question. Maybe they might ask you as a true or false. See, one more thing, they didn't ask you all these difficult questions till now. All the questions which are asked in GATE are very simple. I am going to solve all of them, and these are the difficult questions which I am trying to solve. They might not ask them in GATE, but still knowing them will give you an advantage in case if they ask you. Okay. Now the set of all languages that are not recursively enumerable is uncountable. So we know that the set of all languages can be partitioned into two sets: the set which is recursively enumerable and the set which is not enumerable. We know that set of all languages is nothing but 2 power sigma star, isn't it? Now this 2 power sigma star can be partitioned into two sets. It is set of all languages. One set is countable. Why? Because it is recursively enumerable. These are all set of languages which are recursively enumerable. Since Turing machines are countable, this set is countable. So the set of all recursively enumerable languages is countable. Now we don't know about the other set. This is the set which is containing languages which are not recursively enumerable. We don't know anything about it. Just assume that this is countable. If we assume that this is countable, then the entire set is a union of two countable sets. Therefore it has to become countable, but then we already know that 2 power sigma star is not countable, therefore this is not countable. Okay, I don't know if you understood it or not. See, again let me explain you. What I mean to say is, the set of all languages is nothing but 2 power sigma star, set of all subsets of sigma star, that is set of all languages. Now out of these languages, some languages are already recursively enumerable. How? If there is a Turing machine for a language, then that language is recursively enumerable, and we already know that the number of Turing machines are countable. Therefore number of languages in the total languages which are recursively enumerable are countable, and that will be equal to the number of Turing machines. Therefore one part of this set which is recursively enumerable, which contains set of all languages, which means in this side all these languages are recursively enumerable, are already countable. Okay. Now the remaining set we don't know about it. So I am just assuming that the remaining set might be the set which is nothing but the set of all languages which are not recursively enumerable is, I am just assuming that is countable. Then what happens to the resulting set? The resulting set is a union of two countable sets. Therefore that should be countable. How? By using this rule. The union of two countable sets is again countable, isn't it? If that is true, then our initial proof that 2 power sigma star is uncountable is a failure. But then that is true, isn't it? Therefore our assumption that it is countable is false. So the set of all languages which are not recursively enumerable must be uncountable, which means there are infinite number of languages which cannot be accepted by Turing machine, and that infinity is uncountable infinity, very large. Got it? Okay. Let's talk about computability and decidability. Actually, both computability and decidability are same. In the sense, both of them talk about whether there exists an algorithm or not. Okay, before going ahead, let me explain you what an algorithm is, and let me show you what the difference between Turing machine and algorithm. Okay, so algorithm it is nothing but a Turing machine, but this Turing machine is supposed to halt. So if for a problem there is an algorithm, it is as good as saying that for that problem there is a Turing machine which is always going to halt. But then if you have a Turing machine, it is not actually an algorithm. The reason is algorithm is supposed to halt after finite number of steps or after some number of steps. But then Turing machine is never going to halt. Therefore, only halting Turing machines are considered as algorithms. Okay, and now you already know that Turing machines are countable. So I'll just extending this concept. You already know that Turing machines are countable, isn't it? And therefore halting Turing machines are a subset of Turing machines, and I already told you that every subset of a countable set is already countable. Therefore halting Turing machines should also be countable. So halting Turing machine is nothing but an algorithm. So what did we find out now? Even the algorithms are also countable. But then we found out that the number of languages are uncountable. Every problem can be compared to a language. Okay, so now the number of problems are uncountable and number of algorithms are countable. Therefore what could we derive? That there are some problems for which an algorithm might not exist. Okay, so let's talk about what is the exact meaning of computability and what is the exact meaning of decidability. I hope that you understood what an algorithm and Turing machine is. From now on I am going to use wherever in order to say that there is an algorithm, I can even say that there is a Turing machine which halts, or in place of Turing machine which halts, you can put an algorithm. Okay, now let's see what is the difference between countability and decidability. Actually both the concepts are very identical, or sometimes both of them are used in place of each other with a minor difference. Okay, whenever we talk about a function, so whenever we talk about a function, like let us say f of n equal to n square plus 1. So what is the meaning of it is, if you give it some n, it is going to compute this value. So given an input, if it is going to compute some output, then that is called a function. Now if there is a algorithm to compute a function, then such a function is called computable. Okay, so if there exists an algorithm, or what is an algorithm? Turing machine which halts, isn't it? If there exists an algorithm or a Turing machine which halts, which takes this input and then produces this output. In terms of Turing machine, how can I write it is, if there exists a Turing machine to which if the input is given on its tape, then again it is going to produce the output on the same tape, and then it is going to halt for every input given is called a then that function is called computable. Okay, so what is the definition of computability is, if there is a function which is defined on a domain. So what is the domain for this? F of n, let us say the domain is set of all numbers, set of all integers. Then what about the range? Range is nothing but set of all a subset of positive integers. Okay, so given a function and a domain, domain means from which set are you going to pick up the input. Given a function and the domain, if there is a Turing machine which will produce the output on the tape, given that input on the tape, it should produce the output on the tape, and it should definitely halt for every input chosen from the domain. Okay, domain is very important. So once you fix up a domain, and if for all the inputs from the domain, if your Turing machine is definitely going to halt with the output on the tape, then we can say that such a function is computable. It is very simple. See, in simple words, what it is let us say you have a function. Okay, let us say the function could even be not just this one. The function could even be a problem. I don't want to use the word problem, but then just think of it like this. We want to sort all the numbers. Now all the numbers are given to the Turing machine. They are all on the tape, and now the Turing machine should try to sort it out and then keep them in ascending order. Then that is also a function. A function is going to take a set of natural numbers, and then it is going to produce a set of natural numbers. Therefore domain and range both are natural numbers. So if your Turing machine is able to solve that function for all the inputs coming from your domain, and it is definitely going to halt, then such a function is called computable. Okay, and coming to decidability, we just want to simplify the things. So very often talking about functions and then giving some proofs is somewhat difficult. It is not impossible, but then it is somewhat difficult. Just to simplify the things, we are more interested in rather than functions, we are more interested in problems. So what is a problem is a statement whose output will be either true or false. And now our whenever we, for example, a problem can be like this. Classic problem is n, a number n, a prime? You just have to find out is m a prime, which means here you are not actually taking the input and then producing some output. Here you take an input and you just say one thing, either yes or no. If 3 is given, if n is given as 3, you say yes. If n is given as let us say 10, you say no. Alright. So if you have such a problem whose answer is either yes or no, and if there is an algorithm or a Turing machine which should definitely halt for all the inputs from the domain. So here domain is, let us say domain is set of all natural numbers. Set of all natural numbers. Okay. Now when do I say that a problem is decidable is if for a problem there exists an algorithm or a halting Turing machine, both are same, which will take anything from the domain, which means it will take any input from the domain and which will say either yes or no correctly, and it should halt. If you have such a machine or such an algorithm, then we can say that that problem is decidable. So decidability is very easy to apply compared to computability. It can be shown that we can convert a problem from computability to decidability and then think about this, or give some proof whether a problem is decidable or not. Okay, so what we are interested in is either in TOC or in algorithms. Rather than talking about computability, we will talk about decidability. We will take a function and we somehow convert it into a yes or no problem, and then we try to find out if there is a Turing machine which can answer that problem. In case if there is a Turing machine which can answer that problem, we can say that there will be a Turing machine which can compute it. It is straightforward. Therefore we are not interested actually in the functions, we are interested in the problems. Okay, so what I mean to say is whenever we have a domain, okay, and now given any input from the domain to a Turing machine, that Turing machine should definitely halt and say yes or no for such a problem if you can find such a Turing machine, or if there exists such a Turing machine. If we can prove that there could be such a Turing machine existing, then we can say that the problem is decidable. Okay, simple. So function means, computability means we talk about function and there should exist algorithm or halting Turing machine, and decidability means we are talking about a problem which is nothing but yes or no answer, and if there exists algorithm or Turing machine which halts, then we say that it is decidable. So computability and decidability both are actually same, but only difference is when we talk about the function and when we talk about the problem. I hope that you understood it. And one more thing you should be very careful is every time a problem, whether it is decidable or not, that should depend on the domain, because given a single instance it is always decidable, isn't it? So for example, given a single instance it is always decidable. Simple. So how can I prove that a single instance is decidable is, let us say you have given me some problem. Okay, I'll just talk about a problem which is undecidable, which means we cannot give a generic algorithm for that, and then I'll tell you that for a given instance we can find see, it is somewhat difficult to understand, so you please pay more attention here. Now there is one example, classic example. Example is a given grammar capital G is ambiguous, which means given a grammar you should find out whether it is ambiguous or not. Okay, and now let me say the domain is set of all context free grammars. So actually this problem is undecidable. Okay, I know I'll just talk about this problem shortly after some time, but then this problem is undecidable, which means there is no algorithm or there is no halting Turing machine which can say that a given grammar capital G is ambiguous. This problem is ambiguous. Or see, so how is it a problem is, now you give a specific instance or specific grammar and you put in place of G, the answer should be either true or false, isn't it? So the statement will be either true or false depending on what the input is, but the domain is set of all context free grammars and this problem is undecidable. Later I'll show you how to prove that it is undecidable, but for now assume that it is undecidable. Now if the domain is not set of all problems, if I give you only single instance, which means I am just giving you domain is not this, I am just giving you this particular grammar G1, is it decidable or not? This is definitely, this particular grammar G1, is it ambiguous or not? So answer is definitely it is decidable. The reason is you could find a Turing machine which will always say yes or which will always say no. Now if this grammar is actually ambiguous, now you can give this Turing, now there exists a Turing machine which will say yes, isn't it? So it is, it is very difficult to understand this, but just pay attention here. See, I am saying that if the domain is very large, sometimes some problems might go undecidable, but then if the domain is a single instance, which means given a grammar, if you are asking whether it is ambiguous or not, I am saying that it is decidable. Why? There has to be a Turing machine which should say yes or no, and then it should definitely halt. Now what I take is, I'll just produce a small Turing machine which will always say yes, and then I'll say that there exists a Turing machine which will say this, or I'll produce a Turing machine which will always say no, and in case if the answer for this one G1 is not an ambiguous grammar, then I'll say that for this problem there is a Turing machine, therefore it is decidable. So just keep this point in mind, that a particular instance of any problem is always decidable, but then when it is applied to a common domain, it might be decidable or undecidable. For that we need to prove. So it is very important, just write it somewhere. Any particular instance of a problem is always decidable. Any particular instance means given a particular grammar G1, whether it is ambiguous or not, it is decidable, because you can give a Turing machine which always says yes or which always says no. At least one of it is going to be the answer, isn't it? So very important point, given an instance of a problem, it is always decidable. Why? Because there always exists a Turing machine. What is a Turing machine? Take a Turing machine which always says yes, or take a Turing machine which always says no, whatever the input is. Now at least one of the Turing machine is going to be the Turing machine for this instance, isn't it? That is how we can prove it. But then given over a range, then that depends, right? So now in TOC, our main concern is will be given many problems, and now we should be able to say whether that problem is decidable or not. So in order to do this, we use a trick, we use an indirect method. So finding out whether every problem is decidable or not, it's somewhat difficult. So what we do is, we find out one problem which is undecidable. Okay, let me just show you this in terms of writing. Hope that you have taken everything, and whatever I speak you please note it down, note them down also. You keep pausing the video and writing it. Okay, these are all very important. And what happened is, in GATE for the past 2-3 years, before 2-3 years they didn't focus much on the Turing machine decidability, countability, but then I think they have used up regular expressions, regular languages, context free grammar questions so much that I think they are out of the questions. Therefore they are now focusing on a new topic. See, and one more thing is, previously, in maybe before 5-6 years, this particular GATE question paper, the number of aspirants used to be less and the coaching used to be not so good. Therefore, even for a moderate kind of question, it was very difficult for many people to answer them. But now with these many coaching centers and with this lot of effort going on, people are able to answer many questions very easily. Therefore, the standard of the GATE examination is going to be increased. So if they have to ask a difficult question in TOC, the only topics which will be suitable will be Turing machines, or decidability, undecidability, countability. So these are very, very important. Even in algorithms also we have the same concepts. So I feel that in GATE 2015 they are going to definitely touch more questions from PNP, decidability, undecidability, and then Turing machine. So I'll be discussing about Turing machines in depth, so that even if they ask you a very difficult question, you will be able to answer it. Okay, so what I would like to tell you is, whatever I speak, even every single word, you please pause the video and keep noting them down. It is very difficult for me to write everything on the board. It is not that if there is something on board you should write it. Write everything that I am speaking, so that you will be able to easily understand it later, or easily refer to it later. Now let me tell you one important, very, very important point here. This is going to be very important even when you discuss algorithms. Now, how can we prove that a problem is undecidable? I'll talk about something called as convertible. So if there is a problem P1, and if there is an algorithm or a halting Turing machine which can convert it to a problem P2, which means there is algorithm, okay, and now if there is an algorithm to solve problem P2, which means there is an algorithm, this P2 is decidable. See, now there is a problem P1, I am able to convert it to problem P2, and now problem P2 there is algorithm. Then I can say that for problem P1 there is an algorithm. Therefore, if P2 is decidable, then P1 is decidable. How? First you convert the problem P1 to P2 and then you solve P2. Therefore, since we are able to solve P2, it is nothing but the answer for P2. Now the conversion should work in such a way that the answer to P2 should also be an answer to P1. Okay, I'll just repeat it again. See this, if there is a problem P1 and there is an algorithm to convert it to a problem P2 in such a way that if the answer to P1 is true, the answer to P1 should be true, which means whatever answer I get here, that should even be the answer to P1. If there is a conversion algorithm like that, and now there is an algorithm to solve P2, it is as good as saying that we got an algorithm to solve P1. Then what is the algorithm? Conversion algorithm plus solving algorithm. Now this procedure is called reducibility. Reducibility means converting one problem to other problem in using an algorithm or a halting Turing machine. Now if you find out that this problem is decidable, then definitely this problem is decidable. Okay, so I'm just writing it. See this, if P2 is decidable, then P1 is decidable. Under the conditions, what are the conditions? There has to be algorithm to reduce every instance of problem P1 to an instance of problem P2, and there has to be algorithm to solve problem P2. Therefore, if there is a reduction algorithm and then there is a solving algorithm for P2, then we can say that if P2 is decidable, which means if there is a solving algorithm for P2, then P1 is decidable. If you can solve P2, it is as good as solving P1. Okay, it is very straightforward. I think you will understand it, but the next point is somewhat difficult to understand. So just try to understand this. Now if it is already known that, if it has been already proven that, or it has been already proved that problem P2 is undecidable, problem P1 is undecidable, and now there is a polynomial time conversion to problem P2, definitely problem P2 cannot be decidable. Okay, so try to understand this. If P2 is decidable, P1 is decidable, but before this, if it has been already proven that the problem P1 is undecidable, which means there is no algorithm or Turing machine, it has been already proven, then definitely P2 should be undecidable. The reason is, in case if P2 is decidable, then it actually conflicts with our proof that P1 is undecidable. Okay, these 2 points are very important. Okay, so if there is a polynomial time conversion from, or not polynomial time conversion, we shall talk about the time later. If there is an algorithm or a halting Turing machine which can convert every instance of problem P1 to some instance of problem P2 in such a way that answer to problem P2 is also an answer to problem P1, and if there is an algorithm or halting Turing machine which can solve P2, then we can say that P1 is decidable, which means if there is a reduction algorithm from P1 to P2 and if P2 is decidable, then P1 is decidable. This is straightforward, isn't it? Now the second point is very important. If P1 is already proven to be undecidable, it is already proven to be undecidable, then definitely P2 must be undecidable. Why? The reason is, if P2 is decidable, then it turns out that P1 is decidable, which actually conflicts with our already existing proof that P1 is undecidable. Therefore, P2 should definitely be undecidable. So how do we now from now on, how can we prove that a problem is undecidable? Is, see, this particular point is given wrong in every possible book, in every possible local addition book you take it, in every possible gate question they solved it, this point is completely given wrong. Okay, if you want to learn about it, please read the standard books like Ullmann, there they have given it right, but then don't read them, you will not be able to understand this. Just follow my lectures, I am going to cover everything possible. Okay, now what I am trying to say is, in order to prove that a given problem is undecidable, so what you should do is, try to find out first a Turing machine. If it is not possible, you cannot say that if you fail to find a Turing machine which halts, or if you fail to find an algorithm, you cannot directly say that it is undecidable. There should be a rigid proof. Now for that reason, already there is a one small problem or one basic problem which has already been proved to be undecidable. That problem is halting Turing machine, that is also called as halting problem. I'll discuss about it shortly. Now there is already a basic point or basic problem which everyone knows that it is undecidable. Okay, that is nothing but halting problem. Now you take this halting problem and then you give it to you convert it to any problem, any given problem at hand, then we can say that it is undecidable. And now you take this problem and you convert it to any other problem, then you can say that it is undecidable. So that is how undecidability is decided. Okay, I mean undecidability is found out. So given any problem, first you start with the halting problem, convert it to some other problem, convert it to some other problem. Whatever you get on the way, all these problems are undecidable. Okay, so the starting point for the theory of undecidability is halting problem. Now I will show you what the halting problem is. We shall discuss about it, and then we shall see how to prove that various other problems are undecidable based on this one. Okay, Turing machine halting problem is the most interesting problem in computer science. The reason is, this is the basic point which is used to prove that other problems are undecidable. And in early 1900s, the scientist and the professor Turing has found an interesting scenario. So what happened is, he is a professor and he is having many PhD students, the students who are doing PhD under him. And actually the requirement for a PhD is you are supposed to publish at least 5 papers, or I think 3 papers if it is related to the same area, and it is 5 papers if it is chosen from various random areas, which means if you are working in the same area, same topic, 3 publications are enough, international publications. And if it is in different areas, 5 are required. So what happened is, he is having lots of PhD students, and whenever he see them, actually they all seem to be very busy. So always they are very busy working, but then no one is graduating, which means no one is publishing papers or no one is leaving the university. So because obviously you know the reason, the university life is the best life, and they got addicted to that cool job, cool life, because they will be getting the stipend, they need not do anything, they have to go to lab, sit there and then come out, there are no deadlines, anything. Therefore he got confused, what should I do? I mean, it is not, they are never halting, they are always busy computing, but they are never halting. So should he wait for more time or should he stop them? Isn't it? That is a kind of Turing machine halting problem, isn't it? So what he did is, he tried various methods, like he said that after 6 years, if you are still in the university and if you didn't finish your PhD, I am going to stop your stipend. And then he removed from their computers all the video games, everything he tried, but then nothing seemed to work. Then what happened is, he tried to persuade them using some other means. He started sending them mails saying that there are attractive jobs in the industry if you finish PhDs. But even that plan also backfired. The reason is, they had to go there and work in order to get the money, but here they are getting the money without anything. So I mean, even if it is not for money, they need not work, they can just stay in the campus and in the lab, and they have a cool life. So they are never going to graduate. So then he found out that this problem can never be solved, no one could solve a problem. Now in present scenario, if anyone joins a PhD, there is no guarantee that he is definitely going to halt and get the PhD degree. Similarly, so how he has framed this Turing machine based on that idea is, this Turing machine halting problem is, given a Turing machine, some Turing machine from the domain of all Turing machines, and given a string to that Turing machine, will that Turing machine ever halt and say, yes, this I accept this string, or no, I don't accept it? And now it has been proven to be undecidable, which means there is no way anyone can come up with an algorithm which can say that a Turing machine will ever halt. So it is undecidable. I'll just explain you the statement, and then I'll show you the theorem which is used to prove that this problem is undecidable. It is very straightforward. I'll just go step by step. You please note down whatever I speak. Okay. Now see this. Turing machine, given the description of a Turing machine M, which means some Turing machine M is given and an input word and an input W. To the Turing machine, some input is given, does capital M when started with W, which means if I start the Turing machine with the input as W as its input, ever halts. So what does it mean? So the question is, given a Turing machine and an input to that Turing machine, will that Turing machine ever stop and say yes or no? That is the question, and it has been proved that we cannot decide it. This problem is undecidable, which means there is no algorithm as of now discovered which can say whether a Turing machine will halt or no. So how to prove it? See this, the theorem. This is very interesting theorem. You'll love it. You'll love this. See this. If the halting Turing machine were decidable, which means if the halting problem is decidable, so what does it mean? If there is an algorithm which can say whether a Turing machine halts or not. What is an algorithm? Some other Turing machine, isn't it? If there is some other Turing machine which can halt and say whether this particular Turing machine can halt or not. Okay. If it is decidable, then every recursively enumerable language would be recursive, which means if that is so, if it is decidable, then every RE is recursive. What is the main difference between recursively enumerable language and recursive languages? Membership algorithm, isn't it? Which means for recursively enumerable languages, there is no membership algorithm, but for recursive languages, there is definitely membership algorithm. What does that mean? Okay, I'll just talk about it shortly. Let's finish this theorem. if the halting Turing machine were decidable, then every recursively enumerable language would be recursive. What is that? If it is true that halting Turing machine is decidable, then the recursively enumerable languages and recursive languages both would be same. Consequently, the halting problem is undecidable. It is undecidable that because we have already proved that the recursive languages and recursive enumerable languages are different. Okay, so which means I'll just go step by step. Now we already know that the main difference between recursively enumerable languages RE and the recursive languages is this. Here, if there is a Turing machine, then that language is called recursively enumerable. Okay, and what about recursive? If there is a Turing machine which halts for every input, then it is recursive. So what is the main difference between these two statements is, given a recursive language, we never know, given a recursively enumerable language, we never know whether given a string, okay, one second, let's see this. The difference between the recursively enumerable language and recursive language is, if there is a Turing machine, then it is recursive language. If there is a Turing machine which halts, that is recursive language. So what does it say is, now here I have a Turing machine and given a string W, it will say yes, I accept it, in case if the string W belongs to the language, or it might say no sometimes, or it might go into infinite loop. That is the meaning of it. Therefore, whenever you ask the question, does W belongs to the language, that is called membership algorithm. So that is called membership question. So whenever you ask that problem of membership, does given string belongs to the language, our Turing machine might never halt. Therefore, that membership algorithm is undecidable for the recursively enumerable language, which means the main difference is here I don't have any membership algorithm, no membership algorithm. Even though I explained it once, I am again doing it because maybe I will use a different set of words and different set of statements which might help you in understanding the concept, in case if you didn't understand it earlier. That is why if there is a difficult concept, I'll try to touch it even 2-3 times so that you will understand it better. Okay. Now coming to the recursive language, given a string W, it means that there is definitely a Turing machine which will halt and say yes, this string belongs to the language, no, this string does not belong to the language. What does that mean? For this one, the membership algorithm always exists, and for this one there is no guarantee that there is a membership algorithm. Why? Because our Turing machine might go and fall in the infinite loop. So the main difference between these two languages is, one language contains membership algorithm and the other language does not contain membership algorithm. And moreover, it is very easy to observe that recursively enumerable languages are subset of recursive languages are subset of recursively enumerable languages. Why? Because the basic definition for recursively enumerable is if there is a Turing machine, and for recursive languages if there is a halting Turing machine. Therefore, by definition itself, every recursive language is recursively enumerable. Okay. Now, even there is a proof saying that there is at least one language here, which is recursively enumerable, which is not recursive. I didn't give you that proof because it is very difficult to understand and it is not required for GATE and it might be very confusing. So I didn't give you that, it is not very important. But then remember that there is already a proof saying that there is at least one language which is recursively enumerable and which is not recursive. Therefore, recursively enumerable and recursive languages both are different, or this is the actual scenario. You cannot say that all recursively enumerable languages are recursive, because there is at least one language which is recursively enumerable and which is not recursive. And now this theorem is saying that if halting a problem is decidable, then every recursively enumerable language would be recursive. But already we have proved that every recursively enumerable language is not recursive. Therefore, definitely halting problem must be undecidable. Okay, how to prove it? I'll just prove it now. Now see, the theorem proof is not yet over. I'm just revising what are all the points required to prove this theorem, and you know all these points already. In case if you don't know them, please make a note of them now. Okay, so two basics are recursively enumerable languages and recursive languages. The main difference is there exists a membership algorithm for recursive but no membership algorithm for recursively enumerable. In case if we can prove that for all recursively enumerable languages there is a membership algorithm, then we can say that recursively enumerable and recursive languages are same. But then we have already shown a proof that earlier someone has already proved that there is at least one language which is recursively enumerable which is not recursive. So now the entire concept boils down to a single point. Now you just prove that recursively enumerable equal recursive by using this statement. What is the statement? If halting problem were decidable. If you prove that, then under this assumption, then we can prove that this assumption is wrong. Okay, just see how we can prove it. Let us assume that a language L is recursively enumerable. A language L is recursively enumerable. Then definitely there exists a Turing machine M which accepts all strings which are present in the language, and it will say yes if the string is present in the language, and it will say no if the string is not present in the language. Okay, but then we don't know whether the Turing machine halts or not. Got it? So now this Turing machine M is such a way that it will say yes, I accept this string, or it will say no, I don't accept this string, or it might even fall in the infinite loop. Now let us assume that this halting problem of the Turing machine is decidable, which means there is other Turing machine or algorithm which will definitely say yes, this Turing machine halts or not. Okay, now let us say the input, see, this is sigma star and this is the language L, and now we have a Turing machine M. We have a Turing machine M. I am giving you diagrams also so that maybe you'll understand it better if you are not understanding by my words. And now if I give any string from the language to this Turing machine, it will say yes, this string belongs to the language. If I give any string W, if I give any string which is outside the language, then this Turing machine may say no sometimes, or it might fall in infinite loop. This is the problem, right? That is why there is no membership algorithm. Now if there is an algorithm, which means if the halting problem is decidable, then there would definitely be an algorithm which can say whether this Turing machine, in fact any Turing machine, can halt on a string or not, right? Then what I do is, before giving to this Turing machine any string, I'll just give that Turing machine to the algorithm. Why? Because there is an algorithm, there is one such algorithm. So I'll not directly give the string to the Turing machine. Whenever you wanted to give a string to the Turing machine, then what I do is, before giving that string to the Turing machine, I am going to give it to the algorithm, right? Now that algorithm is going to take that Turing machine M and the string W, and it is going to say yes, it halts, or no, it does not halt. In case if it says that yes, it halts, which means yes, the Turing machine M halts on W, then I really take that string and I give it to machine M. I really take that and give it to the machine M, the string W. Then what happens is, I wait for some time and it definitely halts, and it will say yes, it is there, or no, it is not there. In case if the algorithm is saying that no, the machine does not halt on W, then I will directly say that no, this string does not belong to the language, isn't it? Therefore I have an algorithm which will definitely halt and say whether a string belongs to the language or not. Therefore what happened to this language L, which is a recursively enumerable language, has got a membership algorithm. Therefore every recursively enumerable language must be recursive, which actually contradicts with our earlier proof that there is at least one language which is recursively enumerable, which is not recursive. Therefore, what can we say? Halting problem is undecidable. Got it? So I don't know if you really understood it or not, but I tried to make it very simple. Okay, what you could do is please rewind the video and watch it again. I'll just go through these steps once again. See this? Now what I mean to say is, L is a recursively enumerable language. Then there must be a Turing machine M which will take any string and it will say yes if the string belongs to the language, or it will say no if the string does not belong to the language, or sometimes it might fall in infinite loop in case if it does not belong to the language. That is the problem. Now if the decidable problem is, if the halting problem is decidable, then there must be an algorithm which will be able to take any Turing machine and any string, and it should be able to say that yes, the Turing machine halts, or no, the Turing machine does not halt. Then what is that I am trying to do is, given this Turing machine M, I'll take the word W and I'll not give the word W to M directly, the string. What I do is I'll give it to the algorithm and then I'll ask it whether it halts or not. In case if it halts, which means if it says this yes, then I am going to take this string and then give it to the machine, and then I am going to say yes or no. Got it? And now in case if it doesn't halt, then I am going to say no. Okay, if you didn't understand it, I'll just give you a metaphor so that you'll understand it. So it is like this. Now before, you don't know whether a PhD student is going to finish his PhD or not. Now if the halting problem is decidable, it means that there must be some procedure available during the selection process. When you recruit that, when you give a seat to the PhD student, then there must be some procedure available during the recruitment which says whether a student will be able to finish his PhD or not. So before taking the student, which means before giving the string to the machine, we ask that procedure, which means we ask that particular person who is able to decide whether he could finish the PhD or not. We'll ask him whether he will finish the PhD or not. If he says yes, he is capable of finishing the PhD, then only I'll take that student and then I'll give him some time, and then he either finishes or he will leave the institute. Okay, and now if there is that person is saying that no, he will never finish this PhD, he will just stay there and he will just stay in the institute and he will never leave the institute, or he never finishes the PhD, then what I do is I will not give him this seat and I will initially say no. Therefore that actual original Turing problem, that PhD problem, has been decided. But then if you have such a procedure, now we got that every recursively enumerable language is recursive, which is contradicting the proof that there is a recursively enumerable language which is not recursive, right? Therefore what we could say is our halting problem is undecidable. Okay, I don't know if you really understood it or not. At least remember one point, that halting problem for Turing machines is undecidable. Okay, let's see some of the problems to which this halting Turing machine can be converted, that halting problem can be converted, and then since we have converted this halting problem to that problem, we can say that that problem is undecidable. So these are two important problems. I mean, these are the popular problems. See, most of the problems given in GATE, or they'll give you in GATE, they'll be simple that you could easily see the correlation between the halting problem and the given problem, and we can say that they are undecidable. But some problems are not very easy, so I'll give you a list of problems which are all decidable or undecidable. You just by heart them. They are not very trivial to see, but then we can answer them. And these are the important problems for which I'll try to give you a small proof. Okay, how generally the proofs are used in order to say that a problem is undecidable. This will just give you some more insight into the problem. See this? A state entry problem is given a Turing machine and a state Q belongs to capital Q, which means there is a Turing machine and one of the state of Turing machine is small q, and a word W belongs to sigma star, which means they are giving you a Turing machine and a input. Decide whether or not the state Q is ever entered when capital M is applied to W, which means if you take a Turing machine and if you give it an input W, now the question is whether to find out whether a state capital Q is ever entered by the Turing machine or not. That is a simple question. Now we can convert the halting problem to this problem. How to convert it is, you know how a halting problem behaves. So when do you think that a Turing machine halts? Whenever it reaches any configuration which is dead, isn't it? The only way a Turing machine will halt is whenever it reaches a dead configuration. Dead configuration means it has reached a particular state and now it is looking at particular symbol, right? And now for that symbol, for that state, nothing is defined. That is called dead configuration. That is the only way a Turing machine will halt. Even if you look at the final state that we have given in Turing machines, all the final states are actually dead configurations. In the sense, once you reach the final state, whatever symbol you look at, no transition will be defined, right? Now let's convert some Turing machine, that halting problem, into this problem. So this problem is saying that given any string, whether a particular state is reached or not, can you say it, can you decide it, which means is there an algorithm to do that. Now what I will try to do is, if there would have been an algorithm for this problem, I'll say that there will be an algorithm for undecidability, that halting problem. Therefore, since there is no algorithm for this, there will be no algorithm for this. Okay, so let me not confuse you. I'll just state the problem again. Now they are saying that there is some Turing machine with some states and there is a state q. Now given a string w to this Turing machine, and if I start it in initial state, will we ever reach this state small q? That is what is given. That is what is the question, which means will our computation, will our Turing machine ever get into this state? Then what I do is, I'll take a normal Turing machine, okay, and now in this Turing machine, for every state, whenever there is a dead configuration, which means if no move is defined for that particular state, I'll just give a transition to a particular state which I nominate as q. Therefore, whenever any dead configuration is reached, I'll just end up in this state q and I'll halt. Therefore, actual halting problem is now resolved, is now reduced into the problem of halting in a state q or seeing a state q. Therefore, since the halting problem is reduced to this problem of halting problem in q, we can say that this problem is undecidable. The reason is, if this would have been decidable, then the halting problem itself would be decidable, but then we already know that it is undecidable. Therefore, the resulting problem must be undecidable. Okay, simple. Even if you didn't understand the proof, just by heart this statement. Okay, and now the next statement is, given a Turing machine M, whether or not capital M halts if started with a blank tape, which means they are saying that a Turing machine is given and nothing is given on the input, all blanks, right? Now if this Turing machine is started in this on blanks, will this Turing machine ever halts? Again, it is undecidable. In order to prove that, I'll take that halting problem again. How can I convert that halting problem to this problem is, now initially I'll start the Turing machine in the blank only, but then I'll write some few states in such a way that these states will just write the input w onto the tape, and then actually start the original Turing machine TM1. Now if the original Turing machine, which is started in blanks, if that could halt, which means our problem of that halting is decidable. Therefore, since our problem of halting is not decidable, this problem is also not decidable. Till now they didn't ask any such questions in GATE like this, but then these are important statements which have been directly derived from the halting problem. I mean, these problems are initially used to prove that these problems are undecidable because of the halting problem. Therefore, there is a chance that they might ask you, even if you didn't understand the proof, just by heart it. Okay. And next one is, almost any problem related to recursively enumerable languages is undecidable. So whatever you talk about coming to recursively enumerable problems, languages, they are all undecidable. The reason is, for recursively enumerable languages, there is no membership algorithm. Therefore, because of that, there will be lots of problems which can be not decided. We shall see what are all the problems which are undecided. Okay. Post correspondence problem. Given two sequences of n strings on some alpha, see, okay, this is a problem which is very popular. See, Using that halting problem of Turing machines, we can prove that many of the problems which are related to recursively enumerable languages are undecidable, and some of the problems which are related to recursive languages are undecidable, which I'll show you what those problems are later in a table. But then coming to this context-free grammars, we have a problem of this few problems in context-free grammars. For example, ambiguity problem, which is undecidable, right? So directly taking that halting problem and then converting it into that ambiguity problem is somewhat difficult. Therefore, what people did is they have taken this halting problem and then they converted that halting problem into post correspondence problem. Now they have taken the post correspondence problem and then converted into ambiguity problem. Using that, they have shown that even the ambiguity problem of context free languages or context free grammars is undecidable. Got it? So it is a kind of intermediate step. So anyway, if we have an undecidable problem and we keep on converting that problem to some other, that problem to some other, that problem to some other, the entire chain, whatever we get, completely everything will be undecidable. But then in order to reach a problem, sometimes it will be better if you have to go through some other problems, and post correspondence problem is invented for that reason. The reason is halting problem will be converted to post correspondence problem, and then post correspondence problem will be converted to that ambiguity problem. So finally we can say that in context free languages, ambiguity problem is undecidable. I'll just explain you what the post correspondence problem is, and then we shall see how it is related to ambiguity problem. Okay, anyway, at the end I am going to give you a table of what are all the problems which are decidable and what are all the problems which are undecidable, just by hearting that table. In case if you don't remember any of these proofs, don't worry at all. I am just going to give you a table, and using that table you can just look at the table and answer the questions. Okay, now look at, but anyway it is good to know the procedures also. Even though you could memorize it, it is always better that you know the derivation. Let's see this. Post correspondence problem is given two sequence of n strings. Some strings will be given, some strings, okay, over the same alphabet sigma. For example, capital A is a sequence of some strings w1, w2, so on wn, and capital B is a sequence of some strings v1, v2, so on vn, in such a way that both w1, w2, so on wn and v1, v2, so on vn are all from the same alphabet sigma. If you have two such strings, we say that there exists a PC solution. PC is nothing but post correspondence solution for a particular pair A comma B, which means given this A and B, if there exists a non-empty sequence of integers such that this is this. Okay, so whatever it is, I'll just take an example and explain you. Let's go to the example first, and then we shall come back and read it. See, example is, now they are saying that there is a sequence of strings capital A, W1, W2, W3, which means A consists of these three strings where sigma equal to small a comma small b, and B consists of these three strings and where sigma equal to small a and small b. Now the post correspondence solution is, you find out some sequence of integers like this 3, 2, 1, 1 in such a way that if I put W3, W2, W3, W1 by 3, 2, 1, 1, 3, 2, 1, 1, then whatever string you get, then the same string I should get for V3, V2, V3, V1. If you can find such a sequence, then it is called post correspondence solution. Then what is post correspondence problem is whether such a sequence exists or not. So it is not a very easy question to solve, isn't it? And it can be proven that it is undecidable. The reason is we can take that halting Turing machine and convert that into halting problem of Turing machine, convert it into post correspondence problem. But then the proof is going to be very difficult. So just don't get into it. Understand this one. Okay. Now theorem, this problem states that there are two sequences like this, W1, W2, W3 like this, and both of them should have a sequence, some sequence ijk in such a way that wij and vijk, both of them should be equal. So example is this. So if this is given and if this is given, find out some sequence of numbers like this in such a way that if I put all the w's in that sequence and if I put all the v's in that sequence, whatever strings you get, both of them should be same, right? If you get such a solution, that is called PC solution, and such a solution if that exists, then that is called that is yes to the problem of PC problem. PC problems ask whether such a thing exists, and PC solution means what is that if it exists, right? So how is this related to that ambiguity problem is, we can think of it as a string from a grammar, and now this string from a grammar can be derived using two ways. One way is using this and other way is using this, where you can think of all these as some variables, which means if a string can be derived in two ways from the start symbol in such a way that the final string is same but the intermediate derivation is different, then that is nothing but ambiguity, right? Therefore this problem can be converted to ambiguity problem, and so ambiguity problem is also undecidable. Already we know that terminating problem, that halting problem of Turing machine is undecidable, and therefore PC problem is undecidable. Now from PC, ambiguity problem is undecidable. Got it? That is how we could prove it. Complexity classes means there are some set of problems which are called P class and some set of problems which are called NP class. Anyway, I am going to discuss about this topic in depth when we discuss about algorithms. In algorithms, I am going to take about this topic in depth, in detail. There we are going to take an algorithm and then see how to classify P and NP. But here we are interested in taking a Turing machine, and in terms of Turing machine, I am going to define what is P and NP. But then generally people are not interested in talking about these complexity classes coming to Turing machines. So I am just going to give you definitions and leave it here, but then the detailed explanation I'll give you at the algorithms course. Anyway, before going ahead, I'll just tell you what P and NP is. I told you that a problem is decidable if there exists a polynomial time, not a polynomial time, if there exists a Turing machine or an algorithm, that's it. So, but then when I say that there is an algorithm, we are not actually interested in all the algorithms. Even though there are some algorithms, we will not be able to implement some algorithms as a program at practice. Theoretically, if there is an algorithm, it does not mean that we could apply that algorithm at practice. The reason is that algorithm, if I implement as a program, that might take lots of resources like CPU time or memory, so or number of copies of computers. So some problems, even though they have algorithms, I am not going to implement them as a program, because not even today's computer, even in future if there is a supercomputer, even that supercomputer will not be able to compute those algorithms efficiently in the sense in less time or less energy or less space. Okay, now we are interested in finding out the algorithms which can be easily implementable as a practical program. That is what the entire purpose is. Okay, so now we know that there are various types of Turing machines, and I told you that all the Turing machines are equivalent in power, either deterministic or non-deterministic or single tape or multi-tape. All the Turing machines are equivalent in power, which means the number of languages accepted by every Turing machine is same. If some Turing machine is accepting some language, we would accept the same language using some other Turing machine, unless you restrict the way tape is used. That is a completely different topic. If you do modifications enhancing the power of a Turing machine, still all the Turing machines are equal. But then some Turing machines are better compared to other Turing machines for some problems. For example, if I take a language, I already gave you this example. If I take this language a power n, b power n, if I use a single tape deterministic Turing machine, the time taken to accept a string of length n is order of n square, isn't it? If I have a single tape deterministic Turing machine, a time taken to accept a power n, b power n is order of n square. The reason is, if you have a so on n times and b so on n times, in order to match 1a with 1b, the number of cells I might have to cross is order of n, isn't it? I have to go there and again come back, isn't it? Which means 2n, which is nothing but order of n. Then how many such a's and b's have to be compared? N. Therefore it is going to be order of n square. But for the same problem, if I apply a multi-tape Turing machine, then what I could do is, I'll have a so on n, and then b so on n in one tape initially. Then I'll copy the entire input onto the second tape. Therefore, since I have multi-tapes, okay, I'm talking about a Turing machine with multi-tapes, then I can directly in one scan I can match AB, like that. Therefore here the time taken is order of n. So what I mean to say is the time taken to solve or the time taken to accept a string of length n, it may vary significantly based on the type of Turing machine, but then every Turing machine can accept the language. Therefore all the Turing machines are equivalent in power, no problem, there is no argument about that. But only I am trying to say is, depending on the type of Turing machine, some Turing machines can do some work faster and some Turing machines can do some work slower, and it is very easy to see that non-deterministic Turing machines will do any work very fast compared to deterministic Turing machines, isn't it? But then we cannot implement a non-deterministic Turing machine at practice. The reason is, non-determinism is what? At any point it is making two copies of itself. At any point it is making two copies of itself, which means if I have to implement such a program practically, your computer has to make two copies of itself, which is nothing but we need more and more resources. If the size of n increases and at every phase if you are simply replicating the copies, then what happens is, see this, a non-deterministic Turing machine at every point it is going to, at some point it is going to replicate like this, right? If at every point it is going to replicate like this, if I have to implement it as a practical algorithm, then what happens is our computer should be able to split itself into these many, or you should have overall these many machines in order to implement this program, that particular Turing machine, which means the requirement for the number of resources is going to be increased exponentially in case your algorithm is in case if your Turing machine is non-deterministic. But what is the effect we get? Our work will get done very fast. But then still even though our work will get very fast, easily done, we are not really going to use such algorithms. Got it? Therefore, even though there are algorithms, we are not going to use the algorithms which are actually equivalent to non-deterministic Turing machine. We are going to do the algorithms which are equivalent to deterministic Turing machines. Okay. Now, depending on that, what are easy to do and what are not easy to do, or what are easy to do by deterministic and not by non-deterministic, we have divided the class of problems into two types. One thing is for sure, there are some problems for which there is no halting Turing machine. We have taken it out. And in the remaining problems, again we are dividing it like this. The problems which can be solved by a deterministic Turing machine using multi-tape, and the problems which can be solved by a non-deterministic Turing machine using multi-tape. Got it? So all the problems cannot be solved. For every problem there is no Turing machine, but then among the problems for which there is Turing machine, again there are two types, deterministic Turing machine and non-deterministic Turing machine. Got it? So deterministic Turing machine problems are called P class and non-deterministic Turing machine problems are called NP class. Therefore, we are interested mainly in P class. All the practical algorithms are generally P class. If we have any NP class problem, we don't use that algorithm at practice. Instead of that, we use something called as heuristics. I am going to talk about in algorithms course. Now just see the definition here. The set of all languages that are accepted by some deterministic Turing machine in polynomial time. What is polynomial time? Order of n power k. This k can be any number, that we don't worry about it. So the set of all languages that are accepted by some deterministic Turing machine in polynomial time is called P class. So you take all the problems which can be accepted by a deterministic Turing machine, and remember that this deterministic Turing machine can have any number of tapes. There is no restriction on that. Our practical computer can use any number of tapes, okay, which means any number of data structures, right? Therefore, such problems are called order of n power k. So we generally take such an algorithm and we generally implement it as a program in the computer. NP class is the set of all languages accepted by non-deterministic Turing machine polynomial time is NP. So if you take all the Turing machines, which are the languages which are accepted by non-deterministic Turing machine. Non-determinism means they can multiply themselves, right? They can make copies of themselves. Non-deterministic Turing machine, and here also remember that either this or this, there can be multiple tapes. In polynomial time means order of n power k is NP. It is very clear to see that if a problem is solved by a deterministic Turing machine in polynomial time, definitely it could be solved by a non-deterministic Turing machine in polynomial time. Therefore, it is very easy to see that P is here and NP is here, which means for every problem where there is a deterministic Turing machine, for every language where there is a deterministic Turing machine, for that there will be a non-deterministic Turing machine as well, isn't it? Therefore, it is very easy to see, but then we don't know whether P equal to NP or not. Till now, one question is still open, which means is P equal to NP? No one is able to prove it, but then we are just started believing that P might not be able, P is not equal to NP, but then we are not sure it. In future, if someone says that, or if in future if someone has proven that, okay, that one we shall discuss in algorithms. Just now leave it. Okay, just understand these two definitions. Okay, now the main question is P equal to NP? So no one has ever given that solution. So when will P be equal to NP? P will be equal to NP if whatever problems were solved by non-deterministic Turing machines in polynomial time, if they could be solved by a deterministic Turing machine in polynomial time, then we can say that P equal to NP. But now, till now, no one has ever given an algorithm which will take a non-deterministic Turing machine and convert it into a deterministic Turing machine in such a way that the language accepted will be order of n. See, for every it is all okay. One more thing, I have been using problem and language interchangeably, so don't worry about it. Both are same. Either I say a problem or a language, both are same. So if I say language, it is nothing but set of strings. When I say problem, it is nothing but set of instances. Every instance of the problem can be compared to a string in the language. That is first thing. And next thing is, now whenever I say that for every deterministic non-deterministic Turing machine, definitely there will be a deterministic Turing machine. But the problem is, once we convert that non-deterministic Turing machine to a deterministic Turing machine, the time taken by the deterministic Turing machine to solve the same problem will be exponential, not polynomial. Which means, see this, I told you that all the Turing machines are equivalent. If a problem or a language is accepted by a non-deterministic Turing machine, there will definitely be a deterministic Turing machine which will accept the same language. Okay, but then the problem is, when you convert a non-deterministic Turing machine which is solving a problem in order of n power k, a polynomial time, into a deterministic Turing machine, we can solve it, we can convert it. There will definitely be a deterministic Turing machine which solves the same problem, but the problem is the time complexity required is becoming exponential, which means by taking the same time, both the machines are not able to solve the given problem in polynomial time. When I convert the non-deterministic machine to deterministic machine, it is actually taking order of 2 power n time. I'll just give you a small example of this thing. I'll just give you a small example explaining you this concept of converting a non-deterministic Turing machine to Turing machine, and then telling you what is happening here. But then this should not be taken as any valid proof for the for saying P is equal to NP or P not equal to NP. The small problem is this. See this, if I have a Boolean expression A or B or C. Okay, now what are the values? The A and B and C, A, B, C are Boolean variables. Boolean variables means they can take a value of 0 or 1. Okay, now what are the assignments of, or tell me at least one assignment of 0 and 1 to A, B, C in such a way that this expression becomes true. True means 1. If that is the question, then the problem is our deterministic Turing machine will have to go through all possible values. So how many possible values will be there? If you write, if I have n variables like this, and if every variable is having 2 chances, true or false, then how many possibilities will be there? 2 power n. Then our deterministic Turing machine is going to take 2 power order of 2 power n time. The reason is it has to take every possibility and check it. But then on the other hand, what our non-deterministic Turing machine will do is, it will simply make a copy of itself. How many copies? 0 to 2 power n copies. And then like this, for A, our non-deterministic Turing machine will be starting at here, and then for A, it will one copy will assume A equal to 0 and other copy will assume A equal to 1. Depending on that, we got two Turing machines. And again at B, one copy will assume B equal to 0, B equal to 1, B equal to 0, B equal to 1, and again here C equal to 0, C equal to 1. Therefore, we are going to get nearly all 8 Turing machines for every combination, and at least one Turing machine is going to say yes. Got it? Therefore, in just order of n time, we are able to solve the problem using the non-deterministic Turing machine. But then using a deterministic Turing machine, it is going to take order of 2 power n. The reason is we have 2 power n rows or 8 rows, and every row has to be examined by only a single instance of machine. But here the work is being done parallelly, therefore we are able to do this in polynomial time, here exponential time. So for every problem which can be solved by non-deterministic Turing machine, there will be a deterministic Turing machine, but the time taken by the non-deterministic Turing machine, if it is linear or polynomial, the time taken by the deterministic Turing machine for the same problem might sometimes go to order of 2 power n. Got it? But then there is no valid proof, which means no one has ever proven that there is no way we could find out a deterministic Turing machine which can solve a problem in polynomial time like non-deterministic Turing machine, nor no one has ever given a proof saying that there is at least one problem for which there is non-deterministic Turing machine but for which there is no deterministic Turing machine. As of now, P equal to NP or not, it is unknown. Got it? Got it? So we are going to look at this P and NP class in detail again at later in algorithms. There I am going to talk about some other things like what is NP hard, what is NP complete, and then I am going to compare everything. Okay, so this is all about Turing machines, and coming to Turing machine terminology, what is the complexity classes. Fine. See, the problem of decidability or undecidability for any given problem is I told you how to do it from the halting problem, but then in GATE exam, if they give you such a question, it is going to be difficult to answer it. Therefore, what I did is, for the sake of your information, I've taken all the problems and I've formed a table like this. Now these problems I have taken from the exercise questions of various textbooks, and proving them is not required for GATE, and moreover it is going to be tedious and time taking procedure. So I suggest that you just by heart this table, just one table, I mean 2 tables are there, you just by heart it, and I'll just tell you what are the problems, and I'll just give you a hint about how to by heart it. You need not by heart the entire table, only the most important things I'll just tell you. Okay, see this, the problems I'll just read out for you. Just zoom in this area. Okay, now see this. The problem is, does W belong to L, which is nothing but given a language, some representation of the language like finite automata or Turing machine, some representation, and then given a language, given a string W, does it belong to the language or does it not belong to the language? It is nothing but membership problem. And next one is L equal to 5, which means is the language empty? It is called emptiness problem. And next one is L equal to sigma star. Sigma star means does L contain everything in the universe? Sigma star is the universal language, isn't it? So if L equal to sigma star means does L contain all possible strings? That is called completeness problem. Other name of it is completeness problem. And now L equal to L2, L1 equal to L2, which means given two languages of same type, either regular or context free, are they both equal or not? Equality in the sense, are they both containing same strings or are they going to contain different strings? Is L1 subset of L2? So L1 subset of L2 means given a language L1 is the other and language L2, both are of same type. Is one language a subset of other language? Subset, you know that, right? It is also called as subset problem. So remember one thing, whenever I say L1 L2 here, L1 L2 here, L1 L2 here, I am assuming that both L1 L2, this problem is discussed given when both L1 and L2 are of same type. Either they could be regular or context free or CSL, whatever it is, both are of same type. Okay. And next one is L finite or not? It is also called as finiteness problem. Finiteness. Next one is complement of L a language of same type or not? Which means if I take a language L and if I complement it, is its complement the same type or not? is intersection of two languages same type. If I take L1 and L2 and if I apply intersection, is the resulting language same type? For example, if I take regular and intersect it, then is the resulting language also regular or is it not regular? Okay. Next one is L regular language, which means given some representation like a Turing machine, is that language regular or really recursively enumerable? Or given a context free grammar, is that language regular or context free, like that? So even though a language is regular, you know that still we can give a Turing machine for that. Therefore, given a Turing machine, you should be able to say whether it is regular or not. So all these are the problems. Now when we ask such a problem for one particular type of language, whether there exists an algorithm to answer it or not, that is what I want to do. Okay, so what the question is, these are all problems. Now when this problem is applied to some particular type of languages, now the question is, for that kind of languages, is that problem decidable or not, which means for that problem will there be a algorithm or not. Okay, so just you can just copy it all. I'll just tell you how to remember it. You can just take this, pause it, show this all in one frame. Is it possible? So you can pause it and just copy down the, okay, so you can just copy it down, and now I'll tell you how to memorize it. See, whenever you find out that something is undecidable for a smaller type of language, if for a smaller type of language it is undecidable, obviously for the other languages, bigger languages, it is undecidable. Therefore remember it, whenever you start undecidable somewhere, the entire row should contain undecidable from that point on. So that is a hint. Okay, and what are the main important languages that you should remember is, one thing is for sure, for regular languages everything is decidable, that is for sure, and for recursively enumerable languages nothing is decidable, all these problems are undecidable. These two things you need not remember at all. So what is it? For regular languages everything is decidable, for recursively enumerable languages nothing is decidable, and for recursive languages only membership is decidable and nothing else is decidable, which means only this is decidable and nothing else is decidable. Oh, there is one more, is complement. Yes, complement is it is also decidable. Okay, so apart from complement and the membership, nothing is decidable for recursive languages. For recursive enumerable nothing is decidable, and for this only two exceptions. And now it is very simple. See, I am saying that for regular everything is decidable, for recursive enumerable everything is decidable, and for recursive language only two things are decidable, and apart from that everything is undecidable. And you need not worry about deterministic context free languages and CSL, generally they will not be asked, and the one important one is CFL. So you have to by heart only CFL. So CFL is important, maybe it 3 times there it is decidable and all the others are undecidable. You just remember what are the problems that are decidable, then obviously the remaining are undecidable, right? So questions will be 1 regular, 2 recursively enumerable, 3rd recursive, and 4th one is CFL. So CFL only 3 are decidable. Okay, remember what are decidable and the remaining are undecidable. So these 4 classes are important: regular, CFL, recursively enumerable, and recursive. Okay, so you can by heart this table. You are definitely going to get one question from this. Definitely one question next year. I mean the coming gate. Okay. Now let's see the properties of context free languages. In context free language, see, if a language is context free, definitely there will be a context free grammar. Let us say 2 context free languages are given, L1 and L2, then definitely there will be context free grammars, right? Context free grammar, let me say CFG1 and context free grammar 2, and each context free grammar is going to start with a start symbol, isn't it? So let us say the start symbol for context free grammar G1 is S1. S1 derives, it is going to start like this, and the context free grammar this one is going to start with S2. S2 derives, it is going to start like that. Now if I want to combine these 2 languages, which means if I want to apply the union, what does that mean? The resulting language should have all these strings, or should have all these strings of L1 as well as L2. Therefore what I do is, I'll write a new grammar, S derives S1 or S2. So if you want to derive any string which is present in the language L1, you start with S1, which means from S you start with S1, and S1 is going to generate this string which is present in the language L1, right? Or if you want a string which is present in language L2, then from S you start with S2, right? Then you are going to generate a string which is going to be present in the language L2. Got it? So if whatever you want to generate, you could choose appropriate start symbol, and since this is the resulting grammar is also a context free grammar, the resulting language L1 union L2 is context free. How did we do this? Find out the context free grammars and you just apply the slash and put a new symbol, isn't it? It is straightforward. And next one is, if L1 is a context free grammar and L2 is a context free grammar, L1 concatenated with L2 is again a context free grammar, context free language. So if two context free languages are given, the concatenation is also a context free, which means context free languages are closed under concatenation. How can we prove it? You start a new start symbol with S1 dot S2. If this one is having a context free grammar which is starting with the start symbol S1, and if L2 is having a context free grammar which is starting with the starting symbol S2, then you write a new grammar which is going to start with a start symbol S and which is having S1 followed by S2, and all the remaining productions are same. For all the S1 and S2 you add all the productions of S, language L1 and L2. Here also you add all the productions of language L1 and L2, right? It is fine. And now after concatenation, let us say closure. Closure means if you have L1 as a context free grammar, then L1 star should, what can you say about the L1 star? It turns out that even L1 star is context free, which means context free languages are closed under closure operation. So how can we prove it? If L1 is a context free language, then there will be a context free grammar which is starting with some symbol S1, right? Now what we want to do is, we want to repeat the number of strings in L1 as many times as possible. Then I am going to introduce a new grammar which is having S1s or epsilon. So what is the meaning of it? If you want to generate epsilon, it will generate it. If you want to generate one string from S1, you can take this one and then S will go to epsilon. If you want to generate two strings from S1 concatenate with S1, then what you do is S will generate S1 concatenated with S, and again S will generate S1 concatenate with S, and wherever you wanted to stop, you can stop it. Now if you want two strings, yes, you got two strings. If you want three strings, you extend it. Therefore by using this rule, you can generate closure of the language. Therefore context free languages are even closed under closure. They are closed under union, concatenation, as well as they are closed under clean closure. Got it? Context free languages are not closed under intersection and complementation. We shall prove it with a counter example. See, now I am saying that context free languages are not closed. Till now we have seen the closure properties. Now I am saying that they are not closed under intersection. Intersection means if I take two context free languages L1 and L2, and if I do the intersection, then the resulting language might not be context free, which means the resulting language need not be context free all the time. It might be some other language also. So how can we prove this? If you have to prove it, find at least take two context free languages in such a way that at least one example should give us a language which is not context free. So let's see which examples will be better. See, this is called proof by counter example, which means I am assuming that context free languages are closed under intersection. Then I'll find out an example which will show that actually intersection of two context free languages, we are not getting the context free. But then there will be other examples where when you apply the intersection of context free languages, then the resulting might be context free language, but it doesn't prove that they are closed, isn't it? In order to prove that they are not closed, you find out one example which says that they are not closed. But then if you find an example which says that they are closed, it doesn't mean that they are closed. Okay, it is like this. See, if you want to prove that some person is bad, you can find out one bad thing which is done by that person and you can say that he is bad. But then if you want to prove that a person is good, one good thing is not going to be enough. It has to be his entire lifetime in which there is no bad thing, isn't it? Similarly here, if you have to say that the context free languages are closed, you have to take every possible languages, all possible languages, and apply the intersection and find that all the languages or the resulting languages when you apply the intersection are actually context free. Got it? But then if you can find out at least one example in which the resulting intersection is not context free, that is enough to say that the languages are not closed under intersection. Now just see this. Let us say you already have seen this example. L1 equal to a power n, b power n, c power m such that n comma m greater than or equal to 0. Do you remember this? We have already seen this example, isn't it? So this is definitely context free. How you generate a and b together using a variable, and then you generate c separately using a variable, and then you concatenate them. This is context free. We did both the context free languages, the context free grammar as well as PDA for this example. And let us say L2 equal to a power m, b power n, c power n such that n comma m greater than or equal to 0. So what does language L1 say? That the number of a's and b's are equal. And what does language L2 say? That the number of b's and c's are equal. And when I apply L1 intersection L2, see, it is most confusing. Many people get confused here. Okay, so think about it. So what are these strings that we get in L1 intersection L2? I am saying that the strings which will be present in the intersection will be a power n, b power n, c power n. It is very easy to see it, but then I don't know why people get confused in this. See, if a's and b's are equal in L1 and b's and c's are equal in L2, if the string has to be present in both L1 and L2, obviously all of them have to be equal. You please work it out on math. Okay, what you could do is take some examples and work it out. See, if L1 is containing all these strings in which a's and b's are equal, and L2 is containing all these strings in which b's and c's are equal, then definitely L1 intersection L2 will contain the strings in which a, b and c are equal. Otherwise they will not be present. See, a string is present in here, which means a's and b's are equal, and a string is present here, which means cc. A string which is present here is also present in L1, which means a's and b's are equal. A string which is present here is also present in L2, which means b's and c's are equal. Therefore, applying these two rules, a, b and c's are equal, isn't it? Therefore, I got this one. I don't know where people get confused. Whenever I teach this in the classroom, they'll generally have this doubt. How did you write this? Maybe for me it is just easy. You just think about it. You please work on it. And a and b, see, this language is definitely not context free. We have seen it. There is no context free grammar for this one, or there is no PDA for this one. We have already seen it, right? And it is actually context sensitive language. We have seen the context sensitive grammar also. You please refer to the context sensitive grammars concept. Okay. So anyway, this is not context free. Therefore, what can we say? The languages, context free languages are not closed under intersection. And we can even extend it and say that context free languages are not closed under complementation also. So how can we prove it is? Using this proof, now we have already shown a proof that context free languages are not closed under intersection, isn't it? Now L1 intersection L2 can be written as L1 complement union L2 complement whole complement, right? Now let's say, just for the sake of assumption, so it is called proof by contradiction, which means I am going to assume something and again I am going to prove that my assumption is wrong. I am assuming that context free languages are closed under complementation. Then what happens? See, if they are closed under complementation, if L1 is a context free grammar, context free language, L1 complement should be context free. If L2 is a context free language, then L2 complement should be context free, right? And we already know that union of two context free languages is context free. Therefore, this entire thing must be context free, and I am assuming that the complement of a context free is context free. Therefore, this entire thing should be context free, which means this one is now turning out to be context free. So if I assume that L1 complement is context free, then what is that we are getting? We are getting that L1 intersection L2 is also context free, but then it is already shown that L1 intersection L2 is not context free. Therefore, our assumption must be wrong. What is our assumption? That the complementation of a context free language is context free. So, it is not true. Therefore, what can we say? Context free languages are not closed under complementation. So, it is very important to remember context free languages are not closed under intersection, as well as they are not closed under complementation. It is a popular question. They have asked it many times in GATE, and again there is a chance that you might get it. Okay. In context free languages, membership problem is decidable. What is membership problem is, given a string, does it belong to L or not, which means if L is a context free language, a string W, does it belong to L or not? That is what is membership problem. And we have already seen that there is CYK algorithm, which is a membership algorithm, and therefore you can say that this is decidable since it is having a algorithm, right? And decidability means having an algorithm, right? And now emptiness problem. Emptiness problem is, given a language, some representation of a context free language, is the language empty, which means does it is L equal to 5 or does it accept anything? So in order to know that, what you could do is take the context free grammar, because the language is context free. Whatever the representation is given, you take the context free grammar and then you apply the simplification algorithm, which means you try to simplify the context free grammar by eliminating the useless symbols. We have already seen examples on that. Now in the resulting grammar, in case if any of the in the resulting grammar, if you find out that the start symbol S is useless, if the starting symbol S itself is useless, it means that we cannot generate anything, isn't it? So if S is useless means there is no way we can, what is the useless symbol? There is no way we can generate anything from that symbol, isn't it? Therefore, if S itself is found out to be useless, then we can say that the grammar is useless, or the language is empty. So what is the algorithm? Take the context free grammar and then apply simplification algorithm. In the resulting one, if S is useless, you can say that it is completely useless. It is completely empty. That is, therefore, emptiness problem is decidable because we have an algorithm. What about the finiteness problem? You can do the same thing. Take the context free grammar and then you apply the simplification algorithm on that, which means you delete the these useless symbols, and then in the resulting grammar you try to draw the dependency graph, which means if you have something like this, after simplification, let us say you got this, and then A derives small a c, and then C derives small a, and then A derives small a, which means here it is small a, here it is small b, and capital B derives small a, something like this. Then let us assume that this is the simplified grammar you got. Then you try to draw the dependency graph. Dependency graph means you take every vertex as the node and then see if there is a, like this, S is a node, A is a node, B is a node, and C is a node, like this. And now S derives A, B is given. What does it mean? From S you have to give like this. The reason is S is deriving A and B, and then A derives C is given, therefore A to C, which means like this. Whenever there is a production from generating any variable from one variable, you just use the directed edge from that. And again C is deriving A, which means like this. Now in the dependency graph, if there is any cycle, we can say that the language is infinite. In the dependency graph, if there is no cycle, we can say that the language is finite. For example, if the grammar, simplified grammar is like this, A derives, S derives AB, and capital A derives small a, and capital B derives small b. In case if this is the grammar you have, then S will have A and B with no cycle. If there is no cycle, then it is finite. If there is cycle, then it is infinite. Got it? That is how we could do it. Look at these properties of regular languages. So there is something called as closureness or closure, or let us say there is a term called as closed under some operation. What I mean by closed under operation is, if I take set of all natural numbers, let us say this is set of all natural numbers, then set of all natural numbers is closed under addition. So what I mean by this is, if I take any two natural numbers from this set of all natural numbers and if I apply the addition on those two natural numbers, then the resulting is also a natural number, that is called closed under addition. So this set natural numbers, the set of all natural numbers is closed under addition is, if I take any two natural numbers or any two elements from this set and if I apply this operation, if the resulting whatever I get as the result also belongs to the same set, which means if I add two natural numbers, if the result is also going to be a natural number, then I can say that set of all natural numbers are closed under addition. Similarly, whenever I take regular languages, set of all regular languages, if this is the set of all regular languages and if I apply some property on the set of all regular languages, if I take two regular languages and if I apply some property on that, some operation, and if the resulting language whatever I get, it also belongs to the set of regular languages, which means after taking two regular languages and applying a operation, if the resulting language is also regular, then that operation is said to be closed under regular sets, or regular languages are said to be closed under that operation. Terminology is regular languages will be closed under some operation, not operation will be closed under regular languages. Okay, so when can we say that regular languages are closed under some operation? You take two regular languages and you apply a property on that. If the resulting is also resulting also belongs to the same set, then we can say that set of all regular languages are closed under that particular operation. And now let's see how to prove it, which means let's see some of the properties and I'll show you how to prove them. See, for regular languages I am going to prove all the properties, but for the other languages, context free, context free I'll prove some of them, and for the other languages like recursive enumerable and recursive context sensitive, I'll just give you a table. You refer to the table, that table is good enough. Okay, now just watch it. If L1 union L2, see, what can you say about the regular languages under union, L1 union L2? So if L1 is a regular language and L2 is a regular language, then definitely L1 union L2 will also be regular language, which means set of all regular languages are closed under union. How can I prove it? If it is a regular language, there will be a regular expression, let us say R1, and if this is a regular language, there will be a regular expression R2. Then union of these two languages is nothing but putting a plus in the middle, isn't it? And then intersection, okay, intersection we shall prove it later. And let's talk about concatenation. If L1 is a regular language and L2 is a regular language, then L1 concatenated with L2 is also regular. How can I prove it? Same way, if you take the regular expression R1 for L1 and you take the regular expression R2 for L2 and you just apply the concatenation, then whatever language we get or whatever expression we get is again a regular expression. So since it is a regular expression, the language which resulted must be regular, isn't it? Then what about closure, clean closure? Same thing you can do. If L1 is a regular language, then you can find out a R1 which is a regular expression for this language. Then L star, clean closure of the language is nothing but the clean closure of the regular expression, and the resulting regular expression is also a regular expression. The resulting expression is also a regular expression. Therefore, you can say that the resulting language is regular. And now let's prove that L1 complement is a regular expression. L1 complement is regular. So if L1 is regular, then L1 complement is nothing but sigma star minus L1, isn't it? Which means if this is the set of all strings and if this is L1, then whatever is outside L1 is L1 complement, isn't it? Now what I want to prove is, if I take the complement of a language which is regular, then the resulting language is also regular. In order to prove this, it is already given that L1 is regular. Therefore, there will be a DFA for that, right? And now we complement the DFA. Then what we get? again we get one more DFA which will be accepting the complement of the language, given language, which is L1 complement. Since we got a DFA for the language, therefore L1 complement is also regular. How to complement a DFA? I have already given you examples, you please check on that. So complementing a DFA is nothing but construct the DFA and then make the final states non-final and non-final states final, which means only thing that changes here is in the final states, look at this. So if you have Q, sigma, delta, Q naught and capital F representing a DFA, then complement of the DFA will be Q, sigma, delta, Q naught, and the final states will be just the states which were non-final before. What are the states which were non-final before? Q minus F. This is complementation. If this is the DFA for the given language, we got one more DFA which accepts the complement of the language. Therefore, we can say that complement is again closed, which means complement is also a regular language. Almost every property about regular languages is closed. So one good thing about regular languages is everything is closed, everything is decidable, everything is simple. Okay, and now let's prove that intersection is closed. So intersection proof is actually beautiful because it is an example of a constructive proof. Constructive proof means we will prove something else before and then based on that we derive this. That is called constructive proof. So there are various types of proofs. You can prove by contradiction, you can prove by induction, you can prove by construction. Construction means we build some other proofs and then we show that this is true. So in order to prove that L1 intersection L2 is regular, I would rewrite this L1 intersection L2 like this: L1 complement union L2 complement whole complement. If I write this, both are same, isn't it? So we have already shown that L1 complement is regular, L2 complement is regular, and union of two regular languages is again regular. Therefore this entire thing is regular, and again a complementation of the regular language is regular. Therefore this is regular. Okay, understand this. L1 is already given as regular, L2 is already given as regular. So complementation of two regular languages are already regular. Therefore this one is regular and this one is regular. And then we are applying union to two regular languages. Therefore the resulting is regular. And then we are simply complementing it. And so the complementation is also closed. Therefore the resulting is regular. So finally the intersection of two regular languages is always regular. So what can we say? Regular languages are closed under intersection. Okay. Look at these two properties. Regular languages are closed under difference, which means if I have one language L1 which is regular and if I write L1 minus L2, I am saying that the resulting language is also regular. How can we prove this is? It directly comes from the proof of intersection. Already we know that intersection is regular, right? So we can write it like this. Difference is nothing but L1. See, I am talking about the first property, not the second one. I am talking about the first one, then I will talk about the second one. Second one is regular languages are closed under reversal. First one is regular languages are closed under difference. So L1 minus L2, I can write it as L1 intersection L2 complement. These two are same. Therefore, already we know that this complementation is closed, which means this is regular. Why? Because L2 is regular. Therefore, L2 complement is regular. And two regular languages are now applied intersection. Therefore, the resulting is regular. So difference is always closed under regular languages are always closed under difference. This is the proof. And what about this reversal? I told you how to reverse a language of a DFA, or I told you how to reverse a finite automata. That method was applied both for DFA as well as NFA. Do you remember that reversal? How to do the reversal is, you please refer to that examples and I'll just tell you how. Make the final state as initial state and initial state as final state, and you just reverse all the transitions. That is nothing but reversing a finite automata. Now I am saying that regular languages are closed under reversal. So what does it mean? You take the DFA first. or NFA, anything, DFA or NFA, both will do, even epsilon NFA will also do. And now you apply the reversal of the DFA, then again we get a finite automata which will be either DFA or NFA. Okay, and now you can find out that the resulting finite automata, if this one is accepting L, the resulting finite automata will accept L power or reversal. I hope that you remember what reversal of a language is. String reversal is if you take a string and if you reverse it, that is string reversal. Language reversal is if you take every language, every string in the language, and if you reverse it, that is language reversal. So all the regular languages are closed under reversal. You take any regular language and you apply the reversal, you finally get a regular language. That is why they are closed. Okay, these two properties are closed. In fact, every property is closed for regular languages. Now let's look at this. The function h from sigma to tau star is called homomorphism. So what it means is, if you have an alphabet, which means input symbols, and in every symbol, for every symbol in the input, if you substitute a string from some other alphabet, then it is called homomorphism. And it is known that it can be proven that regular languages are closed under homomorphism. So before going ahead and seeing the proof, I'll just give you an example and explain you what homomorphism is. Let us say we have a input alphabet A comma B. Then if it is defined, a h is defined, that a homomorphism is defined in such a way that for every small a in your input, if you substitute a string from some other input, let us say some other input is 0, 1, 2, some other alphabet is 0, 1, 2, and now for every symbol here, if you substitute a string from that particular some other alphabet, then it is called homomorphism. So once you define this homomorphism, then we call it as homomorphic image of a language or a string. So what we do is generally initially sigma is defined, which is your alphabet, and then tau is defined, which is some other alphabet, and now this mapping is defined for every symbol. For every symbol in your alphabet, there has to be some string. Once this mapping is defined, then for a given string from this alphabet or for some language, we are going to find out the homomorphic image. So what is homomorphic image of a string? Let us say a string is ABA. What is homomorphic image of the string ABA? According to this homomorphism is, in place of A you have to substitute 0, 1, and in place of B you have to substitute 1, 1, 2, and in place of A again you have to substitute 0, 1, isn't it? So it is nothing but homomorphic image of a string, right? And then what is the homomorphic image of a language is, you take the language and in every string you find out the homomorphic image, then it is nothing but the homomorphic image of a language. So what is the homomorphic image of a language is, I'll just take an example of a language. Let us say language A is, some language L1 is A star B. It is a regular language, isn't it? And now the homomorphic image of this language is, in this language take every string and in place of every string you put the homomorphic substitution, which means whatever is the homomorphism is substituted there. But then taking every string and doing it is as good as taking the regular expression, and in the regular expression you do it. So in the regular expression we have A star B, isn't it? So take this regular expression and do it. In place of A, what should you substitute? 0, 1, 0, 1 star, and in place of B, what should you substitute? 1, 1, 2, right? Therefore the homomorphic image of this language is this one. So now I'm saying that regular languages are closed under homomorphic image. It is a proof also. The reason is, we have taken if the language is regular, there will be a regular expression. Now take the regular expression, and in the regular expression for every input symbol you substitute the homomorphic image, then you are going to get one more regular expression, isn't it? It is a regular expression. Therefore the resulting language is again regular. Therefore regular languages are closed under homomorphism. Okay. If you apply the reverse of the homomorphism, then it is called inverse homomorphism. The same way where we are taking one alphabet and taking it to some other strings of other alphabet, we could take the strings of other alphabet and bring them back to the original alphabet. by using inverse homomorphism. Okay. So inverse homomorphism is simply, not to understand it, you can understand it as reverse of the homomorphism, which means, like, if homomorphism is from here to here, inverse will be from here to here. So don't worry about the definition, you might not understand it. Let's take an example, then you'll understand it better. So anyway, definition goes like this: inverse of a homomorphic image of a language L is H inverse of L is X in case H of X is in L, which means if the homomorphic image of a string is in language L, then that string will be in H of L. And homomorphic image of a language can be found out, and homomorphic image of a string can be found out, isn't it? Similarly, inverse homomorphic image of a string can be found out, as well as inverse homomorphic image of a language can be found out. Let's take an example. Let sigma equal to 0, 1, 2. So one alphabet is defined as 0, 1, 2, and delta equal to a comma b. Other alphabet is defined as a comma b, and we are given a homomorphic image from sigma to delta, from sigma to this delta star, which means in place of 0 a is substituted, in place of 1 ab is substituted, in place of 2 ba is substituted. Let L1 equal to ab aba, which means we are given only one string, L1 equal to ab aba, one string, and now they are asking us to find out the inverse homomorphic image of L1. So how to find out is, whenever they ask you about the inverse homomorphism, take that string and see using what combinations of the original alphabet we could form the resulting string, which means if this is the string required, what are the combinations of the original alphabet in order to form this string. So you can see that I could have substituted, if you have AB, ABA like this, AB, ABA, I could have substituted in place of AB 1, which means 1, and in place of AB 1, and in place of A 0. Therefore, what did I get? 1, 1, 0, isn't it? And other inverse homomorphic image is AB, ABA means in place of A, I could have substituted 0, and in case of BA2, BA2, which means 0, 2, 2. The same string can be generated with different strings. That is why I am getting more than one answer here. It is completely valid, perfectly valid. So, and one more possibility is, if I have AB, ABA, I could have substituted in place of this 1, and in place of this 0, and in place of this 2. Therefore, other homomorphic image is 1, 0, 2. Therefore, for a given string, I have got 3 inverse homomorphic images. Now, if we again try to convert this to the actual one by applying the homomorphism, but you will get only one string. Okay, so just remember that if I apply the reverse again, I get only one string. Okay, now watch the other one. Let us say we have x equal to L2 equal to A, BA star B. This is the language given, and now I want to find out the inverse homomorphism of that language. It is always better to convert the language into strings or enumerate the language, and then you go on back substituting it. That is the best way possible. So if this is the string given, now I am just writing that string in terms of, if this is the regular expression, I am just writing it in terms of all the strings. Then these are all the strings I got. Then inverse homomorphic image of the language is, see this, for A I get only one combination, which is 0. For ABA I get two combinations. AB can be 1 and A can be 0, or A can be 0 and BA can be 2. Therefore, for the second one I got two combinations, 1, 0 and 0, 2. For the third one, ABA, BA, it is same as that string, we have already seen it, ABA, BA, for which I got all this, isn't it? Maybe you could extend it further and you could even get more. What will be next string? A, BA, 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 isn't it? That is the next string. For that, what do I get? One possibility is 1, 1 in place of AB, AB, and then 1 and then 0, which means 1, 1, 1, 0. And other possibility is AB, AB, ABA. Other possibility is, in place of this I could go for 0, and in place of this 2, 2, 2. And other possibility is, if I have this AB, 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 A. Other possibility is, in place of this I could go with 1. AB means in place of 0, small a I could go with 0, and in case of BA I could go with 2, and BA I could go with 2. Other possibility is, in place of AB I could go with 1, in place of AB I could go with 1, and in case of small a I could go with 0, and in case of BA I could go with 2. Therefore these two are possible. Anyway, what are all the possibilities is, for this language, one is 1 star followed by 0, it is an answer, or you could have represented as 0 followed by 2 star. See, 1 star followed by 0, it will generate everything, or 0 followed by 2 star, it will generate everything, or you could have even represented as 1 star, 0, 2 star. In fact, you could write all these three as an answer, or if you could observe this, the third language itself, this will properly contain these two. Therefore, you could even write this only this one as the answer. It is also valid. So, if you want to simplify the answer, this one is the final answer, or even if you write entire three things as the answer, no problem. The reason is, finally everything mean the same. But then if you look at this, in place of this star, if you put a 0, it will boil down to 0, 2 star. In place of this star, if you put a 0, it will boil down to 1 star 0. Therefore, you could go with anything, not an issue. Okay, fine. So that is how you can find out the inverse homomorphic image. Okay. Now I want to illustrate one important property of inverse homomorphism using an example. Okay, take this example. See this one. Let sigma equal to 0, 1 and delta equal to a, b. So one alphabet is 0, 1 and other alphabet is a, b, and they are defining a homomorphic function like this. So h of 0 equal to a and h of 1 equal to aba. So which means in place of 0 they are substituting aa, and in place of 1 they are substituting aba. So then they are asking, if this is the language given, so this is the homomorphism defined, which is in place of 0 they are putting aa, and in place of this they are putting this. And for some language is already formed over delta. Now we want to find out the inverse homomorphic image of that language. Now that language is L equal to AB plus BA star followed by A. So I want to enumerate the language first. So I have written all the strings. If this is the language given, these are all the strings. Now I want to find out the inverse homomorphic image of L. Then I'll take every string and I'll examine if I could write it in terms of 0 and 1, so that I could put it in the inverse homomorphism of the language. Now I'll take this string A. Now if I take this string A, there is no way I could either write it in terms of 0 or 1, because the string lengths are at least 2 and 3. So A is not possible in inverse homomorphic image. And what about this ABA? Yes, it is possible and it is 1. What about BAA? You cannot write either, one thing, it is not just enough that you encode a part of it in terms of zeros and ones. You should do it completely. Okay, so BAA cannot be completely written in terms of ones and zeros, so there is no inverse homomorphic image of this string. And what about this one, ABA? So maybe you could write ABA here, but then the remaining string BA cannot be derived by anything, and AA is completely useless in this case. The reason is no two A's are actually together, therefore it is not possible to write it in the inverse. Then what about this one? AA could be written as this 0, but then ABB cannot be written as 1. Therefore inverse homomorphic image of this string is also not possible. So if you look at this entire language, only one string inverse homomorphic image is possible. Therefore inverse homomorphism of this language is only 1. So see this, inverse homomorphic image of this language is only 1. Now if you apply the homomorphism for this one, which means h of h inverse of L, then we get ABA. So if I apply the homomorphism for the inverse homomorphism applied, contrary to the belief that we should get L, we got only ABA, which is not equal to L. Therefore even though a language is given, and if you first apply inverse homomorphism, we are going to lose some of these strings, and again if you apply the homomorphism back, we are not going to, we might not get the entire language. Sometimes we might get, sometimes we might not get, but actually this subset is the true relation. It is not equal to, it is subset, and it is not proper subset. It might, which means it might not always be the case that we lose some of these strings. In this example we lost some of these strings, but then in some other example we might get all these strings. Okay, so anyway, what I mean to say is, in case if you try to apply the homomorphism to a language and again homomorphism, we might not get the entire language. Some of these strings might be lost in the process. So it is a very important law, you just remember it. And till now it has not been asked in the GATE, so I am expecting that if they want to try something new, they will try with this. Okay, now let's see this operation of right quotient. So right quotient means if two languages are given, then I'll take every string of one language and I'll take every string of other language, and I'll see that if the right side of this string is this string. Okay, so I'll just take an example and explain it instead of using my hands. Let L1 and L2 be the languages on the same alphabet, which means two languages are defined. Then the right quotient of L1 with L2 is defined as L1 by L2 is a string x in such a way that if xy belongs to L1, then y should belong to L2. So what the meaning of it is, if you have a string which belongs to L1, then there should be at least one string in L2 in such a way that the right end of this string is this string. Then whatever is remaining, I'll write it there. Okay, I'll take an example here. See this. Now if L1 is given as 0 1 0 0 1 1 0 1 like this, L1 is containing 1 2 3 4 5 strings, and L2 is containing a string 0 1. Then what is L1 by L2 is, you take every string of L1 and you divide with L2, which is nothing but, see that the right end of it is L2, a string in L2, then whatever is remaining, that will be the left end, that will be written down, right? So if I take 0 1 and 0 1, the 0 1 is completely matching with 0 1, and what is remaining before it? Epsilon. Therefore epsilon is L1 by L2. If I take 0 1 and 0 1 here, what is remaining before it? 0. Therefore 0 is present in L1 by L2. And similarly here also 1 is remaining, therefore 1 is present here. And here 0 0 is remaining, and here 1 1 is remaining. Got it? So how did we get it? Take every string in L2, and then you see that that string is present as the right side, or I can say it as postfix of some string in the L1. Then whatever is remaining in that string, that is nothing but L1 by L2. Okay, now look at this one. It is interesting. L1 equal to 0 1 0 and L2 equal to 0 star 1. If I write L1 by L2, what do we get? Do we really get 1, or do we get even something else? That is interesting, right? So if I write L1 by L2, we don't get 1. So the reason is, we are not actually dividing the regular expressions. What we actually see, you might think that these two are matching, therefore answer must be 1. It is wrong. What I told you, you take all these strings of L1 and then all these strings of L2. For every string in L1 and for every string in L2, you perform the quotient operation. Whatever is the result, you have to write it down as L1 by L2. That is the meaning of it, right? So now I'll take every string of L1. So what is every string of L1? 1 1 1 0 1 1 0 0 1 1 0 0 0 1, so on. And L2 is 1 0 1 0 0 1 0 0 0 1, so on. Okay, and now you had to perform L1 by L2. Take every string of L1 and take every string of L2, and you perform the quotient operation. Now what do we get? If I perform L1 by L2, what do you get? L1 by L2 is, if I perform this, we see that definitely we get 1, isn't it? And if you operate with this, definitely we get 1 0, which means this one and this one. And if you operate with this, I get 1 0 0. The reason is, here there is 1 and this is 1. I am talking about picking up this string and every string of L2. Similarly, you have to pick up this string and every string of L2. Okay, and then I take this and apply this 1 0 0, so on. Therefore what is the language I got? 1 0 star. It is not 1 0. Maybe you could take the second one and you could apply on this, and again we are going to get some strings of 1 0 star only. That is why I am not doing it. You should actually do it and find out that we don't get any new strings. Okay. And one more thing is, if I have a string like this 1 0 1, and if I divide it with 1 1, the quotient is nothing. Here it is 5. The reason is 1 1 doesn't match with any right hand side of this, right? So it is not always necessary that we get something as quotient. Sometimes we might not get anything as quotient. The reason is it doesn't match simply. Okay, it doesn't match with the right side of any string simply. Okay, fine. That is how we could answer it. Regular languages are closed under init operation, INIT, init operation. In fact, regular languages are closed under every operation. Till now, whatever we have seen, homomorphism, inverse homomorphism, quotient, regular languages are closed under all those operations. Now I am going to show you one new operation called as init operation. Init operation is, given a language, take every string and you put every prefix of the string, that is nothing but init. Okay. So for example, if this is the language which is containing 3 strings, then init is what are all the prefixes of a. Okay, so I hope that you remember what a prefix is. I think I discussed it long back in some examples. A prefix is nothing but set of all strings which, okay, let's see this. Let us say Ravi. What are all the set of prefixes of this is? One is epsilon is always a prefix to everything. Okay, and next one is R, RA, RAV, RAVI. These are all set of all prefixes. And what is set of all suffixes is, suffix means from the end. Okay, set of all suffixes is, for this string RAVI, from the end you have to come. So epsilon will always be there at the end, and then I, VI, AVI, RAVI. And what are all subsequences is, from this you can choose some of the you could leave some of them, that is subsequence. Subsequence means you could leave some of them. So R is a subsequence, A is a subsequence, V1 is a subsequence. Anyway, we are going to see that subsequence problem in algorithms. Okay, longest common subsequence problem is there. For here you understand that this is the set of all prefixes and this is the set of all postfixes. Now regular sets are closed under init operation, which means inside this operation they are all closed. So what is init is, I am taking every string and I am applying the prefix operation, which means what are all the prefixes for a string. For this string A, the set of all prefixes are epsilon and A. For this string AB, the set of all prefixes are epsilon, A, AB. And for this string, this one, the set of all prefixes are epsilon, A, AAB, AABB. And anyway, since it is a set, you are not supposed to repeat the elements. So you need not have epsilon 2 times and you need not have A 2 times. You can delete them. Just for the sake of example, I written it, you delete them later. Okay. So it is nothing but init operation. So how to prove that set of all regular languages are closed under init operation is, you construct the DFA first and then you make every state as final state. Then it is going to be like this. Every state as final state except the dead state, which means the set of all strings which could be, or you take all these states from which there is a path to the final state. If there is no path to the final state, you leave that state. So you take set of all such states and you make them all final, then we are going to get a finite automata which is going to accept init of the language. Remember, it is regular languages are closed under all the operations: homomorphism, inverse homomorphism, quotient, union, intersection, difference. I didn't show you any property under which it is not closed. I'll show you later one property at least. Okay. What's this? Regular sets are closed under substitution. Substitution means for every symbol of a language, if you replace it with a other language, then that is substitution. What is it? If every symbol of a language is replaced actually by other language. What is homomorphism? If every symbol of a language is replaced by a string of other language, that is homomorphism, right? But substitution means every symbol of a language is replaced by a other language itself. So if sigma equal to a comma b, then f of a equal to 0 star. So what does it mean? For a, I am going to replace it with a language 0 star. and f of b equal to 0 1 star. What does it mean? B, for b I am replacing it with a language 0 1 star, 0 followed by 1 star, then L equal to a plus b star. So the meaning of this is already some sigma is defined, over that some language is defined, and substitution is given as for every symbol a you are going to replace with the language 0 star, and for every symbol b you are going to replace with the language 0 1 star. Then f of L is nothing but what is this substitution is, for a I am going to place 0 star, and for b 0 1 star whole star. So in place of a and b I substitute the languages, then whatever finally you got, it is again a regular expression, which means it is closed under substitution. Got it? Anyway, proofs are not important. You just don't worry about the proof. Remember the rule. They are not going to ask proof in GATE. They are just going to ask whether it is closed or not. And now you understood that regular languages are closed under everything. Okay. Regular languages are not closed under infinite union of regular languages. So it is not closed. It is very important. Till now we have seen all the properties are closed, but this property is not closed, which means if you take infinite regular languages and if you apply union, then the resulting regular language might not be regular. The reason is, we shall prove it using a counter example. I'll take an example where all the languages independently are regular, and when I apply union among all these languages, they might not be regular. So one example is, let us say L1 equal to a power 1 b power 1. It is finite language, therefore it is regular, and L2 equal to a power 2 b power 2. It contains only one string, so it is finite, so it is regular, and L3 equal to a power 3 b power 3, which is regular, so on. And now if I apply infinite union, L1 union L2 union L3, so on, right? Then what do we get? Infinite union is nothing but a power n b power n such that n is greater than or equal to 1. Now we know that it is not regular. Maybe you could argue that it might be regular in some cases, isn't it? So not closed doesn't mean that it is not regular always. Not closed mean that it might be regular or might not be regular, isn't it? So you might argue with some other example saying that, what if I take L1 equal to a power 1, and what if I take L2 equal to a power 2 and L3 equal to a power 3, and if I apply the union of all these, L1 union L2 union L3, so on, you might say that I am going to get a power n such that n is greater than or equal to 1, and which is regular. It doesn't mean that every possibility is regular. See, whenever I say closed, it means that every possibility has to be regular, but here we got a possibility, at least one possibility, which is not regular, therefore we should say that it is not closed. In case if you get every possibility to be regular, then only we can say that it is closed. Even if we get one counter example, we can say that it is not regular. Therefore this one is not regular. Okay, so infinite union of sets is not regular. Okay. Emptiness problem of finite automata is decidable. So decidable means there has to be algorithm. What is emptiness problem? Given a finite automata, we should know whether the finite automata accepts at least one string or it is not accepting anything at all, right? And it is decidable. Decidable means there has to be an algorithm. So algorithm looks like this. Select the states which are not okay. So first of all, let's discuss about this problem for some time before going to the algorithm. See, given a finite automata, when can you say that it will accept at least one string? If there has to be a final state, at least one final state, isn't it? So, but then having a final state is necessary to accept some string, but then it is not always sufficient, in the sense, even if you have a final state, one final state, it doesn't mean that we'll be able to reach that final state ever. Therefore, having a final state is not just enough. That final state should be reachable from the initial state. Then only we can say that some string is accepted by the finite automata. So how does this algorithm look like is, first select all the states which are not reachable from initial state and delete those states and corresponding states, which means if you are not able to reach some state from initial state, obviously they are useless. Even though you have them, we are never going to use them, useless, therefore you delete them. That is the first step. Now in this step, if the final state is not reachable from initial state, that will get deleted. Therefore if we don't accept anything, that will get deleted there itself, right? And second step is, in the remaining finite automata, whatever is remaining, if we find at least one final state. So in the remaining finite automata, if we get any at least one final state, it means that there is a final state which is reachable from initial state. Therefore there are chances that it will accept at least one string. That is the meaning of it. Okay, so since we have an algorithm, and this algorithm is going to stop in exactly certain number of steps, therefore it is decidable. I told you what is decidability is. You please refer to the concept of decidability, which is discussed at the Turing machines concept. Decidability means we are able to give an algorithm. Since we are able to give an algorithm, the problem of emptiness is decidable. I'll just take an example and explain you what is the meaning of it. Let us say there is a finite automata like this. This is the final state. Okay, now even though there is a final state here, it doesn't mean that it will accept anything, because if you see it, this from initial state I'll never be able to reach the final state. That is the meaning of it. So first step says that if they find out all these states which are not reachable from initial state, and you delete them completely. So in first step, this state is reachable, this state is reachable from initial state, but then this state is not reachable from initial state, therefore it has to be deleted. And after I delete it, I get only 3 states, and none of these states are final. Therefore you can say that this finite automata doesn't accept any string. So the language accepted by this is empty. So emptiness problem has been solved using an algorithm, therefore it is decidable. Okay, what's this problem? Infiniteness problem of regular languages is decidable. So it means that decidable means there is an algorithm to say whether a regular language is infinite or not. So for every regular language, the basics is like this. For every regular language, there will be a finite automata, isn't it? Now let's draw the finite automata for the regular language. That is the algorithm. Okay, and now in the finite automata, I apply the algorithm like this. When do you think that a finite automata will accept an infinite language? Only when there is a loop in that, isn't it? Loop is able to generate infinite number of strings. Now having a loop, is that necessary condition or sufficient condition? Which means if I have a loop, does it definitely mean that we'll be able to accept infinite language? It is not true. Having a loop doesn't mean that we could accept infinite language. I'll give you an example of that. See this. Now this is the initial state, this is the final state, and then there is a state, but then here there is a loop. But having a loop in the finite automata doesn't mean that this finite automata is able to accept infinite language, right? So what should happen? In order to, if a finite automata has to accept infinite language, there should be 2 conditions. One thing is there should be loop, and that loop should be reachable from initial state, as well as from that loop we should be able to reach the final state. Got it? So either if these 2 conditions doesn't hold, which means if the loop is unreachable from the initial state, which means even if you have a loop here, it might sometimes be unreachable from the initial state, or from the loop you will not be able to reach the final state. Even if anything like that happens, we cannot accept infinite language. Therefore in order to accept infinite language, the main conditions are, first thing is there should be a loop. Second thing is from initial state I should be able to reach that loop, and from that loop I should be able to reach the final state. In order to put all these points in terms of an algorithm, and in order to check whether all these points are happening or not, we have written the algorithm. See this. Step 1 is remove the states which are not reachable from initial state and the corresponding transitions. That means you should delete all the states which we never reach. Therefore if there is any loop inside these states which is not reachable at all, that will get deleted. That is what we wanted. Therefore in the resulting finite automata, we have the loops, we'll have the loops only when they are reachable from the initial state. If they are not reachable from the initial state, they'll all obviously get deleted. So see this. Now from the initial state, this state is not reachable. Even though there is a loop, this state is not reachable, therefore we are going to delete it. So what are remaining? Only the states to which we can reach from the initial state. Now what is the second step is, from a state, if we are not able to reach the final state, we should remove it. Therefore the loops which are not reaching the final state will get deleted. See this? Delete the state and the corresponding transitions from which we cannot reach the final state. The reason is, if a loop cannot reach the final state, there is no way we can say that it is going to accept a infinite language. Got it? So now you delete this one, because from this we are not able to reach the final state. In the remaining finite automata, if you find at least one loop and a final state, which means in the remaining finite automata, in case if you find any one loop and final state, then we can say that it is infinite. Otherwise it is not infinite, it is finite. In this case it is finite. The reason is, in the remaining one there is no loop. In case if on the path there is a loop, then we can say that it is infinite, isn't it? So by making these 2 points, we made sure that if there is any loop in the finite automata which is reachable from initial state and from which we can reach the final state, that loop will remain in the finite automata, and we can say that it is accepted by, we can say that the language generated by that finite automata is infinite. Got it? So that is what we derived from this algorithm. Okay, so see, one more thing, when we are doing any when I am showing this algorithm and doing some modifications on the finite automata, you should not take it that the finite automata which we get finally is equivalent to the initial final automata. I don't want to compare the languages, I just want to answer whether they are infinite or not, empty or not, like that, those questions. So the resulting finite automata is way different from the initial finite automata. This method is not actually minimizing or simplifying a finite automata. The language which is accepted by the final, whatever you get, that might not be the original language, but then what we want to derive is the answer to this question, this particular question only. We are not trying to minimize the finite automata here. Okay, fine. Now given two languages L1 and L2 which are both regular, the concept is to find out whether there is an algorithm to find whether L1 equal to L2, which means equality of it is called equality problem or equivalence problem. Now two languages are said to be equivalent if they are actually having the same strings in the language, but then how can we decide it? So let us say two finite automata are given to you, or any representation is given to you. You can convert the representations to finite automata, and obviously you can convert it to DFA and then minimize it, and after minimizing, if both of them are same, then you can say that both are equivalent. Therefore every procedure that I told you is having an algorithm, so ultimately we have an algorithm. So the entire procedure is an algorithm, so it is decidable. So knowing whether two languages are equal or not in regular languages is decidable. In fact, every problem about regularity is decidable, and even membership problem is also decidable, isn't it? How is membership for regular languages decidable is, for every regular language there exists a finite automata. You construct it, and then to the finite automata you give a string. Definitely the finite automata is going to halt after some number of steps. How many number of steps? That depends on the size of the input. So once the input is over, definitely your finite automata is going to halt. Therefore every problem, even the membership problem, is also decidable coming to finite automata. Now let's see this equivalence problem. Now L1 is a regular language and L2 is a regular language. Therefore for every regular language there exists some finite automata. Now you construct finite automata, let us say FA1 and FA2, and then if you have constructed initially some other finite automata, you could even construct a DFA. So for L1 there is a DFA, and for L2 there is a DFA. Constructing it is straightforward. There are many algorithms to convert it. Let us say if it is given as a regular expression, you can convert it to finite automata, or given as a regular grammar, convert it to finite automata. Already we have seen the algorithms. Now take these finite automatas and minimize them. So you just minimize them, and let us say we got again a DFA which is minimized, and again a DFA which is minimized. For minimizing a DFA, again there is an algorithm. Therefore we can minimize this using that algorithm. Now once we get the minimized DFAs, we can compare them and see whether they are equal or not. If they are equal, then we can say that both the languages are equal. So equality problem coming to regular languages is decidable. The reason is whatever steps I told you here, they are all having algorithms. So we got a overall algorithm which will decide it. Got it? So equality problem is decidable. Recursive languages are a proper, look at the options. They are talking about recursive languages. Recursive languages means they have the Turing machines which are going to halt. Recursive languages and recursive enumerable languages both are different. I hope you remember that. Recursive languages are a proper subset of CFL, which means they are saying that recursive languages are contained under CFL. Actually, CFL is contained under recursive languages, isn't it? So if you have, the classification goes like this: recursively enumerable, recursive, CSL, and again CFL here, right? So inside the recursive languages, context-free languages are present. So obviously it is wrong. Always recognizable by PDA. So for recursive languages it is not PDA. For context-free languages it is PDA, and for recursive languages it is Turing machine, right? It is not true. Or also called as type 0 languages. Actually, type 0 languages are the recursively enumerable languages. So I hope that you remember this. Type 0 languages are recursively enumerable. Type 1 languages are context sensitive languages. Type 2 languages are context free languages, and type 3 languages are regular languages. This is the classification by Chomsky. It is also called as Chomsky hierarchy. Chomsky has classified the grammars into 4 types, and according to the grammars, the languages we get are now of 4 types, right? Actually, recursive languages doesn't fall in any of these categories explicitly. It is going to fall under this category, but then recursive languages are not the only languages which are called type 0. Recursively enumerable is called type 0, right? It is wrong. Recognizable by Turing machines. It is right. So definitely a Turing machine can recognize a recursive language. So D is right. Okay. Which of the following is not decidable? Okay, decidable means there should be an algorithm, and algorithm means that is a procedure which should stop in finite number of steps, some number of steps for every instance of the problem. That should be generic one, right? So if you can stop the procedure in finite number of steps, then we can say that we got an algorithm, right? Then the problem is decidable. Now watch this. Given a Turing machine M and a string S and an integer k, M accepts S within k steps. So they are saying that they will give a Turing machine, and now they are saying that they are giving a string S. Either S could be in the language accepted by the Turing machine, or it might not be in the language accepted by Turing machine. Therefore, the Turing machine might halt or might not halt depending on where the string is, isn't it? So, but then we are in luck that they are giving an integer k. You need not wait until the Turing machine halts. You could just run this on this machine. You could run the machine on the string just for k steps. So after k steps, definitely you don't care whether it is halting or not, you stop it, right? And then you can say yes or no. Therefore, this Turing machine is going to halt. The reason is we are going to stop it even if it is not going to halt. Therefore, it is an algorithm, right? So it is decidable. Why is it decidable? Because it is definitely going to stop. The reason is we are stopping it. Why? We just want to know, given this some integer k, which means our Turing machine will always run at most maximum of k steps. In case if it is accepting within k steps, it is great. If it is taking more than k steps, we'll stop it. So we'll never enter the infinite loop. Therefore, what can we say? It is decidable. So what is the algorithm? Just run it for k steps. Any string, any machine, run it for k steps and stop it. Therefore, this algorithm works and stops in fact in k steps. Therefore, it is decidable. Equivalence of two Turing machines. Maybe you could refer to the table where I discussed about decidability and undecidability problems. Equivalence is undecidable in case of recursively enumerable languages. Turing machines means recursively enumerable languages, and there L1 equal to L2, that is undecidable. Okay. And in fact, most of the problems about recursively enumerable languages are undecidable. Maybe you could even take a guess in the exam. If any problem is given about Turing machines, most probably it would be undecidable. Okay, but then use the table once. Okay. Next one is language accepted by a given finite state machine is non-empty. It is nothing but emptiness problem in finite automata. We have already seen that it is decidable, and I have already given you an algorithm also. So what is the algorithm? Just remove all the states which are not reachable from the initial state. In the remaining finite automata, if the final state remains, then it is going to accept something. That is an algorithm. Therefore, it is decidable. So it is decidable. And next one is language accepted by a context-free grammar is non-empty. This one also we had discussed about it. It is nothing but emptiness problem in context-free languages. What is the algorithm? Simplify the context-free grammar. You remember how to simplify it? Remove the useless symbols, remove the epsilon productions, remove the useless unit productions and useless symbols. In the resulting grammar, if you find out that the start symbol is useful, then definitely it is able to derive something. Then definitely the language is non-empty. Therefore, the algorithm is minimize the grammar, and if S remains, then it is non-empty. If everything vanishes, it is empty. So therefore, there is an algorithm. So D is also decidable. Only thing which is not decidable is equivalence of two Turing machines. Okay. Which of the following is true? The complement of recursive language is recursive. See, the main difference between recursive enumerable language and recursive languages, there will be a Turing machine for both of them, and for recursive languages it halts, and for recursive enumerable languages it may halt or may not halt on a given string. Therefore, for recursive languages there is a membership algorithm. What is the membership algorithm? Given the string, it will say yes, the string is present in the language, or no, the string is not present in the language. It is possible only because the Turing machine is halting, right? Now, based on that property, the trademark of recursive languages is Turing machine will always halt. Now, let's see what happens to a complement of a Turing, this recursive languages. If I have a recursive language, then definitely it means that there is a Turing machine which accepts it, which accepts a string, and it will definitely say yes, it is present, no, it is not present in the language, isn't it? Now, if I complement it, what does it mean? For the strings which are present in the, let us say this is it, is the language, some particular language I am talking about, which is recursive language. Then for this language, if I give a string which is in the language, it is going to say yes, it is present. If I give it a string which is not in the language, it is going to say no, it is not present. Now we can take this same Turing machine and see that it accepts the complement of the language. Complement of the language means whatever is outside this circle. Inside the circle is complement, outside the circle is not the the inside the circle is language, outside the circle is the complement. Now we could change this Turing machine in such a way that previously when it was saying yes, now I'll make it to no. Whenever it says yes, I'll tell you that it is saying no, and whenever it is saying no, I'll tell you that it is saying yes. Then what happens? Then there is a Turing machine which always halts, which will say yes for every string which is not present in the language, and which will say no for every string which is present in the language, which is nothing but we got a halting Turing machine for the complement of the language. Therefore, the complement of the language is also now recursive. So what do you understand? Every recursive language is closed under complementation, or complementation of every recursive language is again recursive. See, whenever we are talking about the properties, it should be applicable for every language. You should not take only one example for which it accepts and you should not say it. It should be generic. So for every language this is true. Whatever I told you is true in case if the language is recursive, right? Therefore A is right. A is true. Complement of recursive language is recursive. Okay. Complement of a recursive enumerable language is recursively enumerable. It is not true because the Turing machine does not halt. We cannot give such a kind of argument to say that recursive languages are closed under complementation. See, this statement is saying that every recursive language, for every recursive language, it seems that if you take the complement, it should be recursively enumerable language, I mean REs, right? It is not possible. So by heart it, recursively enumerable languages are not closed under complementation. Very important. And next one is, complementation of recursively enumerable language is either recursive or recursively enumerable. It is not true. If this is not true, definitely it is not true, right? It simply extends it. If the complementation of recursively enumerable language cannot be in the bigger set of recursively enumerable language, how can it be in the smaller set of recursive languages? Fine. If this is false, this is definitely false by extension. And now the complement of CFL is CFL. So we have already seen that context-free languages are not closed under complementation. The reason is, the argument is like this: context-free languages are not closed under intersection, therefore they are not closed under complementation. So how did we prove that context-free languages are not closed under intersection? If I have a language a power n, b power n, c power m, and then a power n, c power m, b power m, c power m, what is the intersection of these two languages? A power n, b power n, c power n, right? Therefore, intersection of two context-free languages, this is a context-free, this is context-free. Intersection of two context-free languages is not context-free language, which means context-free languages are not closed under intersection, right? And now we could write intersection of two languages as like this. Right? Now check this. Already I'm saying that this is not context-free language, I mean this is not closed. If this is not closed, then complementation should not be closed. The reason is, if complementation, let us assume that complementation is closed, then what happens is, we already know that union is closed of, like context-free languages are closed under union. That is simple. Take that initial states, I mean the start symbol, and you write s derives s1/s2. That is straightforward. Now assume that complementation, this context-free languages are closed under complementation, then what happens is, this one will be CFL, this one will be CFL, L1 complement and L2 complement, and union will be CFL, because union of two context-free languages are context-free language, and now the complementation will be CFL. So in case if our assumption is context-free languages are closed under complementation, then we'll find out that context-free languages are closed under intersection, but we already found out that they are not closed under intersection. Therefore our assumption must be wrong. What is our assumption? Context-free languages are closed under complementation. Therefore this is false. So only true statement is complement of recursive languages are recursive. It is very, very important. It is all about complementation. So remember that complementation of recursive language is recursive, and complementation of recursively enumerable language is not closed, and complement of CFL is not closed. So based on this, I'll just like to extend this question and give you some few points. See if you can understand it. It is logical extension. Now we know the placements of how the languages are placed, like that Russian dolls, one inside the other, right? See this. This is context-free languages, assume that, and now this is set of all recursive languages, and this is set of all recursively enumerable languages. There is one more language called context-sensitive language. I am just eliminating it. There will be one more language present here, which is context-sensitive language. I am just eliminating it. Okay. Now tell me. Here there is context-free languages, and here there is recursive languages. It is not regular, it is recursive languages, and here there is recursively enumerable languages. Now, if L is a context-free language, which means here, if L is a context-free language, some language L is a context-free language, then is the complement of L a context-free language? It is false. So I'll just write down some few points. You answer me these questions. If L is context-free language, then L complement is context-free language. Say yes or no. it is false. The reason is, just now we have seen that context-free languages are not closed under complementation, which means every context-free language complement cannot be context-free. There might be some examples for which this statement holds true, but then if it is a generic statement, if it is not true for all the examples, it is not true. Therefore, this statement is false. If L is context free, L complement is context free is false, because context free languages are not closed under complementation. Now, it is interesting, L is context free language only, then L complement is recursive. You think about it and answer it. L is context free only, L is context free language, which means present in the innermost circle. Now I am asking you whether the L complement is recursive or not. Think about it and answer. Okay, see, if L is context free language, then definitely L is recursive language, isn't it? If L is context free language, then definitely L is recursive language. See, how to answer it is, you should go step by step. Now first of all, whenever L is given as context free language, apply the rules of context free language and see if it is closed. If I apply the rules of context free language, definitely it is not closed. Therefore, next apply the next level of properties. If L is context free, then L is recursive language. If L is recursive language, then L complement is also recursive language. Therefore, L complement is recursive language. Think about it. I am saying that L is context free. Therefore, what can you say? If L is context free, then L is obviously recursive language, right? And we know that recursive languages are closed under complementation. What does that imply? Then L complement is recursive. It is very important that you know this procedure. I've seen many students who are really good, but then they get confused at this point. It is very simple and straightforward. I don't know why you get confused. Okay, just think about it. It is very simple. Now my next question is, L is context free language, then I want to know, tell me whether this statement is true or false. If L is context free language, then L complement is recursively enumerable language. How do you want to evaluate it? Now you cannot use the argument that L is context free language, therefore L is recursively enumerable languages, it is recursively enumerable language, and so since recursively enumerable languages are not closed under complementation, this one is false. That is, your argument is wrong, absolutely wrong. How to apply the rules is, you start at the lowest level. What is lowest level given? Context free languages. Apply the property and see whether it is closed or not. If it is not closed, then go to the next level. What is next level? Recursive languages. Apply it there. If it is not closed, then apply the next level. You have to go in steps. You should not directly jump from here to here, because here itself the language is closed. Got it? So how to answer this question is, if L is context free language, right? If L is context free language, then definitely L is recursive language, right? If L is recursive language, what does that imply? L complement is definitely recursive language, right? And now we got a language which is definitely known to be recursive language, and every recursive language is recursively enumerable. Therefore, upon the grounds that every recursive language is recursively enumerable, we can give this statement that L complement is recursively enumerable. Very important, and I think most of you have already got confused. Please watch this video 3-4 times. Okay, L is recursive language. See, L is given as context free language, therefore L is recursive language. Why am I taking it to the level of recursive languages? Because the property failed to show the closedness in the level of context free languages. In case if it would have been closed under the level of context free languages, I would have never raised it to recursive languages. I would have answered the question here itself. How? If L is closed under recursive, complementation, if CFLs are closed under complementation, then L complement is definitely context free language, therefore L complement is recursively enumerable language as well. I could have closed it there, but since context free languages are not closed under complementation, I had to raise it to next level. So understand this, L is context free language, therefore but then L complement is not context free language, therefore I am taking it to the next level. What is next level? If L is context free language, then it is definitely recursive language. And now if L is recursive language, we already know that L complement is definitely recursive language. And now if L complement is recursive language, then definitely L complement is recursively enumerable language by definition. Why? It is already present within this set. Therefore L complement is recursively enumerable language. If you directly try to take the language like this, if L is context free, L is recursively enumerable language, and since recursively enumerable languages are not closed under complementation, it is not closed, that is false. So remember this point is very important, whatever we discussed. Okay, so what are the points? If L is context free, L complement is not context free, or L complement may not be context free. That is the actual statement. L complement may or may not be context free because they are not closed. For some examples that may be, but even if there is one example for which it is not, you can say that in general it is not. And if L is context free, L complement is definitely recursive language. If L is context free, L complement is definitely recursively enumerable. I'll just ask you one more question. Answer this. L1 is here, right? Now tell me about it. If L1 is recursive language, which means it is present here. If it is recursive language, it could be either present here or here. I don't care. If L1 is recursive language, then what about L1 complement? Definitely recursive language, right? Is it recursively enumerable? Yes. If L1 is recursive language, L1 complement is recursively enumerable as well. The reason is L1 complement is recursive language, and therefore it is recursively enumerable as well. I hope that these all points are making sense. You please watch this video to now this Turing machine is given the transition table, and then they ask you some options. Now this question is given in GATE, I think 2003. Yes, 2003 question, and then they are asking you whether it halts on some strings or not, which means they are giving you various options. We can find out the options. So it is, if you could do it like this, you can go ahead, or if you are comfortable with the transition diagram, you can draw the transition diagram and then trace out the input. Anything is fine. So let's see the transition diagram just for practicing. So Q0, the question is about halting, and the initial state is given as Q0. Q0 on 0 is making 0 to 1, and it is moving right, and it is going to Q1. And Q1 on 1 is leaving it as 1 and staying in Q1, which means on 1 it is leaving it as 1 and is moving right. And Q0, so whenever it is halt, you need not write anything. So when you don't write anything, that is nothing but the dead configuration, and obviously it means that it is halt. You need not explicitly mention halt. If you leave it out, it is obviously going to halt. So you need not say that on B Q0 is going to halt. Oh, this one is actually 1, right? This is the transition for Q0. Check this. So Q0 on 0, this is the transition, and Q0 on 1 also it is the transition. On 1 also it is going to make it 1 and move right. Okay, and now Q1 on 0 is going to stay in Q1 itself, and it is going to make it as 1 and move right. And Q1 on 1, it is going to go back to Q0 and leave it as 1 and move left, right? And Q1 on blank also it is going to Q0 and leaving it as blank and moving left, right? So now let's see what happens for any string. The options are various options are given, and one of the option is it does not halt for any string in 0 plus 1 plus. So let's see what happens if I give the smallest string 0, and on the either sides of it there is blank. Okay, so initially you will be in Q0. So what is Q0 trying to do? Q0 on 0 will make it 1 and move right, which means this one will be made 1 and it will move right, and it will be in Q1. Now Q1 on blank will leave it as blank and move left, which means it will leave it as blank and it will move left. Again we are here, right? And now Q1 on 1 will make it as 1 and move right. It will make it as 1 and move right, and again it will leave it as blank and move left. So which means it will always be going like this. It will never halt. It is a non-halting Turing machine for the given input 0, right? It will never halt. It will sometimes be in Q0, sometimes be in Q1. It will just toggle between these two states. Now let's see what happens if the input is 1. If the input is 1 and on the either sides if there is blank, let's see what happens. If you are here, Q0 on 1 is going to leave it as 1, yes, leave it as 1 and move right, okay, and be in state Q1, and Q1 on blank is going to leave it as blank and move left, and again we move left, right, and again we are in Q0, and Q0 in 1 is going to leave it as 1 and move right. So again it is going to do the same thing, either on 0 or 1 it is going to do the same thing, right? So you can take all these strings and you can check out that for any string what it will do is it will convert the entire string into all ones and then reach the blank, and in the blank it will just keep on toggling here and there. I mean, after reaching the blank it will be in Q1 and Q1 will push it to Q0 and Q0 will push it to Q1. Therefore it is not going to halt in any of these states. So it is not going to halt for any string in 0, 0, 1 plus. Watch this. The C languages, the C programming language is what they are asking. Is it a context-free language? So actually if you look at the rules of the C language, C programming language, like in compiler I have given you rules of expression, right, and all the parsers. Every parser is going to take the context-free grammar as the input, right, and at this lexical analysis phase it is going to take the regular expressions. Therefore C programming language is as big as context-free languages, or context-free languages are powerful enough to actually describe the C programming language. And in fact we are not using all the context-free languages. We are using the subset of context-free languages which could be parsed by LR parser, and LR parsers cannot parse every context-free language, right? So the answer is C programming languages, context-free language is true, because every language, every grammar, every rule is encoded in terms of the context-free languages at the parser, right? It is true. At some phase it is regular and at some phase it is context-free. Therefore you can say that it is all context-free. And now context-sensitive language, no, we didn't use any context-sensitive language. We never had the rules like this, AB is actually BA or something like this. We never had any rule like this, right? So it is not context sensitive language. I mean, it is not required, that big language is not required. C language, context-free language are simple. And now regular. So yes, we are using regular also, but then we are not just using regular languages, we are using context-free languages as well. So regular language is too powerless to implement C language. Context-free languages are actually to the exact power. It is not regular. Parsable fully only, so check this, only on Turing machines. It is wrong, because we have seen that at parsing methods, in parsing, every parser is a kind of push-down automata. Therefore, push-down automata, they are able to parse the C language. We don't need, I mean, they are saying that only on Turing machine. We don't need a Turing machine to parse it. Yes, given a Turing machine will be able to parse it, but that is a overkill. I mean, it is like, too much. Okay. So definitely the answer is CFL. Now watch this. Let L1 be a recursive language and L2 be a recursively enumerable language but not recursive. See, in this question I am going to use R. R means recursive and RE means recursively enumerable. Okay, R means not regular and RE means not regular expressions. R means recursive in this question. R means recursive and RE means recursively enumerable. Now watch this. They are saying that L1 is recursive and L2 is recursively enumerable language but not recursive. So if it is recursively enumerable languages, and I mean this one is recursively enumerable and this is recursive. Now L1 is here and L2 is here, because they are clearly saying that L2 is recursively enumerable but not recursive. In case if they left it out and if they had said that only L2 is recursively enumerable, only that part if they have mentioned without mentioning but not recursive, then L2 could be either present here or here. So they wanted to place the language exactly outside the regular languages, recursive languages. So L1 is present in recursive languages and L2 is present in recursively enumerable, which is not recursive. Okay, that is the placement. Now they are asking just about the complementation. You already know about it. L1 is regular recursive languages are closed under complementation. Therefore, L1 complement is recursive, and recursively enumerable languages are not closed under complementation. Therefore, L2 complement may or may not be recursively enumerable. Therefore, this is L1 complement is recursive and L2 complement is not recursive. That is the answer. Sorry, recursively enumerable. So this is the answer. L1 complement is recursive and L2 complement is not recursively enumerable. What about the first one? L1 complement is recursive and L2 complement is recursively enumerable. It is wrong because L2 is not closed under this recursively enumerable languages are not closed under complementation. Therefore, this is wrong. First one is right. L1 complement and L2 complement is not recursively enumerable. It is wrong because L1 complement itself is recursive. Therefore, L1 complement itself is recursively enumerable. Therefore, this is wrong. L1 complement is recursively enumerable. It is right. The reason is L1 complement is recursive. Therefore, every recursive language is recursively enumerable language. This is right. And L2 complement is recursive. It is wrong because L2 complement is not recursive itself, recursively enumerable itself. How could it be recursive, right? Therefore, B is the answer. If L and L complement are recursively enumerable, so we have already seen this. I mean, this is a theorem, right? I think in one of the theorems, I discussed about this. Okay. So what is this question is, if L and L complement both are recursively enumerable, which means for L there is a Turing machine which will say if this string, let us say this is L and this is L complement. So inside it this is L and this is sigma star minus L, which is nothing but L complement. Now there is a Turing machine TM1 which will take the strings inside the language L and it will say yes, definitely yes, right? And L complement is also, now if it is recursively enumerable, we don't know whether if I give a string which is not in the language, if this Turing machine TM1 is for language L, then it will take the string inside the language and it will say yes, I accept it, fine. But then if we give it any string which is outside the language, it will say either no or it will follow infinite loop, right? And definitely there is one more Turing machine TM2. The reason is L complement is also recursively enumerable. Therefore, there is some Turing machine which will take a string which is not in the language and which will say yes, this string is not in the language, right? So now combining these two, I could make a new Turing machine for this language. Combining these two, I could make a new Turing machine, and which is going to say, given any string either inside the language or outside the language, this will say yes, this string is present, and this will say no, this string is not present, right? Therefore, I got a new Turing machine for the language L which always halts, right? So what could you say? So L is definitely recursive. In fact, L is recursive and L complement is also recursive. Why? Recursive languages are closed under complementation. This is a beautiful question, isn't it? So if L and L complement are both recursively enumerable, then definitely L and L complement both are recursive, right? Beautiful question. This is a very good question. The way they framed the question is really good. Awesome. Now let L be a language and L complement beats complement. One language is given and its complement is given, and then they are asking which one of the following is not a viable possibility, which means what are the various possibilities for L and L complement. So can they both be recursively enumerable? Can they both be recursive? That is what they are asking, right? So see this, if L be a language and L complement beats complement, which one of the following is not viably possible? So let's see one by one. Neither L nor L complement is recursively enumerable. So what does they mean is, see, if we have set of all recursively enumerable languages and then set of all recursive languages, set of all context-free languages and set of all regular languages. If you have the set like this, we know that there are many languages which are not known, which means there are many languages which are not recursively enumerable, for which there could be no Turing machine at all, and we have shown a proof also how Turing machines are countable and total number of languages are uncountable. Therefore, there are many languages which are not recursively enumerable. So they are saying that L and L complement could be somewhere here. It is absolutely true. If L is outside this, we don't know how to classify them, we don't know how to accept them, and we don't know what its complement is. We don't know about that language, and we don't know definitely what its complement is. So definitely it is viable that both of them could be outside the range completely, and we don't know how to interpret it. So it is fine, it is true, it is possible, viably possible, right? And one of L and L complement is recursively enumerable but not recursive, and the other is not recursively enumerable. What they are saying is, if either L is here or L complement is here, the other language will be outside. This is perfectly fine. The reason is, recursively enumerable languages are not closed under complementation. Therefore, if L is in recursively enumerable language and not recursive, see, it is very important that this should not be recursive. The reason is, if the language is recursive, both the complement and L are going to be inside it, right? So it is completely fine. If L is here, L complement is here, or if L complement is here, its complement, which is L, will be outside. It is completely perfect, right? So one of L and L complement is recursively enumerable but not recursive, the other is not. So it is viable, perfectly viable. Both L and L complement are recursively enumerable but not recursive. What does that mean? They are saying that both L and L complement are going to lie here, which is not possible. The reason is, recursively enumerable languages are not closed under complementation, right? Therefore, they cannot both lie inside the recursively enumerable languages. I mean, they cannot both lie inside this part, definitely. That is not viably possible. Both L and L complement are recursive. Fine, it is true. The reason is, recursive languages are closed under complementation. Therefore, if L is recursively recursive, then L complement will also be recursive. So both of them can fall perfectly inside the recursive languages. So it is right. So it is also viable. Now let's just extend this question a bit, just a bit. What if both L and L complement or CFL? Is it possible? Can both L and L complement be inside CFL? It is not possible because context-free languages are not closed under complementation. Therefore, it is not viable. Can both L and L complement, sorry, here it is L and L complement, or regular languages, which means can both of them fall here? If L is a regular language, can L complement be also a regular language? It is perfectly valid, viable. The reason is, regular languages are closed under complementation, right? So only case which is not viable is in case of context-free languages and in case of recursively enumerable languages, because they are not closed. All the other languages are closed under complementation. Remember this. Only context-free languages and recursively enumerable languages are not closed. The reason why recursively enumerable language is not closed is Turing machine does not halt. And the reason why context-free languages are not closed is they are not closed under intersection. Therefore, how can they be closed under complementation, right? So it is worth remembering these points because many questions are asked on this, okay? And they are very simple to answer. Initially, they might look confusing, but please watch this 2-3 times or 4 times or 10 times, 100 times until it is clear, okay? Now watch this. Let M be a encoding of the Turing machine, which means this question is given in 2014. You could even refer to this question, 2014 question. M be a encoding of the Turing machine. So what is encoding of Turing machine? We have already seen that a Turing machine can be encoded into zeros and ones. You know, in case of universal Turing machine, I told you that. You please refer to that concept. So every Turing machine can be written in terms of zeros and ones, right? So a string of zeros and ones can be eligible to be a Turing machine, but not every string could be eligible to be a Turing machine. Now, how many strings will be there of 0 and 1? They will be finite, I mean not finite, countable, right? And now the Turing machines is a subset of that original set of all strings. Okay, I'll just write it and explain you like this. See, now encoding is nothing but given a Turing machine we can write it in zeros and ones. Therefore, let us assume that sigma equal to 0, 1, right? And now sigma star contains set of all strings which are possible over 0 comma 1. And now any string within this language, you can take any string in this language, that string could be, or that string is eligible to become a Turing machine. I mean, sometimes it could be a Turing machine, or sometimes it might be too simple that it cannot be a Turing machine. Anyway, Turing machines are subset of a countable set, therefore set of all Turing machines are countable. That we already know it, right? Now they are saying that from all these, so let L equal to, so they are saying that there is a string for every Turing machine, and then the question is like this: let L equal to M. M is a Turing machine that accepts a string of length 2014. So among all these Turing machines, it seems that we have to find out the string, or we have to find out the Turing machine which will accept a string of length 2014. And they didn't give you any language, that is not necessary. Either you could assume the language is A comma B or A comma B comma C, whatever. Now they are just giving you one string, only one string, right? And now you are supposed to find out all the Turing machines which are going to accept this particular string. So the question is, now the main problem in this one is they are asking you in terms of 2. L is nothing but set of all Turing machines which are in terms of zeros and ones, Turing machine 1, Turing machine 2, so on, in such a way that every Turing machine should be able to accept the string of length 2014, right? So now what is recursively enumerable is, recursive enumeration and decidable means there should be an algorithm, which means you tell me some method in which I can solve this question, but then that procedure is supposed to halt. If you can say such a method, then it is nothing but decidable, right? And recursively enumerable means you tell me some procedure that need not halt, but then using which I will be able to write down all these strings one by one. Okay, that is the main difference. Again thinking about it, simple. See, decidable means you tell me some algorithm by which I will be able to find out all such Turing machines, and that algorithm should halt. If you can find out such an algorithm, then it is called decidable. What is recursively enumerable is, the recursively enumerable languages are also nothing but the languages which could be enumerated, or for which there is enumeration procedure, which means if we can come up with a procedure which will be able to list out all the strings in the language one by one, and that procedure need not halt, but it should only write down the strings of the language, right? So there is an interesting theorem. That theorem is very big, so I'll just try to answer this, in simple words. Maybe try to follow this. If you are not able to get it, get this at any point, you please rewind it and watch it. This is a question which you might have to watch more than once, right? So don't worry if you don't understand it first time. Now see this. Decidable means you should be able to find out an algorithm using which you should be able to write down all these strings. So first let's see about the recursive enumeration. I want to find out all the Turing machines which will accept a string of length 2014, right? So let me find out some procedure. That procedure need not halt. Okay, now this procedure should be able to enumerate all the strings T1, TM1, TM2, TM3, so on. Now we already know that set of all Turing machines are from set of all this sigma star. So what you do is take every string from sigma star one by one. So how many strings are there? Infinite. That is why this procedure will never halt. Okay, take every string one by one, and after you pick up a string, just check if that string could be Turing machine or not. So it is very easy to check whether it is a Turing machine or not, which means it should be in some format so that it could be again encoded back into the Turing machine. In case if it is in the form of Turing machine, then take that. Okay, so are you following it? Now from the sigma star you have all these strings like 00, 01, 10, so on, right? Now you pick these strings one by one, and then you examine whether that string could be converted into a Turing machine. In case if it could be converted, then what you do is you write it down, right? Yes, this is a Turing machine, and then this is a Turing machine, and then this is a Turing machine, so on, right? Write all the Turing machines possible. Now this is nothing but the set of all Turing machines. Now what is that they are asking is, you have to find out the Turing machines which will accept the strings of length exactly 2014. So what you take is, take every Turing machine and then try to give the string to it, input of length 2014. The problem is, if you give a input to that and then if you wait, then what happens is, in case if 2014 is not accepted by the Turing machine, it will never halt. Then you will be spending your entire time just looking at one Turing machine which is not accepting a string of length 2014. Therefore that enumeration does not work, or that procedure cannot enumerate all these strings. So let's try to find if there is any other way we could find out the Turing machine. Okay, see, I don't know whether you are understanding this in terms of this mathematical language. I'll just make it simple for you. I told you that in order to teach any subject, let us say like TOC, right, there is nothing called the end. I could keep on teaching it, keep on teaching it, keep on teaching it, which means if you give me that subject, I'll keep on teaching it throughout the life. I'll never halt, right? But then the problem is, if you spend time in one subject like that, you will not be able to learn other subjects. Then what we could have done is, take the first subject TOC, teach it for 1 hour, and take the next subject operating systems, teach it for 1 hour, and take the next subject some other subject digital, teach it for 1 hour. If I go in that way, right, then all these subjects will be covered equally. And in case if a subject is small, let us say TOC is infinite, then if I start with TOC, I'll never stop. See, I think you are following this. See, if TOC is infinite, I'll never stop. Let us say there are finite subjects and there are infinite subjects like TOC. Then what I'm doing is, if I start with TOC, I'll never end teaching it and you will never learn any subject. Then what we could do is, start with TOC, but then teach it for 1 hour, and again start with operating system, teach it for 1 hour, start with DBMS, teach it for 1 hour, start with some other subject, teach it for 1 hour. When all the subjects are finished for 1 hour, and again come back and again teach it for 1 hour, and again come back and again teach it for 1 hour. If I do like this, what happens is, after some amount of time, definitely the subjects which are finite will be over and the subjects which are infinite will be running forever, isn't it? Therefore you have found out an enumeration method there, right? What is enumeration method? Don't take one string and spend your entire time on that. Run it for some time and again go to the next one, run it for some time, run it for some time, run it for some time. Therefore if there is any Turing machine which is going to accept 2014, that will halt at some point. Therefore you could write it down, that is the enumeration method. But then the enumeration method itself will not halt, but you will be able to write down all these things which are in the language. Okay, let's come to this. Now what I mean to say is, first from sigma star there are all Turing machines, and then you are writing all the Turing machines in some order. Then you are taking up each Turing machine and now you are giving it a string whose length is 2014. In case if it accepts it, you can write it down and say that that string is present in the language. But the problem arises when the string is not accepted by the Turing machine, then the Turing machine will get into infinite loop. So you will end up spending the entire time with one machine and you will never go ahead and you will never be able to write down all the Turing machines. Therefore, what is the best method? Take one string and run one time. Run one time means just trace out one move, right? One transition. Just run one time on this and then one time on this, one time on this. So how do you write it is, again don't go on writing like this. Then what happens is, you will never end because Turing machine itself are infinite, right? Then how to do this one is, I want more space. First you run one step on Turing machine 1, which means give the input whose length is 2014 and run one step on that, and after that you run one step on Turing machine 2, right? And after that you again come back to Turing machine 1 and again run Turing machine 1, Turing machine 2 and again Turing machine 3, and next time again you come back to Turing machine 1 and again you run Turing machine 1, Turing machine 2, Turing machine 3, one step each, and Turing machine 4, right? and again you come back to Turing machine 1, and again you run Turing machine 1, Turing machine 2, Turing machine 3, Turing machine 4 and Turing machine 5, and next time 1 2 3 4 5 6, next time 1 2 3 4 5 6 7, right? Therefore if you go in that order, you are not going to stop at one Turing machine and continuously look at it. If it is going to fall in infinite, you don't worry, you are going to go on to the next one. If I follow this this kind of enumeration, definitely at some point all the Turing machines which accept the strings of length 2014 will be written down, which means they definitely halt and we can write them down. Therefore I can list out all the Turing machines which are going to accept 2014, since we have a enumeration method and which can enumerate this all the languages. The language itself is recursively enumerable, therefore the language is recursively enumerable. Now the second question is it decidable or undecidable? Decidable or undecidable means given a string in the language which is nothing but the Turing machine, you should be able to say whether it accepts a string of length 2014 or not. That is impossible. The reason is, if one particular Turing machine is given to you, you could never say whether it accepts 2014 or not. Why? If it accepts it, you can stop, but if it doesn't accept it, it might fall in infinite loop. Therefore you will never be able to say exactly whether a string belongs to the language or not. Okay, so what does it mean? The language is undecidable, but it is recursively enumerable because we have the recursive enumeration procedure. The problem with decidability, or whether to find out the decidability or not, is given a string you should be able to say yes, it is in the language, or no, it is not in the language. But the problem is, if the string is not in the language, that will never be written down, therefore you have to wait forever, right? So what is recursive enumeration means, if the string is inside the language, at some point you will be able to write it down. But if a string is not inside the language, you will never be able to write it down and your enumeration procedure will not halt. But that is fine, as long as you have enumeration procedure. Well, even if enumeration procedure doesn't halt, it is okay, you keep on writing it, but then you are able to write all the strings in it. That is why it is recursively enumerable. But it is not decidable because given a string, you will not be able to say whether that string belongs to the language or not. Why? Given string is nothing but a Turing machine. Now you will take the Turing machine and what you will try to do is give it the input which is nothing but a string of length 2014. In case if you are lucky, it will stop and say that I accept it. In case if you are not lucky, it will go into infinite loop and you will never be able to say yes or no answer, right? Therefore the language is recursively enumerable but not decidable. Okay, so it is undecidable but recursively enumerable. Answer is B, right? Please watch the video more than once. I don't know whether you understood it or not. If I could look into your eyes and then see your expression, I could understand, right? But it is difficult. Therefore better what you could do is watch it many times. Okay, which of the following statements is false? So they are asking true or false question. The halting problem for a Turing machine is undecidable. So obviously it is true. Given a Turing machine, whether it halts or not, undecidable, right? This one is true. This option is true. Determining whether a context-free grammar is ambiguous is undecidable. So I told you that this halting problem is the first one which is known to be undecidable, and if that problem is converted to some other problem, then that problem will also become undecidable, isn't it? So I have shown you that. I think I told you with some text theory that Turing machine can be the halting problem can be converted to post correspondence problem, and now post correspondence problem can be converted to ambiguity problem, right? Therefore from halting, post correspondence, ambiguity, therefore ambiguity problem is undecidable. Even if you don't remember all this, you could see the table. In the table I think I didn't tell you this table, it is not there, but then you can remember it this way, or it is a very popular question, better by heart it. So ambiguity of Turing, this context free grammar is undecidable. Given two arbitrary context free grammars G1 and G2, whether G1 equal to G2. So this is nothing but equality problem in context free languages, right? And I told you that in the table that equality problem in context free languages is we cannot decide, therefore it is undecidable. given to whether the question is not completed, is undecidable, then it is true, which means they are giving you two arbitrary context free grammars. See, if two particular grammars are given, which means for a particular instance we can definitely write an algorithm, but then if generic grammars are given, there is no algorithm, right? So they are saying that context free grammars are given G1 and G2. When context free grammars are given G1 and G2, then it is nothing but two context free languages are given, L1 and L2, right? And now they are asking whether they are equal or not. Equality in the case of context free languages is undefined, I mean not decidable, undecidable, therefore it is true. Given two regular grammars G1 and G2, it is undecidable whether G1 equal to G2, L of G1 equal to L of G2. So they are talking about regular languages. In regular languages, equality is decidable. So it is simple. What you convert these grammars to, the algorithm is like this. Why it is decidable is there is algorithm is like this. You convert the grammars to regular finite automata, and then you convert the finite automata to DFA, and then you minimize both the DFAs. If both the DFAs are equal, you can say that both the languages are equal, therefore that is the algorithm, and so it is decidable, right? So it is decidable, but the given question is, they are saying that it is undecidable. So what can you say? D is false, so all the other are true. Okay, which of the following are decidable? So they are asking which of the following are decidable. We have already seen the table. So in the table I have given you some values like D, UD. You please check that. I'll explain this how to use the table. Whether the intersection of two regular languages is infinite. So first of all, is it decidable that okay, do you know that regular intersection of two regular languages is regular languages, and is there any algorithm to find out the intersection of two regular languages? There is, right? For example, we have, I think I have told you that regular languages are closed under intersection, and I have even given you a proof, right? How? Complementation and union. Okay, I'll just explain you what it is. See, now I told you that regular languages are closed under union and regular languages are closed under complementation, right? And now since they are closed under union and complementation, they are closed under intersection. Why? L1 intersection L2 can be written as L1 complement. Okay, see this. L1 intersection L2 can be written as L1 complement union L2 complement whole complement. I already told you that regular languages are closed under complementation, which means under these two are regular and they are closed under union, which means this entire part is regular, and now they are again closed under complementation, therefore this entire thing is regular. So intersection of two regular languages is definitely regular. Now what they are asking is, now is that language infinite? So the question is, given a regular language, is that infinite or not? That is what they are asking. So what is the answer? In case of regular languages, I told you that we can determine whether it is a infinite finite or infinite or empty. All these can be decidable. Therefore this is definitely decidable. Check the next one. Whether a given context free language is regular. So what they are asking is, if a language is given, right, which is context free, is that regular? Please refer to that row in which I told you is L regular, or given any language is it regular or not. There is a row, I think lost but one row or lost but three row, I don't remember it. In the table you can check it. Okay, let me check it once. So that is in the is L regular, I think the last row is L regular. Yeah, that is the last row. In that table, the last row is L regular. Then you can see that in context free languages it is undecidable, which means given a context free language and whether a given context free language is regular or not is undecidable, right? And now whether two PDAs accept the same language. So here they are asking, PDAs means context free languages. So in case of context free languages, they are asking the equality question, and we know that it is undecidable. So again, this is in that table. If you look at that decidability table, it is I think 4th row. In 4th row under the CFL, why CFL? Because Pujan automatas are given, Whenever they say push-down automatas or context-free grammars, you go to CFL. Whenever they say finite automata or regular grammar, you go to regular languages question, right? So it is nothing but undecidable. Whether a given grammar is context-free. So this is simple. How can I find out whether a given grammar is context-free? I told you that there are 4 classes of languages and we define them, right? If the grammar has to be context-free, then the left hand side there should be only one variable and the right hand side can be a collection of any variables and terminals. Therefore, you take each production and you examine it. Any given grammar, it is a finite grammar, which means every grammar is finite. Let them give it. Then you take the productions one by one and every production you see whether it is following that rule or not. What is the rule? Left side should be a variable and right side should be could be any combination of variables or terminals, right? Therefore, you can see that whether a given grammar is context-free or not, it is completely decidable. And the algorithm is examine each production one by one and see if it is according to the rules. What are the rules? Left hand side, it should be of the type A derives alpha, where A should be belonging to vertices and alpha could be anything vertices and terminals, right? Simple, that's it, right? Therefore, you can take every production and you can examine it. So it is decidable, right? So only 2 which are undecidable are these 2. So you can even remember it about this context-free grammars. Generally, the most frequently asked questions is 2 context-free grammars are equal or not, G1, G2 are equal or not, or 2 context-free languages are equal or not. Equality question is most popular and then complementation is most popular. You can by heart it, okay, fine. Which one of the following problems are decidable? So they are asking what are the decidable problems in them. First one is, does a given program ever produce an output? So it is nothing but program is a Turing machine. So it is asking that whether a Turing machine will ever halt. This is one other way of asking whether a Turing machine will ever halt. I told you that Turing machine like program, see the notion of falling into infinite loop in Turing machine is also there in the programming language, which is nothing but infinite loop, right? The problem of non-halting in Turing machine is equal to infinite loop in program. Therefore, it is undecidable. So simple. Does a given program ever produce an output? What you do is you take the program and try to run it and then watch it for some time. How much time do you want to watch? If it produces an output and stops, it is fine. What if it has fallen in infinite loop? What will you be thinking? You will think that, oh, this must be doing some useful work. Let me just give it some more time, and you'll keep on waiting. You'll keep on waiting. You'll keep on waiting, right? And sometimes it might be true that it is doing the useful work. If you try to stop the program forcefully, maybe it has done work so much that is just about to produce the output and you stopped it. Therefore, we don't know whether to stop it or wait longer. So it is actually the Turing machine halting problem of Turing machine, which is nothing but undecidable. So the first problem is undecidable. The first statement is undecidable, right? They are given statements and they are asking which one is undecidable, and then there are options are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, something like this. Options are there, but we shall examine all of them. If L is a context-free language, then L complement is also context-free. It is undecidable, right? Because context-free languages are not closed under complementation. If L is regular, then L complement is also regular. It is decidable, isn't it? Why? Complementation is closed. It is decidable. If L is recursive, then L complement is also recursive. It is also decidable. I told you that recursive languages are closed under complementation. We have seen enough examples and we have seen enough theorems on this also, right? So it is very important to remember that under the complementation, context-free grammars are not closed, context-free languages are not closed. Regular is closed, recursive is closed, but context-free and recursive enumerable are not closed. Please remember it. Definitely there will be one question on that. Complementation of the languages. Okay, fine. Let sigma be a finite non-empty alphabet and let 2 power sigma star be power set of sigma star, which means they are saying about some alphabet sigma, and then sigma star is nothing but set of all strings and 2 power sigma star is nothing but set of all languages. We have already seen such a problem, right? So if sigma is set of all this, sigma is the alphabet, then sigma star is set of all languages and 2 power sigma star is set of all sorry, sigma is set of all, sigma star is set of all strings, and 2 power sigma star is set of all languages. And I have already proven that this sigma star is countable and 2 power sigma star is uncountable. In fact, sigma star could also be used to represent, sigma star is a superset of set of all Turing machines. Therefore, Turing machines are countable and set of all languages are uncountable. So, we have more languages than Turing machines, right? So, what is the option? 2 power sigma star is uncountable and sigma star is countable. C is the option, right? Again, this question is also about decidability. It is decidable whether an arbitrary Turing machine halts after 100 steps. So the question is, given a Turing machine, they are asking whether it will halt after 100 steps or not. So it is simple. Just run it for 100 steps and then you stop your algorithm and see whether the Turing machine is halting or not. If it halts, say yes. If it doesn't halt, say no. Now your algorithm is able to say yes or no in just 100 steps, which means your algorithm is able to halt or stop. Therefore, it is decidable. So since your algorithm, you are able to give an algorithm which is able to stop after some finite number of steps, how many steps? 100 steps, it is decidable. So whenever the question is like this, given a Turing machine, will it halt after 10 steps, will it halt after finite number of steps, something like that. So it is decidable because you need not run the Turing machine forever, you have to run only for fixed number of steps, right? Therefore it is decidable. Now a Turing machine prints a specific letter, so it is actually undecidable. Now how can we prove any problem is undecidable is take a known undecidable problem and then convert it to this problem, then we can say that this problem is undecidable. Now what is the known undecidable problem? Halting problem, right? So now the question of whether the Turing machine halt or not is undecidable. Now I will convert that question into this question. Check this. How I will convert it is, instead of asking whether the Turing machine halts or not, whenever any Turing machine is given, and if you are asking me whether the Turing machine halts or not, then I will just modify it a bit. Why do you think that a Turing machine will halt? Whenever it come across the dead configuration, then what I do is, from every dead configuration, I will make that Turing machine print the letter Y. Yes, I halted. See, it is not very easy to understand. Maybe just try it. See, it is simple in the sense if you are willing to understand it, it is simple. Try it again. Let us say Turing machine is given, and the question is whether this Turing machine halts or not. Now I want to change this question itself. In order to change it, what I do is, why do you think that Turing machine halts? Only because of dead configurations. Whenever it come across the dead configuration. What is dead configuration? It is in one particular state and is looking at some particular input, but then for that state, for that input, the transition is not defined, isn't it? Now what I do is, I'll take a Turing machine and I'll convert it in such a way that for all the dead configurations it might come across, I'm just going to print a letter Y. Therefore asking whether a Turing machine will halt or not is now as good as asking whether the Turing machine will print a letter or not, right? So we converted the problem of halting into the problem of printing. So what can we say? The problem of printing is undecidable. Why? We already know that the problem of halting is undecidable. Therefore definitely the problem of printing must be undecidable. Otherwise what happens? The original problem of halting will become decidable, which is already proven to be undecidable. Okay, you please do it 2 or 3 times. Okay, I'll just take a diagram and explain you. Those who didn't understand it, just watch it once. Those who understood, you can move on. You can skip this topic. Now I'm saying that I have a Turing machine and I'll modify the Turing machine in such a way that for every Turing machine I can modify it in such a way that whenever the Turing machine halts, I'll make it print a letter Y, right? Therefore for every Turing machine I can compute a different Turing machine TM1 for every Turing machine. Now what happens is, halting Turing machine can be stated in terms of this problem, or halting problem is converted to printing problem now, right? Now halting problem is converted to printing problem. It is already known that halting problem is undecidable, right? And now what happens if printing problem is decidable? In case if printing problem is decidable, then definitely halting problem becomes decidable. But then it is already, we have proved that it is undecidable. Therefore, this definitely cannot be decidable. These two should be undecidable. This is how we prove that problems are undecidable. We take an undecidable problem and convert it to some other problem, then we can say that that problem is undecidable. Got it? So in this case, printing is undecidable. Turing machine computes product of two numbers. This we already know. Turing machine can add the numbers, compare the numbers, product, divide. It will do every damn thing that a mathematical function can do. Therefore, it is as powerful as a computer in terms of the mathematical functions. It is decidable. It is well known. You need not worry about it. None of the above. Therefore, what is the answer? Undecidable is printing one. Right? Fine. Which of the following statement is correct about the finite language over sigma? So they are saying that the language is finite. So when a language is finite, it is simply regular, right? Okay, let's see all the statements they are given. But this question is tricky in the sense they are saying strongest correct statement. So strongest correct statement means it is like this. If a language is regular, saying that it is regular is strongest. Saying that it is context free is not strongest. It is true that it is context free, but then it is not strongest. Just use your intuition like this. See, if a language is regular, saying that it is regular is strongest. Saying that it is context free is not strong. And saying that it is recursively enumerable is not stronger at all, isn't it? So which one is better? You try to say it the lowest as possible, which means tightly bounded. So that is what I think you are getting this. Tightly bounded means say the strongest statement about it. Okay, I'll just take this example. Now they are saying that it is a finite language. Then which of the following could be true? It could be undecidable. Decidable or a language being decidable or undecidable means membership algorithm. Okay, when they are talking about a language, and then when they are asking whether it is decidable or undecidable without giving any question, what is that they are talking about is membership algorithm. Actually, if the language is finite, the membership algorithm is always there. So how does the membership algorithm work? Take the entire finite language and store it in the input buffer. Then given any string, you compare with every string. If it is present in it, then it is yes. Not present, no. Anyway, our algorithm is going to stop after scanning the entire input. Got it? Therefore, it is decidable. So for every finite language, there is always algorithm determining its membership. Therefore, it is always decidable, right? And then it is Turing machine recognizable. Obviously, it will be recognized. Turing machine is nothing but a program. Just now I have given an algorithm. Algorithm can be written into a program, and now that program could be given into a Turing machine, right? Therefore, it is Turing machine recognizable. Fine. It is fine. It is right. First one is wrong because it is not. It is decidable. Second one is it is Turing machine recognizable. It is also right. Third one is it is a regular language. It is also right. And fourth one is it is a context sensitive language. It is also right. Every finite language is regular. I think you remember it. So definitely it is regular. Saying that it is regular is tightest or strongest. And saying that it is CSL is also right, but then it is not stronger. And saying that it is recursively enumerable. Turing machine recognizable means recursively enumerable is not very strong, right? So which is the answer? The stronger one is, the correct one is C. The reason is, if you say that it is regular, it already implies that it is CSL as well as Turing machine, right? But then if you say CSL, it does not imply that it is regular, or if you say Turing machine, it does not imply that it is regular or CSL. So tell me one answer using which other answers can be derived. So once if I pick up this answer, all the other answers are implied. Therefore, that is why it is strongest. It is a bit tricky. Be careful for such questions. Now look at this question. It is asked in GATE 2001. Consider the following problem. Given a Turing machine capital M over the input alphabet sigma and any state small q, this is off, and any state small q of capital M and a word W belongs to sigma star, does the computation of capital M and W visit the state q? So the question is like this. They are saying that they will give you a Turing machine, okay, and they are saying that they will give you a string, and now they are asking whether when I run this string on this Turing machine, will this this Turing machine, will it ever go into a state, some state q? That is what is asked. So what they mean is, Let us say there is a Turing machine and it is having states like this: Q0, Q1, Q2, and somewhere there is Q, right? That is what they have states. And now the input is given here, W. Now they are saying that if this Turing machine is given this input string, will this halt? Will this Turing machine ever visit? It is not halting. Will this Turing machine ever visit this state Q? So what we could do is we would actually convert this problem into halting problem. How we could convert the problem into halting problem is, you know what a halting machine is. Let us assume that there is some Turing machine given, right? And now when do you think that a Turing machine will halt? Only when it is going to hit the dead configuration. Dead configuration means we are going into a state and we are looking at an input symbol, and for that state, for that particular input symbol, the transition is not defined. If Turing machine doesn't know what to do, then it is going to halt. Otherwise it will keep on working, isn't it? Now what I do is I'll just modify it. Let us say there are all states like this and every state is having some dead configuration, which means some move is undefined. Then what I do is, for all the dead configurations, I'm going to give a transition to the special state called Q, right? Now whenever the actual Turing machine halts, the modified Turing machine will halt in a state Q. Therefore, the halting problem is now converted into visiting problem for a state Q. Previously, we have converted the halting problem into a printing problem of some letter, isn't it? Similarly, I did the same. So, whenever the Turing machine is going to halt in some state, I have just modified it in such a way that instead of halting there, it will just take a transition and halt in a state Q. Therefore, if the original Turing machine halts, then the modified Turing machine will halt in state Q, or the computation will visit state Q. So the halting problem can be converted into the visiting problem. Therefore, what can we say? Since the halting problem is undecidable, this visiting problem is undecidable. Therefore, the answer for this question is, it is undecidable. Undecidable. Okay. So before concluding anything, in this question they have used a new term called as partially decidable. Generally, the partially decidable term is not very important, and many textbooks and many authors, they don't really use this term, even though there is a concept called as semi-decidable or partially decidable. Generally no one is interested in that, but in this GATE question they have really used that word partially decidable. Therefore I'll just tell you what a partial decidability is, and then in case I don't think that they'll ask it again and again, but since they have asked it, let's see it what it is. It is not very important, but then now so what is decidability? If there is an algorithm which will definitely stop after few steps, that is what is algorithm, and then if it says yes or no, then definitely it is decidable, right? And anything which is not decidable is undecidable, which means if your algorithm is not going to stop at least for one instance of the problem, then it is undecidable. So actually there are two types of problems can be classified into basically two types. Some problems are decidable and some problems are undecidable. So what does it mean? If there is an algorithm for a problem, which algorithm will definitely halt. If there is an algorithm, then it is decidable, right? If there is no algorithm, it is undecidable. In terms of Turing machines, what can we say about decidable and undecidable is, if the Turing machine always halts and say either yes or no, then it is decidable. If the Turing machine does not halt, or if the Turing machine does not halt for some of the inputs, then I say undecidable. Now in undecidable, again it can classify it into two types. One is partially undecidable, and completely undecidable. So what does it mean is, some of the problems can be so let us say we have undecidable, which means for some of the inputs it is going to be fall into infinite loop. Then now we can classify it like this. If for some of the strings, if your Turing machine is going to whenever the string is present in the language, for all the questions with an answer yes, if the Turing machine halts, and for all the questions with the answer no, the Turing machine may halt or may fall in infinite loop, which means at least it is able to halt for some of them, right? That is why it is called partially partial, right? Therefore, recursively enumerable languages are partially undecidable, which means for the strings which are present in the language, Turing machine is going to halt and say yes. If the string is not present in the language, it may say no, or it may fall in infinite loop, right? Therefore, most of the problems are partially undecidable. Even the halting problem is also partially undecidable. But then we are not really interested in these two classifications. We are interested in main classification, decidable or undecidable. That's it. We don't want to get into this again partial decidability, because if the Turing machine is not going to halt, it is useless. I mean, if it is not going to halt for all the inputs, what is the fun in saying that it will halt for some of them? I cannot use it anyway, isn't it? Because my inputs are going to be from anywhere, right? So just remember this. Again, undecidability is subclassified into partially undecidable and completely undecidable. Partially undecidable means at least for the problems with yes answer, our Turing machine will halt, and the problem with no answer, it may fall in infinite loop. And completely undecidable means it will never halt for anything that you give. That is completely undecidable. And anyway, most of the problems we have seen are partially undecidable, and recursively enumerable languages are especially partially undecidable, because Turing machine halts for all these strings which are in the language, and they don't halt for the strings which are not in the language, right? And recursive languages are decidable, because for every string it is going to halt and say yes or no. Therefore, that is completely decidable. So in case this question is not decidable but partially decidable, which means we cannot halt the Turing machine on all the inputs, but then if the input string is in the language, then the Turing machine is going to halt and say yes. Therefore, half of it is able to solve it, and the remaining half, if the strings are not in the language, then it is not going to solve it, or it is not going to stop. So it is not decidable, which means undecidable but partially decidable. Okay, instead of calling it partially undecidable, we call it partially decidable. Okay, partially undecidable or partially decidable, both are same. Let's call it partially decidable, right? That is a better term. Okay. Now this is a problem about how you given any problem which is undecidable, how could you find out some other problems which are undecidable, or how do you prove that a problem is undecidable? This is a problem about it. Okay, now let us say there are two problems, A and B. Always is right. See, this question is given wrong in every book. Almost every book, this is wrong. You just follow whatever method I'm saying. Okay, and again I'm going to visit this problem at P, NP, NP complete later. The same method is used. Okay, just see this. Now assume that there is a problem A which is already well known and which has been already proven to be undecidable, which means there is no algorithm which can say that which can solve this problem. Now if I take this problem and if I convert it into another problem in such a way that answer to this problem is going to be answer to this problem, which means if I convert this A to B in such a way that answer to B, if answer to B is yes, then answer to A is yes, answer to B is no, answer to A is no, in such a way that if you could convert this problem, then definitely B has to be undecidable. B will be undecidable. The reason is, in case if B is decidable, then what happens is I will convert every instance of A to B in polynomial time. I mean, here the conversion has to be done in polynomial time, right? I'll convert every instance of A to B, and then I'll apply the algorithm. Polynomial time in the sense you have an algorithm. Okay, think about it. There is some method which using which we should be able to convert it to B. If there is no algorithm, that means that there is no conversion between A and B. Now assume that for every instance I'll take it and convert it to B, and now I'll solve B because it is decidable. Therefore this one will become decidable. Then why did you initially say that it is undecidable? Contradicting, isn't it? Simple. If initially you are saying that it is undecidable, A is undecidable, which means there is no algorithm existing, and we have shown a proof for this. Therefore in future no one can say that it is decidable. Now if A can be converted to a problem B, then definitely B should be undecidable. The reason is simple. So if B is decidable, then it turns out that A is decidable, but then which is contradicting our initial known fact, which is A is undecidable. Therefore, what can you say? If an undecidable problem can be reduced to some other problem, then that problem will become undecidable, right? So that is the proof. We cannot say that if a decidable problem is converted to a, okay, that is how we shall see later again with PNP and P class in algorithms, how to use this concept again. But for now, just solve this question using this concept. Now they are saying that P1 is decidable and P2 is undecidable. Then they are giving you some options about P3. P3 is a new problem. Now P3 is decidable if P1 is reduced to P3. See this, they are saying that P3 is decidable if P1 is reduced to P3. See, already there is a problem, and when you are trying to reduce it to P3, you are not saying anything about P3. See, P3 has to be, if you have to say that P3 is reducible, P3 is decidable, then P3 has to be decidable, reduced to some other problem. Then only you can say that it is decidable, right? So it is not true. And next one is saying that P3 is undecidable if P3 is reducible to P2, which means you are taking P3 and if you are reducing it to P2, you are saying that it is undecidable, which is wrong, right? So what is the next option? P3 is undecidable if P3 is reducible to P3, which means if P2, which is the undecidable problem, if it is reduced to a problem P3, then the resulting problem will become undecidable, because since this is undecidable, this will become undecidable, right? So remember this. Option is C. So if there is any undecidable problem and if you are able to convert it to some other problem, that problem would become undecidable. And on the other hand, when can you say that a problem is decidable is, let us say there is a problem A and there is a problem B. If it is already known that the problem B is decidable, and if there is a conversion algorithm from A to B, reduction algorithm, then I can say that A is decidable. The reason is, if B is having an algorithm, then I can convert every instance of A to every instance of B and solve B. Therefore, there is a solution to A. So since we found out the algorithm to solve A, then we can say that it is decidable, right? So they use these two proofs. So what is the proof? Maybe you can write it down somewhere. See, A, B. If it is already known that A is undecidable, and if I could reduce A to a problem, then this problem will become undecidable. Okay. And now if it is already known that B is decidable, and if I could reduce a problem A to this problem, then A will become decidable, because we have found out the algorithm, right? So these two are important. Okay. And this is saying that P3 is decidable if P3 is reducible to complement of P2. That is wrong. P3 is, if P3 has to be decidable, then P3 has to be reducible to P1. See, if this is reverse, which means if P3 is reduced to P1, then it is true. In this case, if P3 is reduced to P1, then what happens? Already for P1 there is an algorithm, and now we have an algorithm to convert P3 to P1, and now therefore we found an algorithm to solve P3. If this is reverse, then this first statement would have been true. You just remember those two rules, you can answer any question, right?